Okay, I think it's time to start. So, hi everyone. Good morning, good afternoon. Welcome to our second day of the conference ICMAM 2024. For today's first talk, is for me a huge honor introduce to Professor Hiraku Nakajima, who is professor of the Kavli Institute for the Physics and Mathematics for the University of Tokyo. Professor Nakajima is a worldwide known mathematician, mainly for his important contribution in the interplay between geometry and representation theory. Also, Professor Nakajima is now the president of the International Mathematical Union. Professor Nakajima has received many awards, such as the Geometry Prize, Spring Prize of the Mathematical Society of Japan, Hall Prize in Algebra, Japan Academy Prize, among others. We're really grateful with you, Professor Nakajima, to accept our invitation. And I hope all the participants enjoying your talk entitled 3D Quantum Field Theories and Lagrange Duality. So welcome, Professor Hiraku, and time is yours.
Okay, thank you very much for invitation, and I'm very glad to give a talk here at ICMAM. So I will talk about the 3D quantum field theory and Lagrange duality. So I understand that this is very early for you and for most of you. So I don't speak about the detail of the result, and I just want to illustrate the philosophy or idea behind the relation between the quantum field theory and Lagrange duality. And if you know much more detail about the relations, I wrote an article and posted it in the archive. So this is about 10 pages long, so it's not so long. I hope many people can read easily. And if you study more seriously, then there's a very long abstract article by Benji Sakelaris and Venkatesh. So this was also put on the archive. Okay, let me start. So first, I prepare some notion from the topological quantum field theory, or more precisely, the axiomatic approach to the topological quantum field theory. So this is due to that here. So, so this is the definition of the topological quantum field theory. So I consider d-dimensional topological quantum field theory. So I denote it by Z. So Z is an assignment. So for d minus 1 dimension, d is a positive integer. For d minus 1 dimensional closed manifold, closed mean oriented without boundary. So suppose X is a d minus 1 dimensional closed manifold, then G of X is a complex vector space. So in the physical terminology, physical literature, it is called quantum Hilbert space. And the d-dimensional manifold M with boundary Dm is a vector in vector space assigned for boundary. So M is a d-dimensional manifold, and the boundary is a d minus 1 dimensional manifold. And dm has no boundary, so this is a closed manifold. And so you can, by the first requirement, G of dm is a vector space, and the G of m is a vector in Z. And you require several constraints. So for example, if you have disjoint union of two d minus 1 dimensional manifolds, x1 and x2, then the corresponding vector space is a tensor product, G of x1 tensor with G of x2. And in particular, if, for example, x2 is an empty set, then G of x on left-hand side and the first term of the right-hand side is equal. So G of x2, G of empty set must be in the the one-dimensional vector space. This is also implicitly required in this statement. And if you consider X with opposite orientation, then this is a dual space to the vector space assigned for X. So G of X star is dual space. And also, if you have D manifolds, which is a union of two D-dimensional manifold, M1, M2, with common boundary in the middle. So I denote the common boundary by X. And you can glue M1 and M2 along X to obtain a new D-dimensional manifold. So which I denote by this symbol M1 union over X with M2. Then this is there is a left boundary and the right boundary, and from this requirement, this gives an operator from the vector space assigned for this left boundary to the vector space assigned for right boundary. And this is a composite of G of, oh, sorry, I should go from right to left. So this is a right to left. This is G of M2. G of M2 is a homomorphism from the vector space for here and the middle. And the G of M1 is a vector space for middle to the vector space for the left. So this is equal to the composite of those two linear maps. So that is a requirement. So if you are familiar with quantum mechanics, so this horizontal direction, you can regard this horizontal direction as an analog of the time direction, and you have the Hilbert space at time t, and there's Hilbert space for t prime, and so on. But in this topological quantum field theory, so this assignment depends only on the topology of the X, topology of the smooth differentiable structure on X. So in particular, length of the interval is irrelevant information. In that sense, this topological quantum field theory is a toy model of the quantum field theory. But nevertheless, because we are considering higher dimensional space, so there's time and space direction can be arbitrary. So this is really quantum field theory. In that sense, it's more interesting than the quantum mechanics. Okay, but here I said this is a definition of topological quantum field theory, but today I use this in an informal way. So if G is defined for arbitrary D-dimensional manifold, so if I can take X or M to be arbitrary D-1 dimensional manifold or D-dimensional manifold, then it is known that G of X is automatically finite dimensional. So if you consider this kind of cylinder, and you bend it to this kind of, oh, maybe I should write the two. So you consider the tube and then bend it to then you get pairing between the perfect pairing between the dual space and the original space. So it means that you have the finite dimensional manifold. And this is a finite dimensional vector space as G of X. And this is too restrictive for our purpose. So in practice, we consider G as a G in an informal way, and this assignment is defined only particular class of D-dimensional manifold or D-1 dimensional. So then there is no contradiction that the G of X could be infinite dimensional space. And in fact, in quantum mechanics, G of X is Hilbert space, and it is usually interesting if G of X is indeed infinite dimensional. So in order to include interesting example, we need to allow such, we don't want to require Gx to be finite dimensional. So it means we need to relax definition of the topological quantum field theory slightly, so that this is defined only particular class of D-1 dimensional manifold and D-1 dimension. Okay, then for application to Lagrange correspondence, we need to extend this topological quantum field theory. So we allow so-called codimension defects. So in practice, we consider manifold M with corners in general. So this is a D-dimensional manifold, and we have D-1 dimensional boundary. But we have also horizontal, so this is vertical boundary, which appears already in the previous page. But we also allow the vertical boundary like this. So we have blue boundary and red boundary and green boundary like this. Then we assign the linear map from this manifold with corners, and for here we have the in boundaries, or we have the manifold with boundary. So this is a difference from the previous page. So boundary could, because we start with manifold with corners, the boundary may be the manifold with boundary. So this appears, for example, if you consider the quantum field theory of the space of all maps from this kind of manifold with corner to some target space T, and we impose boundary condition for those horizontal boundaries, which, for example, we choose a submanifold S in T, and we require the map satisfy the property that f of the horizontal boundary is contained in this submanifold S. So if you have those different colors, then you imagine the case that you have the submanifold for blue and the submanifold for red and the submanifold for green. So they might be different ones. And you consider maps F defined on M, whose image of which has image of this boundary, horizontal boundary into the corresponding submanifold. And in the axiomatic approach, you can regard this more general extended topological quantum field as assignment to the following data. So you consider for each boundary condition, you consider is an object in the category. And if you have consider the boundary, vertical boundary like this, then the vertical boundary has boundary which is coming from the intersection between the vertical boundary and horizontal boundary like this. Then by the topological quantum field theory requirement in the previous, we should assign the vector spacing. So then we regard this vector space as homomorphism from left object to right object. So in this way, so from topological quantum field theory extended in this way, you should first consider assign a category, and then for each boundary, you should assign homomorphism between the object and the boundary. And this picture, in the left side, you have the homomorphism from red to blue. And from the right, you have red to green and green to blue. Then this picture means you have the homomorphism from red to green, green to blue, composed to homomorphism from red to green, to red to blue. So this is a composite of homomorphisms in the category. So Fukaya category of a simplex manifold is an example of this kind. So you consider the maps from two-dimensional manifold M, and the target space T is a symplectic manifold. And those blue and red, green and red boundary condition correspond to Lagrangian subvariety in a symplectic manifold. So you can, one of the advantage of this axiomatic approach to this to the quantum field theory, topological quantum field theory is, so you can forget all those original motivation to consider quantum field theory, considering like those maps from the domain to the target spaces. So you can consider the category and the homomorphisms and such kind of things. So then you might have algebraic approach or axiomatic approach to the quantum field theory. That is one of the advantage to use this kind of axiomatic quantum field theory. But intrinsic, motivation of this axiomatic approach is coming from those kind of consideration of the space of maps. Okay, then Kapustin and Witten use this kind of quantum field theory for extended quantum field theory to explain Lagrange duality, more precisely so-called geometric Lagrange duality. So they wrote a paper in 2007 claiming that geometric Lagrange is a consequence of S-duality of four-dimensional supersymmetric Yang-Mills theory. So this Yang-Mills theory is defined for a choice of compact Lie group, or in my talk, so I consider the so-called complication of the compact Lie group. So G is a complex deductive group. For example, if you are not familiar with this notion, then G is just GLN. And in this case, Yang-Mills theory is Yang-Mills theory for connection on a vector bundle of rank n. Then this is a four-dimensional theory, four-dimensional gauge theory. The space-time is four-dimensional. So you consider the space of connections. But we take a particular four manifold of this form. So M4 is some two manifold. So dot is some two manifold, which you can choose arbitrarily. But the other factor is C. So this is a fixed two-dimensional manifold and equipped with the complex structure, namely C is a Riemann surface. So they consider the gauge theory on this particular form of four manifold. Then, by considering the extended topological quantum field theory, like in the previous page, so they have the category of boundary conditions, and they claim that these categories are, in fact, so there is a procedure called twisting, which is a little difficult to explain, but starting from supersymmetric, twisting is a procedure starting from supersymmetric gauge theory to obtain topological quantum field theory. So there are two ways to twist, and you have A twist and B twist. They give a different category. They correspond to different categories. And for one twist, it is a Fukaya category whose target space is T star of band G of C. So you consider the space of maps from this two-dimensional manifold, which I said I allow to move. So then the target space is the T star of band G of C. So band G of C is a moduli stack of the band G bundles on C. So whatever it is some space, and take its contangent bundle. So this is a symplectic manifold, and you can consider the Fukaya category. And indeed, this is a category, or it's another version. You can consider the category of sheaves on constructible sheaves on this moduli stack. So anyway, this is one of the category which appears in geometric language. And if you use another twist, then it is a derived category of coherent sheet or local system on G local system on C. So these two spaces are some spaces which arise from the gauge theory on C. And so you consider the two-dimensional quantum field theory whose target space is G star of Bungie C or a local system. And the object for the first case, object is a Lagrangian submanifold. And in the second case, objects there are kind of generalized the complex submanifold of the moduli stack of local systems. Okay, then the most important statement of Kapstein-Witten was, so this gauge theory is known to have the so-called S-duality. So which means that G Yang-Mills theory for M4 and G check Yang-Mills theory for M4 are in a sense equivalent. So G check is a Lagrange dual group, and you replace G by G check, but you still get the equivalent gauge theory. So in particular, if the gauge theory is equivalent, then the categories of boundary condition should be the same. But because of the twisting, so when I say the gauge theory is the same, so the twisting could exchange. So for A twist and B twist for G, exchange to B twist and A twist for G check. So from this, you get to this statement, the category of the T star Bungie is equivalent to the derived category of coherent sheaves or local system for G check. And this is the naive form of geometric Lagrange conjecture. So people notice that this is not true in strict sense, and you must somehow make a correction to that. But anyways, I will not go into the detail. This is a very rough statement of the Lagrange correspondence. So you have two categories, and the two categories are equivalent. So this is the statement, and the two categories are coming from some sheaves or Lagrangians on moduli space of associated assign defined for the group G and G check for the curve C. So so this is the heuristic explanation why you start even. So it's really strange. So this is a two-dimensional, as I said, this is a statement in the two-dimensional quantum field theory. But they start with four-dimensional theory, and they consider the very specific four manifold, which is a product of two-dimensional manifold, like this. So this reduction, so this is called so-called the dimension reduction. So four-dimensional quantum field theory is changed to two-dimensional quantum field. So this is called dimension reduction. And the idea is that, so you consider the four-dimensional theory, but of this particular form of four-dimensional manifold, product of two-dimensional manifold. And suppose C is very small compared with this another two manifold. Then, so this theory has a different description. So in physics, so many quantum field theory may have many different aspects or descriptions. And this is a particular example. So four-dimensional gauge theory has two-dimensional description. And in this case, the two-dimensional quantum field theory, whose target space is moduli space, which was studied by Hitchin. And this Hitch moduli space is known to be hyperkähler. And if I choose, so it means you have the complex structure I and J and K, which satisfy the cotanient relation. Then if I pick up a particular complex structure, this Hitch moduli space is cotangent bundle of the moduli stack of bundles. And if I pick up another complex structure, this is the moduli space of local system. And in this description of the two-dimensional sigma model, then SDRT becomes more familiar two-dimensional homological mirror symmetry. So these two modular spaces are mirror dual to each other, and the homological mirror symmetry predicts the equivalence between the category for symplectic manifold and the derived category coherencies for the mirror complex. Okay. Then Gayotto and Witten. So subsequently, Gayotto and Witten study the boundary condition. As I said, the category boundary condition is a relevant categories for geometric Lagrange. So it's very natural to study what are the boundary conditions. And they observe that three-dimensional supersymmetric quantum fields give a class of boundary condition. So this three is three because we are considering four-dimensional quantum field theory. And if you consider the four manifold with boundary is three-dimensional. So then three-dimensional supersymmetric quantum field give a class boundary condition. And you can understand also the SDRT, how SDRT acts on the boundary condition. So this is related to the so-called three-dimensional mirror symmetry of three-dimensional supersymmetry. So three-dimensional mirror symmetry is different from the homological mirror symmetry, which I just mentioned. Three-dimensional, but and also in mathematics, it is relatively new subject, but still it is an active research area, and I'm also very much interested in 3D mirror symmetry, and many interesting phenomena has been observed in 3D mirror symmetry. So let me go back to the first statement. So we have example of 3D supersymmetric quantum field theory. So again, we consider the sigma model, which means that we domain is a three manifold because we are considering the three-dimensional quantum field theory. But the target space is a smooth affine algebraic symplectic manifold. Or maybe M is a hyperkähler manifold, like in the Hitchens modular space. And in order to make a relation to Lagrange conjecture, so the four-dimensional quantum field theory start with the choice of the group G. So I assume this M is equipped with the Hamiltonian action of a complex group G. So Hamiltonian means that the G preserves the symplectic form, and also there is so-called moment map for the action. So this existence of moment map is a mild condition, and so anyway, so I will not go into detail. So G basically G acts. G preserves the symplectic. Then for given G and M, you can construct a three-dimensional supersymmetric quantum field theory, at least in the physics level of rigor. In fact, for well-defined quantum field theory, you need to require the so-called anomaly-free condition for M. So M is not arbitrary, and you must assume some condition. But except this, M is arbitrary. Then, because I said that three-dimensional boundary condition is an object in the category relevant for the Lagrange. So it means that starting from the Hamiltonian G space, so G acts Hamiltonian axis, G has M is a symplectic manifold with Hamiltonian group action. Then we should have the boundary condition, and which gives an object in the four-dimensional quantum field theory, which is after topological twist, it is a object in the Fukaya category, and also another twist, it is object in the derived category. So then, so there's, maybe I should say that the quantum field, I should say at the beginning, quantum field theory has no mathematical rigorous foundation. So I use quantum field theory only as a somehow as a tool for investigation, and I don't use it as a proof. But if I combine quantum field theory and those Guyot-Witten and Kapustin-Witten, and then it becomes a mathematical rigorous statement. For given G and M like this, you should have the object in the Fukaya category and also object in the derived category. Then G of M, G acts of M, and those objects are well-defined mathematical objects. So this assignment may be regarded as a conjectural statement in geometry. And SDRA condition. So for a boundary condition, so you consider the SDR boundary condition. Then in many cases, dual boundary condition is just a three-dimensional supersymmetric quantum field theory. But in many examples, this is also coming from another Hamiltonian space, M check with the action of G check. Well, in general, you cannot expect this always holds, but at least this dual boundary condition, which is a three-dimensional supersymmetric quantum field theory, can be at least approximated by those data, G check and M check. And this approximation is a good approximation if M check is smooth, but if it's not genuine dual and if it is bad approximation, then it means M check has singularities. So I will give some example where M is, even though M is smooth, M check could be singular. So it is a reflection of the fact that this dual supersymmetric quantum field theory is not coming from this Hamiltonian G space, but a more complicated space, but it can be approximated by singular target space. And this is somehow closely related to the concept of Coulomb branch. So I can make the following conjectural mathematical consequence. So for G and M, I can assign the object in the Fukaya category, and for and also VCM, which is the object in the derived category. And for M check and G check, I can also assign the object in the derived category and Fukaya category. And under geometric Lagrange correspondence, this Fukaya category is equivalent to derived category. And under this correspondence, equivalence of categories, those objects is intertwined. So that is a mathematical, conjectural mathematical consequence. And if you exchange twists, then you have the opposite relations. So this V for G and M is mapped to the L of G check, M check in this opposite twist. Okay. So for example, this is a base. In fact, this example appears in, it has been observed, and it is very basic example in geometric Lagrange. So maybe right-hand side is easier. So consider M check. The case M check is a single point. So this is a trivial symplectic manifold with trivial G check action. But its dual space is something non-trivial, and this is the so-called equivalent constant Schrodinger's slice. So I don't recall the definition, but S is some vector space or affine space. So there's no notion of origin. So this is affine space, and this is slice in a sense that, so you consider this S is a subset in the dual of the Lie algebra for G, and it has the same dimension as the rank of G, which is the dimension of the torus. And this is a slice for the adjoint quotient. So anyway, so this is a kind of space which appears in geometric theory quite often. Then in this case, one can formally compute the object in the Fukaya category and the object in the derived category. So the object in the derived category for M check is a structure shift. This is the most trivial object in the derived category. And the other is so-called Hitchin section. This is the so-called Hitchin integrable system, and Hitchin section is a section of this Hitchin. And in this case, in fact, if you if you consider the opposite twisting, the people don't know the corresponding object in this derived category. Although the right-hand side, the Lagrangian subvariety in the Fukaya category is just a zero section. So, but this zero section contains a singular point in this modular stack, and because of this reason, it is a little delicate object in the category. So this is one also the reason why people don't understand what is a dual object. So in that sense, I mean, this conjecture has two parts. First, maybe I go back to the previous. Oops. Sorry. So maybe I'm. Do you see my screen yet?
Yeah.
So this assignment from GM to the object. So this is already a conjecture. Like in this example, we don't know what it is. And the second statement is correspondence under the equivalence, the categorical equivalence is also conjecture. And there are some pairs of Hamiltonian spaces, G Hamiltonian space and G check Hamiltonian spaces like this. So for example, so this is in fact the example for this one. And in this case, this is not conjecture. So for general G, this is still conjecture, but for this, it's established. So you consider T star C check. So constant slice is just the whole Lie algebra in this case, and the dual is the trivial space. And if you consider C star acting on the C2, so you have a natural symplectic form. So this is a self-dual, and the action is weight one action. Then the dual is also the same space. This corresponds to the so-called thesis in geometry in Lagrange program. And slightly more generally, so if you consider C2L with still weight one action of C star, then dual space is C star acting on C2 divided by finite cyclic group G mod L. So this is an example where the M dual space is singular. So it has a singularity at the origin. So in that sense, this is a indication that the corresponding space, supersymmetric quantum field theory, is not a genuine space of genuine sigma model, but it is just approximated by the sigma model whose target space is this singular space. And if you consider the C2 but weight L action, then the M check is the same space. Right? So this is also some indication that, so this is duality. So it means that M check of check should be returned back to the original space M. But this is not true if you just naively consider the singular ones like this. So you get different space for the left side, but the M check, this M and this M are different, but M check are the same. So M check, and in order to consider M check of M check for singular M check, then somehow you must be more careful. This is the meaning of this example. And also there's the important generalization boundary conditions, which is called interfaces. So this is a four-dimensional manifold, which is separated by three-dimensional manifold. And then you can consider slightly exotic gauge theory. So in the left region of the four manifold, you consider G1 gauge theory, and upper region, you consider the G2 gauge theory. So you can consider such interface between two different gauge theories. So for example, if you have a space M, Hamiltonian space, with action of G1 times G2, commuting action of G1, G2. So I do not like this. So then you can put this space as a three-dimensional quantum field theory, which interfaces between G1 gauge theory and G2 gauge. Then as a dual gauge theory is G1 check, it is an interface for G1 check and G2 check. And this can be regarded as a functor between the categories, because categories are boundary conditions. So you have the, here is a boundary for G1 gauge theory, but you can, by combining this, you can consider also as a boundary condition for G2 gauge. So you have the functor from the category for G1 and the category for G2. So namely, Fukai category for T star and G1 and Fukai category for T star. So, and also the corresponding functor for G1. Oh, sorry, I think I can make, I make a mistake for G1 check and G2. So this is G1 check and this is G. And this is a commutative diagram. So you have the functoriality for the Lagrange correspondence. And this is very important. And for example, if I take M to be T star of G with left and right multiplication of G, then the SDR is expected to be T star G check with G check action and G check. In this case, in fact, this arrow, these functors are both identity. So it is trivial that this we have this commutative diagram. And so this is not strictly speaking, it's not the example because this is not affine manifold, but Eisenstein series is a functor between the T gauge theory and the G gauge theory. So this is supposed to be given by choosing M as a T star of G mod U. So U is a upper triangular particle. And this SDR is the Eisenstein is an induction, the functoriality functor between T check and G check, defined in the same. And also there's more example of this kind, which is in the physics context, which is not it is called also symplectic quick. But in general, the computation of, in fact, so I didn't write what is the, so this is C2N tensor with C2M with action on SO2N and SP2M. So I didn't write what is equivalent slices. So this is some well-known symplectic Hamiltonian space appearing in geometric representation theory. But the computation of M check is not so simple. So this is some non-trivial statement. And then relative Lagrange duality conjecture due to Benzibi, Lakelaridis, and Venkatesh says that these relations are all tiers of Lagrange duality. So which means that so this kind of correspondence holds for global Lagrange, global geometry Lagrange, which I just formulated, but also global arithmetic Lagrange. So this is a usual Lagrange correspondence in number theory. And also you have the local Lagrange, both local geometric and local arithmetic Lagrange theory. And for all those versions of Lagrange duality, you have similar relations. So which means that for in the usual number theoretic Lagrange program, so you consider this L and B instead of considering them as an object in the category, they appear as a function of moduli space. Moduli space of bundles and moduli space of the local systems, and those are functions of moduli space. And those functions are the same. And for local Lagrange, so you formally take the instead of the usual Riemann surface, you take the formal puncture disk this time. So then instead of categorical equivalence, so this equivalence is supposed to be hold in two categories. So then, these one in geometric Lagrange, usual geometric Lagrange, these are objects, but this is replaced by objects in two categories, which means these are they are itself they themselves are categories. So then those two categories are related by categorical equivalence. So this is a formulation of relative Lagrange duality in local geometric Lagrange. So it means that so you have the very not only particular Lagrange duality, so you have the many very similar statements for all variants of Lagrange duality. So this is one of the interesting parts of this relative Lagrange duality. And for G and M, so this G and M, the S duality for G and M and G check M check is independent of C. So this I didn't emphasize, but I'd like to emphasize here. So they are independent. So if you can compute G check M check for one particular version of Lagrange duality, then you can expect the same G and M, G check M check can be used for all other versions of Lagrange duality. So it means this is very powerful. So once you compute the dual for one Lagrange duality, one version of Lagrange duality, then you can automatically predict similar equivalences in other versions of Lagrange duality. So in that sense, it is important to know that how we can compute G check M check from the given Hamiltonian space G acting on N. And as I mentioned, Guyota and Witten said that this relation S dual is a cousin of 3D mirror symmetry. S dual for the boundary condition is a cousin of 3D mirror symmetry, which is, as I said, is a one hot topic in both mathematics and physics now. And this Benjamin and others in the context of relative Lagrange. So in fact, if you consider the local equivalence for function of this, then somehow you can recover this dual space from the category which is assigned for G and N. So anyway, in either approach, or to make more precisely, there are so the recent advance of the mathematical understanding of this three-dimensional symmetry, which I have been working on with Brevan and my collaborator, Brevan Pinkerberg. So M-check is an analog of the so-called Coulomb branch of three-dimensional quantum field theory, which means that the M-check can be defined very roughly in the following way. So maybe I didn't say at all how maybe I should say that. We come back to this statement. So I mentioned that this category appears is a boundary condition, and I consider the gauge theory on this four manifold and consider the boundary condition. But anyway, so this it's kind of gauge theory on the boundary manifold. So it means that we consider some modular space of the all connections and consider corresponding quantum field theory. So then, so we use a mathematical approach to understand this quantum field theory. So it means that the following. So from G and M, so we cannot consider the space of all connections. So we somehow consider the finite dimensional approximation. So this is a modular space. So this is the absolute minimum of Lagrangian. And I consider this modular space on very particular two manifold, which we call Raviolo space. So this kind of space. So this is a union of formal disk glued along the formal puncture disk. So this is a modular space. Then, so I need some kind of quantization of this modular space. So then in here, quantization, because of supersymmetry, quantization is given by considering the homology. So this is a homology of the topological space. This modular space, I regard this as some topological space, and I consider some homology group coming from this modular space. And I don't take the genuine homology group of this modular space. I need some modification of that, but this is also some technical part, so which I omit. Then this homology group is equipped with the so-called convolution product. So this is a ring, and also it is a commutative ring. So then we recover this M-check as the follows. So this you consider space of polynomial functions on M-check. So this is this commutative ring built from the homology group of this modulus. So this is a very rough idea how to consider how to construct M-check. And this construction has very similar in different tiers of this relative Lagrange program. So in order to consider the corresponding dual object, no, sorry. Let me go back. So this assignment, the objects V and L, those are constructed by considering modular space of G and L. And more detail can be found in my article posted in archive. So then you have the natural several actions. So I don't explain the technical, one very important technical detail. So So in order to define this modular space, I need to assume M to be cotangent bounded to another affine manifold, smooth affine manifold N, and this condition must be dropped. So as I said, we cannot expect M can be M gives a well-defined quantum field cell in general, so we need to assume anomaly-free condition. But at least if we assume this condition, that for T star N, this anomaly-free condition is satisfied. But we need to drop this cotangent boundary condition, and we need to generate the anomaly-free condition. And the second is more complicated. So as we saw, as I illustrated, there are some cases that even though M, if you start with M, smooth M, the M check could be singular. Then in order to get to duality, we want to consider M check of check. Then it means that we somehow need to generalize this construction for singular case. For smoothness is crucially used in this statement because this is a homology group, and in order to get the ring structure, we need a smoothness because cohomology you have the cup product, but homology group you don't have product in general. So smoothness of N or M are hidden, secretly used in here. And for example, if you consider T star G with G action, then the dual is known to be nilpotent cone. And most difficult question is computing the M check of check, S dual of M check, dual of dual. So we expect the dual of dual to be the original space, but as I illustrated, so the construction M check is highly non-invertible. You start with M, you consider the modular space, and you consider the homology group. So these process seems to forget many information of the original M. So if you apply M check again to M check, then there's no reason to return back. But so far, if we consider the case when M check is smooth, then it seems M check seems to be the original space. So this seems to be true, but we still don't see any clue why this to be true in general. Okay, thank you very much. I stop here.
Thank you, Professor Nakajima, for your night talk. We have some minutes for a couple of questions. Maybe someone can raise your hands right on the chat. I don't know if we have some question in YouTube.
Okay, maybe I would like to make a question to Professor Nakajima.
Yes.
Professor, sorry, I am not expert in your field, right? I found very interesting your talk, but could you please explain, maybe in a general way, which kind of, let's say, information one has to think that the relative Lagrange duality conjecture is valid?
I'm not sure I understand the question. So you mean that you're asking the quick condition for M and G?
Right, maybe conditions on M and conditions on G.
So that is also the part of conjecture, I must say. So in this relative Lagrange of Benziger and others, they assume the so-called hyperspherical Hamiltonian space. But it seems this is too restrictive assumption, and if M and G are hyperspherical, then the dual M check and G check is also hyperspherical and smooth, in particular smooth. And there are lots of examples where the M check is singular. And in that case, in that such kind of situation, I don't know what is the correct formulation of the relative Lagrange duality. So somehow you, as I said, if you just naively consider the example, there are examples where you have the two m's, two different m's which give the same singular m check. So if you just consider then the duality is not valid in this example, if you just formulate naively. So I still don't know what is the correct formulation, including if you want to include singular Hamiltonian space. So this is also part of the question. And I believe that the supersymmetric quantum field theory, in the level of the supersymmetric quantum field theory, this operation seems to be well defined. So this Hamiltonian space is just approximation. So we really need more deeper understanding quantum field theory. But still, this is very difficult question.
Okay, thank you. Thank you very much for your very interesting talk. Okay. It seems, sorry, that we don't have more time for questions to Professor Nakajima. So just Professor Nakajima, thank you very much for accepting our invitation. Welcome forever to ICMAM Latin America, and thank you for supporting our conference.
Thank you very much.
Ya no estás con el micrófono
Hola,
cerrado.
¿qué tal? Voy a probar de
Buenos días.
compartir pantalla. Buenos días, ¿cómo
¿Cómo
están?
está, profesora?
Muy bien, muchas gracias. Voy a probar de compartir pantalla. Ah, no, todavía no puedo.
¿Ya está habilitada para compartir pantalla?
Lo que pasa es que quiero compartir desde la tablet que aparece, que no es en mi computadora, que aparece con nombre y apellido, es la tablet que aparece como Andrea, nada más.
Andrea, ok, ya.
Sí,
Sí,
gracias.
yo-
Pruebo. Ah, ok. Ahora debería.
Buenos días, ¿me escucha?
Sí, sí.
Ok, es que hoy estoy con el micrófono de un lado y la cámara del otro. Entonces,
De acuerdo.
aquí vamos a estar. Muy bien.
Perfecto, bueno, ahí pude compartir, así que todo bien.
Bueno, profesora Andrea, entonces podemos iniciar con
Cuando
su-
quieran, gracias.
Bueno, muchas gracias a todos los que continúan con nosotros en esta sesión, segundo día del ICMAM Latinoamérica 2024. Y vamos a tener ahora el placer de escuchar a la profesora Andrea Solotar. Voy a hacer la presentación en español y luego en inglés. La profesora Andrea Solotar es profesora titular de la Facultad de Ciencias Exactas de la Universidad de Buenos Aires e investigadora senior del IMAS, CONICET Argentina. También es asociada senior del Centro Internacional de Física Teórica, ICTP, de Trieste, Italia. En 2023, la Academia Nacional de Ciencias Exactas, Físicas y Naturales otorgó a la profesora Solotar el premio Consagración de las Matemáticas, en reconocimiento a sus destacadas contribuciones a las matemáticas. Es un honor para nosotros contar con la profesora Solotar en este evento. Gracias por aceptar la invitación y bueno, procedo ahora a hacer mi mejor esfuerzo con el inglés. Andrea Solotar is full professor at Facultad de Ciencias Exactas de la Universidad de Buenos Aires and a senior researcher at IMAS, CONICET, Argentina. She's also a senior associate at International Center of Theoretical Physics, ICTP, in Trieste, Italy. In 2023, the Academia Nacional de Ciencias Exactas, Físicas y Naturales awarded Professor Solotar the Mathematics Consecration Prize in recognition to her outstanding contribution to mathematics. It is an honor for us to have Professor Andrea in this event.
Thank you. Thank you.
She's going
So,
to speak
yes,
about
please.
on the tau tilting Hochschild cohomology of an algebra. Thank you, Professora Andrea. Go ahead.
Gracias, Diana. Thank you very much for the introduction, and thank you for inviting me. I'm very happy to talk in this meeting. And as it was mentioned, well, I'm going to write in my tablet, I am going to talk about Hochschild cohomology, as it's quite usual, and something that is called tau tilting, that is theory, a tool appearing in representation theory. And what I'm going to tell is a joint work with Claude Sibils, Eduardo Marcos, Claude from Montpellier, Eduardo Marcos from Sao Paulo, and Marcelo Lancilota from Montevideo. And one part of this is preprint in archive, and the second half, or a bit less than the second half, is a work in progress. Okay, so Hochschild cohomology is a cohomological invariant which is associated to, let's say that lambda is an algebra. For me, in this talk, it is going to be a finite dimensional, always a finite dimensional algebra over a field K, and let X be a lambda bimodal. By a lambda bimodal, sometimes I will say lambda bimodal, and sometimes I will say left or right module over the enveloping algebra. This is the enveloping algebra that I will also call lambda E. It's a tensor. Tensors are always over K module, either on the right or on the left. Okay? So it is a very, very well-known theory from the 50s, 1950s, first defined by Hochschild and then redefined, let's say, or studied in a different way as a cohomological functor. And it is important because it allows to distinguish among algebras that are not derived equivalent. Well, it has lots of results on Hochschild cohomology that have consequences about the algebra have been obtained during, well, since the 50s. And well, so we look at this as invariant. So the notation that we will use for Hochschild cohomology is the cohomology of the algebra lambda with coefficients in the bimodal X. And for X equal to lambda, H, the Hochschild cohomology with coefficients in lambda, which is a lambda bimodal, is going to be denoted just by a double H of lambda. Okay, so this is a well-known theory. On the other hand, we have tilting theory. So first of all, tilting is a theory, you know, maybe Morita equivalences. So two algebras, and if two algebras are Morita equivalent, then their categories of, it is equivalent to the categories of modules are equivalent. And then as a consequence, the category of bimodules are also equivalent, okay? So we have a generalization of this, which is given by a tilting theory. And then, some years ago, it has been also generalized to tau tilting, and this is from 2014, and it's work by Iyama, Adachi, and Reiten, either Reiten. Okay, so it has many applications in representation theory that I will not mention today. So what is tau here? Because I mentioned tau tilting, but what is this tau? Okay, so how is it defined? Let me give you the definition. So suppose A is a finite dimensional K algebra, I changed names because I will get back to lambda at some points, and M, a finitely generated A module, okay, let's say a left A module, then one can consider the minimal projective presentation of M as a module. And so we start with a projective A module P0 and then a projective P1 that covers the kernel, and we have a map that is called D1. Okay, we can continue the resolution, but for the moment we are just interested in this presentation. So by applying a functor home, it induces the following sequence, which is not exact. So it's applying the contravariant functor. So we have, of course, not to M, but just to the part of the resolution, P0 into A, and then we have a map D1 start going to from A, P1 to A, and well, in principle, we should stop here, but we are going to consider the co-kernel of this map, D1 star, okay? And then we have a 0 here. And this co-kernel is what is defined as the Auslander-Ruyten translation of M, okay? That we are going to define, like to denote like this. And finally, tau of the module M is defined as the dual, the K-dual, okay? This is the K-dual of this Auslander-Ruyten translation of M, okay? So the dual is just there because we want things to be covariant and not contravariant, okay? This is why we have this dual there. So some remarks about this. First of all, there exists an exact sequence of left A modules that starts, it's just dualizing the previous one, starts with tau M and then continues with the dual of A of P1 into A, and then of course continues with the dual of A of P0 into A, and that's it, okay? Second remark is that if M is projective, then of course, in this case, P0 is M and P1 is 0. So in this case, we have that then the tau of M is just equal to 0. Okay, so it's not an interesting case. Okay, this is because already the Auslander-Ruyten translation is 0. And third remark here is that it does not seem this, when I say it is tau, does not seem, in principle, presented in this way, to be a cohomological functor. But even though this will not be a big problem, okay? So please, if you have questions, just interrupt me, okay? Okay. So first, well, a theorem, a very famous theorem, which is called the theorem of Auslander-Ruyten duality, is that in the previous situation, so given A finite dimensional and A modules left, A modules, let's say M and N, we have that the first X space of M with coefficients in N is equal, in fact, is isomorphic, but X already is defined up to isomorphism, to the dual of the home linear maps from N to tau of M, but we still have to do something here because, for example, I said that if M is projective, then, well, this is okay because tau of M is going to be 0 and the x1 is also going to be 0. But suppose, for example, that N is injective, then the x is going to be 0, but the right-hand side is not going to be 0. So we take the quotient by morphisms that from N to tau of M that factorize through injective. Okay? So in this way, if N is injective, then we also obtain 0. So remark, if N is injective, we get trivially 0 equals 0. Okay, so but it's necessary to divide by this to take this quotient. Okay, so well, this is a very important theorem because it relates this cohomological functor, the x1, with the dual of a home. Well, it's with this tau that is not a cohomological functor, and well, it's a very useful relation. Okay, so just two more remarks. So remarks 4 is that, well, as I mentioned, the formula relates x1 with this functor tau, and the other one is that the x1 of Mn, if we just look at the home without taking the quotient, well, we will have an inclusion. Okay? So now, after having talked about tau, let me recall something about Hochschild cohomology. So, as I mentioned, now we have, suppose that we have lambda an algebra and M a lambda bimodule. The Hochschild cohomology of lambda with coefficients in M is defined as the X functor over the enveloping algebra lambda tensor lambda op of lambda with coefficients in M. Okay? So now we are going to set the algebra A equal to this lambda tensor lambda op, lambda enveloping. Okay? And so we are going to consider the functor tau for bimodals, okay? Because lambda is going, A is going to be this algebra, the enveloping algebra of lambda. Okay? So here comes our definition. We started by defining the what we call the tau Hochschild cohomology in degree 1 of the algebra lambda, and we define it as the, well, as something that I mentioned before, the dual of the home over our algebra A of lambda with coefficients in tau lambda. Okay, so looking at the previous thing, we kind of forgot this part of taking the quotient. Okay? Okay, so this is a new object. So we started studying this new object, and in principle, we started with relations with tilting theory, and we got some results, but nowadays we are interested in this new invariant because of other reasons that I will mention in a while. Okay? So we also defined something that is called the excess of lambda. Okay, so we call this the excess of lambda. And the excess of lambda is a positive integer, which is the difference between the dimension of this tau cohomology in degree 1 minus the dimension of the usual Hochschild cohomology in degree 1, okay? Because thanks to this inclusion here, okay, we always have, by taking A equal to the enveloping algebra of lambda and M and N equal to lambda, okay, that the Hochschild cohomology is contained in the tau Hochschild cohomology in degree 1, okay? So we also started studying this number, okay, because we wanted to find for which types of algebras this excess was going to be 0 and when it was going to be different from 0, okay? So let me recall something that will help to understand this tau Hochschild cohomology in degree 1, so that for x lambda bimodule, we have the invariance and the co-invariance of the action of lambda over A, okay? And of lambda tensor lambda opposite. So the invariance that we denote like this, x superscript lambda, is just the 0 Hochschild cohomology of lambda with coefficients in x, and it is just the form lambda e of lambda with coefficients in x. And the co-invariance that we denote with a subscript is just the homology in degree 0, and it turns out to be x tensor over the enveloping algebra with lambda, okay? So we have a first lemma saying that the tau 1 Hochschild cohomology is equal to the co-invariance of the Auslander-Reiten translation of lambda. That is, in fact, to the Hochschild cohomology in degree 0 of lambda with coefficients in this Auslander-Reiten translation of lambda. Okay? I will not do the proof of this lemma. I will maybe just do one proof today because it's just using homological tools. It's a bit technical, okay? So I just wanted to mention this. So the problem is the problem now was how to compute the excess of lambda, okay? And what is it related to? Okay? So we have a proposition allowing us to compute the dimension of this Hochschild tau 1 Hochschild cohomology of lambda, saying that it is the alternate sum of the dimension of the center, that, as you know, the center is the cohomology, Hochschild cohomology in degree 0, minus, and here I will use something that is that if you have lambda, a finite dimensional algebra, it is Morita equivalent to, and I will suppose that since Hochschild cohomology is Morita invariant, to a quotient of a path algebra, so Q here is a finite quiver, divided by an ideal I, a two-sided ideal, okay, with some properties. And the thing is that we think of I as the ideal of relations, and once you have lambda finite dimensional, the quiver is unique, but the generators, but the ideal may not be unique, okay? So this is because here I am now going to write, the sum for x in Q0, that is a vertex, the vertices of the quiver, of the path going in the algebra from x to itself, okay? And up to here, it's a formula that it looks like the formula for the dimension of the Hochschild cohomology in degree 1, but we add a term which is the sum for all the arrows in the quiver of the dimensions of, here I forgot the dimensions, of all the possibilities of going from the source of the arrow to the terminus of the arrows in the algebra lambda. And in fact, it is this term that differs from what happens for usual Hochschild cohomology, and the excess comes from here. So the excess comes from this term. Okay? Okay, so again, this has a quite long homological proof. So instead of giving the proof, I will give you some examples of results that we have obtained about this excess. So first of all, a proposition that says that if lambda is just a path algebra, that is the path algebra associated to a quiver, to a finite quiver Q, and Q is connected, the quiver is connected, and without oriented cycles, then in this case, the excess of lambda is 0. That is, the dimension coincides with the dimension of the Hochschild cohomology in degree 1. And since this last one is a subspace of the tau Hochschild cohomology in degree 1, they will be equal. Okay? And then the idea of proof is that the resolution, that in fact, that this algebra is hereditary. So the resolution stops in degree 1. Okay? And so what we are taking, which is a co-kernel, coincides in fact with the homology computed at this degree. Okay? But what happens for more complicated algebras, because this is a very particular case? Well, we will have a result that will generalize this, and for this we need a definition. We will consider lambda, let lambda be an algebra, such that it has what we call the HH2 cancellation properties that I will define in a minute very easily. This means the H2 cancellation properties that the Hochschild cohomology in degree 2 is 0, and the Hochschild cohomology in degree 2 of lambda, but with coefficients in all the powers of the Jacobson radical of the algebra are going to be 0. Okay, so later we will see some examples of these algebras to see that they exist and they are interesting algebras. But before this, just our result, the proposition, is that if lambda has this property, okay, this property that I will just write like this, then in this case, the excess of lambda is again 0. So this contains the hereditary case, okay? So an example of algebra satisfying this property, well, is the following. You take lambda equal to the path algebra of a finite quiver divided by what is called the radical square. The radical square means that any composition of two arrows or more is zero, okay? So we also suppose that Q is not a cycle. It may contain a cycle, but not be just a cycle, and that there are, I will write Q2 parallel to Q1 is empty. What I mean here is that there is no path of length 2 with the same source and same target as an arrow, okay? So this cannot happen, okay, in the quiver. Okay, so another family of examples that we were interested in was the following. So because we were using these algebras for other problems. So what about the following type of quivers? So because in the previous result, we have just left aside the cycles, okay? So now what about the cycles? So we have a cycle, and the cycle has, let's say, C vertices, okay? And well, we can define which are the relations. So the proposition that we proved is the following. So proposition 3. In this case, considering lambda equal to kq divided radical square, that was the case that was missing, there are 3 possibilities, okay? The first case is when C is bigger than 1, so it's not a local algebra, it's something with at least 2 vertices, okay? So if we have at least 2 vertices, then again, the excess is 0. And then what happens when the number of vertices is 1? Well, we have if C equals 1, and we have to consider 2 separate cases. The first one is when the characteristic is not 2, and the second one is when the characteristic is 2. Because in this case, in case C is equal to 1, the algebra we are considering is polynomial algebra in one variable divided by x squared, okay? Because we have one vertex, we have one loop, and the square is 0, okay? So what happens in this case? Well, the thing is that if the characteristic is different from 2, then the excess is going to be positive, is going to be 1. And this is because the k-linear derivations are spanned by a unique derivation sending x to x. But in the characteristic 2 case, the excess is going to be again 0. And this is because the derivations are spanned by the derivation sending x to x as before, but also we have another derivation sending x to 1. Okay, and in this case, it is a derivation because of the characteristic. Okay, so, we also know what happens with cycles. Okay, and another result that helped us to understand the excess is that the excess, in general, for finite dimensional algebra, can be computed as a difference between the dimension of the morphisms as kq by modulus of, remember, k is lambda is kq over I, of I divided by I squared with coefficients in lambda minus, and here we will see that we have already seen the cohomology in degree 0 appearing, the cohomology in the Hochschild cohomology in degree 1, and now we will have the dimension of H2. Okay? So it gives us the idea that this Hochschild cohomology, this tau Hochschild cohomology in degree 1, is also related to deformations. Okay, so consequence H1 tau is also related to deformations of lambda that are ruled by H2. Okay? Okay, fine. I don't know if there are questions up to here. Let me check the chat. Okay, no, that's it. So I will continue. Okay, so let me try to generalize things a little bit because, well, having this invariant only in degree 1 was not very satisfactory for us. But before this, we asked ourselves, and we will receive also a question from other people, that even if this HH1 tau is not a cohomological functor, we can also ask if it is a Morita invariant, and even more, so Morita invariant, even more if it is a derived invariant. And the answer is yes in this case, and oh, sorry, and no in the other case. Okay, so let me explain why. So first of all, for yes, for the Morita case, so H1 tau is a Morita invariant. And this is because of the following easy fact. It is that if we have algebras, lambda and lambda prime, that are Morita equivalent, then not only we know that the projective modules correspond to each other, I mean, the equivalence sends projective into projectives, also for lambda bimodules and lambda prime bimodules, and minimal resolutions are sent into minimal resolutions. So the respective minimal resolutions of lambda as lambda bimodule and of lambda prime as lambda prime bimodule, so the minimal resolutions, and also the presentations correspond to each other through the functors giving the equivalence. I hope my handwriting is not so ugly to you, but I cannot help it, sorry. And I said that it is not a derived invariant. So I'm going to show you a counterexample. Not going up to derived equivalence, but up to tilting equivalences, which is a bit less general. But since we show in a counterexample that it is not a tilting invariant, it will not be a derived invariant neither, okay? So tilting equivalences are given by something that is by tensoring, by bimodule, okay, lambda prime bimodule, that is a bit more general than the bimodules giving the Morita equivalence. For a Morita equivalence, you need a bimodule which is projective and is a generator, okay? For a tilting equivalence, you need a bimodule T, lambda prime bimodule, and the definition for T being tilting is that, first of all, the projective dimension of t over lambda prime is smaller or equal to 1, before it was 0, then the x1 as a lambda module, also as a lambda prime module of t with itself is 0. And then there is a technical condition saying that the number of indecomposable components of T is equal to the number of simple non-isomorphic lambda modules, okay? And the same for lambda prime. Okay, so it is a generalization of Morita equivalences. Okay, and which is the example now. So take Q, the following Q1, let's say the following quiver. So you have one arrow and then something like this. We call this arrow alpha, and this is beta and delta, and then we have gamma and epsilon. And the algebra lambda 1 is the quotient of this path algebra divided by the ideal generated by a thing that says that going like this is the same as going like this, okay? So in fact, it is the ideal generated by delta beta alpha minus epsilon gamma alpha, okay? And then take Q2. Q2 is a very, very easy quiver. It is a tree, which is just like this. I don't need the names. And lambda 2 is just the path algebra of Q2. Okay? So it is proved, for example, in a paper by Happel, that these two algebras are tilted equivalent. But the dimension of the HH1 tau of the first one, with the formula I have already given, can be computed as 1 minus 5 plus 5, that is 1, while the dimension for the second one is, using the same formula, equal to 1 minus 5 plus 4, so this is 0. So HH1 tau cannot be a derived invariant because it's not a tilted invariant. Okay, so as I said, we were interested in defining these spaces in higher degrees. And let me recall for this something again about Hochschild cohomology. So if you have the Hochschild cohomology in degree n of lambda with coefficients in a bimodule, by definition, as I mentioned, it is the xn over the enveloping algebra of lambda with coefficients in x. And this is also the same thing as computing the x in degree 1 of what? Of the n-1 CCG of lambda with coefficients in the same x, okay? Because we can stop the resolution wherever we want and take the CCG. Okay, so based on this, we give a definition, which is that the cohomology, the tau cohomology in degree n of lambda x with coefficients in x is going to be what? Before, let me add something using the Auslander-Reiten theorem. We have that this is the, this is the same as the dual of the ohm over lambda e of x with coefficients in tau of omega n-1 of x divided by the morphisms that factorize through injectives. Okay, so that's it. So now, again, we do the same thing, and we define the tau Hochschild cohomology as the dual of the ohm over lambda e of x with coefficients in tau of omega n-1 of lambda okay? That is, we do the same as before, we don't take the quotient. This is a kind of philosophy that people working in tau tilting theory has, okay? This idea comes from tau tilting theory. Okay, so we give this definition. Of course, it's well defined, etc., etc. And the first remark, well, is we have to verify that for all n greater or equal to 1, there is an inclusion of the usual Hochschild cohomology into this new tau tilted cohomology, okay? And more precisely, we know exactly how to compute the difference of these dimensions and when this is going to be 0. So we have a theorem. Of course, when this is going to be 0, the Hochschild cohomology also, but in some cases, this is not the case. Okay? So let me finish by stating the theorem. And the theorem says that the tau Hochschild cohomology of lambda with coefficients in x is 0 for big values of n, if and only if something that I will explain in a minute, an x of 0, an of x is 0 for n very big, where in this case, the an of x is exactly the morphisms of lambda bimodules from this thing that is E is KQ0, just the semi-simple algebra generated by the vertices. This is the n, which is the n, and what I have here is the nth step of the minimal projective resolution of lambda as lambda bimodule with coefficients in x. Okay? So why are we interested in this last theorem? And this I will explain maybe our interest in this theory. Well, this is related to the Hahn conjecture, to Happel's question. I will mention it in a minute, and Hahn's conjecture. Happel question is the following. Happel question is, you know, that if the global dimension of the algebra lambda is finite, then the Hochschild cohomology of lambda is 0 for n very big. Okay, so it stops. So Happel question was the converse of this. If the Hochschild cohomology stops, then if it is true that the global dimension is finite. And for several years, people worked on this, but in fact, there is a counterexample given by a local algebra, a finite dimensional algebra with just one vertex. Okay, so this is an example of an algebra such that the Hochschild cohomology stops. In fact, it is very small. It has, there is non-zero cohomology in degrees 0, 1, and 2, and then everything is 0. But the global dimension of the algebra is infinite. Okay, so the algebra is very easy. Since I have a couple of minutes, I will give you an example. So the example is the algebra where you have one vertex, one vertex, and you have two arrows, x and y. So this is the quiver, and the algebra is the quotient of the path algebra divided by the ideal span by x squared, y squared, q is a number which is a complex number which is a non-root of unity for any n, and the commutativity relation is like this. Okay, so this is the algebra, which is the counterexample, very easy one. Okay, so then Hans conjecture is the same thing, but for homology. So Hans conjecture is that if H, the Hochschild homology is 0 for n big, then the global dimension is finite. And this conjecture has been proved only partially for several families of algebras, but is still open. And we have been working on this, and we think that the difficult case is the local case, and we have to reduce to the local case. But our aim here, our aim with the tau cohomology is not to prove now Hans conjecture, but to define a cohomology that it is more adapted than Hochschild cohomology to describing the finiteness of the global dimension of the algebra. So we have proven in some cases the tau analog to Hubble's question that I mentioned before, and we are still working on the general case. So this is all I wanted to tell you. Thank you very much for your attention.
Thank you, Professora Andrea. I'm going to.
I will stop sharing maybe.
Okay, I'm here.
There are questions.
Thank you.
Okay. Oh,
Thank you.
sorry.
It has been a very interesting talk, very well
Thank you.
structured, which illustrates the excellent work you have developed, and there is still a long way to go. Let's see if we have any questions from the audience.
Okay, maybe I have more than the question, a curiosity. Professor Andrea Solotar, thank you very much for your very inspiring talk.
Thank you.
No, my question, sorry, I am not expert in your field, but is if in your notion of Hochschild cohomology, this Hochschild cohomology that you introduced, you have applications to, let's say, the non-commutative geometry, like in the case of the standard Hochschild cohomology, that is, for example, a proof of the Con's equivalence theorem and things like that. My question is if in your notion of Hochschild cohomology, similar things also happens or not? Just this general question, sorry.
Yes. We think it has application to non-commutative geometry, but to precisely to notions related to the global dimension. You know that the global dimension, of course, in the commutative case is a very geometric thing, but it is the generalization to the non-commutative case is just studying this homological invariant. So this is the main application we have in mind up to now of this new Tau-Hochschild cohomology. We have not thought about other applications because we are working with finite dimensional algebras. Okay, so because we only have the Auslander-Reiten translation for finite dimensional algebras and their formula. Okay.
Okay.
This
Thank
is
you
the
very much.
restriction. No, you're welcome.
Thank you.
So we want to thank you, Professor Andrea, for accepting our invitation and for being a mathematical woman who inspires others to enjoy this science en español. Muchas gracias, profesora, por inspirarnos a otros a seguir estos caminos. Y
Gracias,
gracias por aceptar la invitación de venir a compartirnos sus avances. Es muy valioso para nosotros. Bueno,
gracias, un placer.
Cerramos entonces la charla de la profesora Andrea y damos paso 2 minuticos a hacer el cambio con la profesora Isabel.
Okay.
Gracias a todos. Thank you very much. Just a few minutes. We are going to connect with next time.
Professor Gallagher.
Yes, hello. Hi.
Okay, thank you for being
Can you hear
here.
me? Yeah.
Yeah,
Thank
we
you.
hear you.
Perfect.
Welcome, Professor.
Okay.
Thank you for accepting our invitation. It is really an honor for us to have you here. I'm going to ask you for share your screen,
Yes,
please.
sure. Okay. Is that all right?
We're seeing your screen.
Okay, good.
Just let me introduce. See, it is a tradition maybe to give some words presenting our speaker. So it is my privilege to introduce Professor Isabel Gallagher. She's the current president of the French Mathematical Society, or Société Mathématique de France. She's an expert in partial differential equations and mathematical physics, and it is really an honor for us to have Professor Gallagher at our event today. She will be presenting the talk entitled On the Cauchy Problem for a class of parabolic quasi-linear systems, and I hope everybody enjoy this interesting presentation. Welcome, Professor Gallagher.
Thank you very much, and thanks for the presentation. So thanks for being here for this talk. So please, maybe what I could say right now is don't hesitate to stop me whenever you have any question. Just turn on your mic, I guess is the best. I won't be following the chat maybe so well, so please don't hesitate to interrupt me at any time if you like. So yeah, I'll be talking about a recent work I've done with Ayman Moussa, who's also in Paris. And so actually, what I want to talk about today is not really new results, but it's more revisiting an old proof of an old result, and in words that at least I understand better. And hopefully, yeah, so you might have something to gain about this new proof. So let me just start with a bit of a motivation. So originally, so I'm not at all a specialist of this kind of a problem. It's Ayman Moussa who brought this system to me, which is called the SKT system, after the names of Shigesada, Kawasaki, and Teramoto here. Okay, so they brought up the system in 1979, and it's about density populations. So you have unknowns, which are called U1 and U2, okay? And they follow this system, which is a two-component system, okay? Which looks parabolic, right? You have a Laplacian here. And you have coefficients, which are given, which are non-negative or positive. So D1 and D2 are diffusion coefficients. They're constant and they're positive. And then you have those coupling terms. Okay, so you have a matrix essentially. Okay, coupling U1 and U2. So it's highly nonlinear. It's quasi-linear, right? Because the higher order derivatives have nonlinearities. That's why we call that quasi-linear. And then on the right-hand side, you might have some source terms, which can be linear or nonlinear, whatever. Okay, and so the question is, can we solve this problem? Okay, so obviously, I mean, if you didn't have those terms here, then this would be a parabolic equation, which we can solve. Okay, sorry, maybe you should just remove this. Okay, this you can solve. But the question is now, if I have those nonlinear interactions, what's a good function space to solve this equation? Is it possible to solve the equation, etc.? It will be important in the following that each of the vector fields are non-negative. If not, the diffusion coefficients have the wrong sign, and then everything goes wrong. So this has to be also part of the proof of existence of a solution, the solution should be non-negative, even for physical reasons. Okay, so actually, I'll be looking more generally at what we're interested in is in the Cauchy problem, as said in the title, which means I want to know if there exist solutions, if they're unique, and I need them to be non-negative. Okay, and why is this not totally obvious? Because everything is very mixed because of the nonlinear term. And so, for instance, there's no maximum principle. You can't say the solution is always bounded by the initial data, which would be true for an elliptic or parabolic system. But there, because of those couplings, there's no structure a priori, so it's not so easy to solve. So I'll be interested here in strong solutions. I want them to be to exist and to be unique. So I'll just say one word about weak solutions, which I won't be talking about again, but still I think it's interesting to know that, as you might know, I mean, if you want to prove the existence of weak solutions, what you usually need is to have some a priori bound, something which you know exists globally, and then you have to work around with approximations and stuff to be able to prove existence of solutions satisfying those bounds. But so what's interesting here is to find this Lyapunov functional, which is written here. So it looks complicated, but it exists, and it's not so easy afterwards to use it to prove the existence of weak solutions, but it can be done. Okay, so psi is a primitive of log, and then you even have those regularizing terms. And using this, it's possible to prove the global existence of weak solutions. All right, but this is not my goal today at all. Today, we're interested in uniqueness and local, possibly in time, existence of solutions. So again, this is not new. Aman in '93 proved a very general result for a very general system I'll be showing you later on, saying that if you have some structural assumption on the matrix A, which I'll give you later on, which is not enough to get a maximum principle, but still gives you some spectral condition, which is known as the Petrovsky or normal ellipticity condition, then you can prove uniqueness and local existence of solutions. Okay, so what we're going to do today is revisit this with maybe a more modern, or at least a proof which I understand better. Okay, so let me look now at a more general framework. So the SKT system was just a motivation for a more general result, which is also the case for Aman. And the more general system we'll be looking at in this talk is the following. So now you have n components. Okay, so J here is going from 1 to n. Okay, we used to have n equal to 2, now n is anything. The space I mentioned is D, as before. And I forgot to say, but the space variable is periodic. Okay, which is maybe not so important. It could be in the whole space. For bounded domains for the moment, or domains with boundaries, I don't know at all what we can do. Okay, so let's fix the torus here. And so you're given initial data, and you want to know if you can solve this system. Okay, and so the assumption I'm going to make here is a spectral condition, which I mentioned a few minutes ago. It's known as the Petrovsky condition. And this condition is telling you that a matrix satisfies this condition, Petrovsky condition, if for some positive delta, you look at any element in the spectrum of your matrix, the real value of this element has to be bigger than or equal to delta. Okay, and delta is positive. So the real value has to be on the right side of the plane. And that's the condition we're going to ask. We want to know that we're going to assume, I'll give you a precise statement in a second, but that the matrix A of U, whatever U you feed to the matrix, you end up in one of those spaces for some positive delta. Okay, so this we can try to remember as the Petrovsky condition. And let me just give you some remarks on this condition before we move on. So first of all, let's look at the linear system. Okay, so now you have a matrix capital A, the entries are Aij's. And let's assume this capital A does not depend on U. So it's just a given matrix. Now you might know, or you might be able to prove this, that if you assume that this matrix A is symmetric, positive, definite, okay, so this means it has eigenvalues which are all bounded from below by alpha, okay, but it's symmetric, positive, definite, and you can write an energy estimate. Okay, you put the derivatives on the right-hand side, you integrate, and it's not so hard to prove you have this kind of an energy estimate. Okay, and you can even take derivatives because everything is constant. Right? And in that case, it's not so hard to solve the system. Unfortunately, the matrix A for SKT is not symmetric, positive, definite. So you can't just use this and solve the problem. Okay, other results would ask just for the symmetric part to satisfy this condition, and we'll see in a second that that does not hold for the SKT system as well. So that's why we need to use that Petrovsky condition, which we'll check will be held for the SKT system. Actually, some results also ask for the symmetric part of A to satisfy this condition, and it's again easier in that case. In our case, it's not the case. Okay, so in the linear case, it's been a long time since people have understood that kind of system under the Petrovsky condition. In our case, we're having a nonlinear situation where the matrix A is actually nonlinear in U. So let's go back for a second to the SKT situation. So now you've probably forgotten the system, but it doesn't matter. Here is the matrix again for you. Okay, so you can write it out just as I said before, like the abstract way, with this matrix A sub SKT, which is given by this 2x2 matrix. Okay, so first question is, let's look at the symmetric part and see what happens. Does that satisfy the Petrovsky condition? Meaning, do the eigenvalues stay on the right-hand side of the plane? The answer is no. Just compute the determinant, and you see that you can very well have something negative because this term could very well be much larger than that one. Okay, so there's no reason for this matrix to have a symmetric part with the good behavior. On the other hand, this matrix does satisfy the Petrovsky condition. Why is that? So you just compute the determinant and the trace of your matrix. I gave you the matrix, compute the determinant. If my solutions are non-negative, then the determinant is positive, right? Because you have D1, D2. Okay, and then you can see those two terms cancel out actually with the product here. So that's fine. The determinant is positive strictly. And the trace here is obviously strictly positive. Okay, if U1 and U2 are non-negative. Okay, so now if I assume my eigenvalues are written like A plus IB, okay, I have two eigenvalues, then just using the fact that the trace has to be positive, you see that B1 plus B2 has to be 0, okay? So let's call B1 some number B. And the determinant has to be 0. That means the product has to be non-negative, sorry, has to be positive. So the product B times A1 minus A2 must also be 0. So either the imaginary part is 0, and then A1 and A2 has to be non-negative, has to be positive, or A1 is equal to A2, and they have to be positive. Great, so this small computation is telling you that if I have a non-negative solution to my system, then the Petrovsky condition is satisfied, whatever U1 and U2 are. Okay, and it's satisfied uniformly, right? So I don't know what delta is, but I know that this matrix is in this set here. So it makes sense to try to understand an abstract quasi-linear parabolic system of that type with the Petrovsky condition assumed. So one last comment maybe on this condition. So it's written here on the slide again, in case you've forgotten. This condition at first sight seems very reasonable. Okay, if the eigenvalues are the right side of the plane, then everything should be fine. Actually, it's not the case. So, which came as a surprise to me like a few years ago, but actually it's quite reasonable when you think about it. You can very well look just at an ODE. Okay, this is an ODE driven by some matrix M of t. And you can assume that your M of t is continuous and satisfies a uniform Petrovsky condition. Okay, but still, the solution to this ODE will be exponentially increasing in time. Okay, which is maybe strange because you want to say the eigenvalues are bounded from below, so you're going to have an exponential minus something, it should be fine. It's not the case because M depends on time. You can cook up matrices for which the solutions actually will increase exponentially. So let me just make a drawing here to show you. You give yourself a first matrix M1, which is fixed, with the spectrum on the right-hand side of this plane. So you know the trajectories will be exponentially fast converging to 0. Okay, then you can look at another one, which is of the same type. So the eigenvalues will also be on the right-hand side of the plane. So the solutions will be exponentially decaying to 0, but you see in another angle. And now putting both together, and you can do that in a smooth way, you can cook up a matrix M, which is made up of M1 and M2, okay, such that the solutions will exponentially increase in time. Okay, so this is just to say that this Petrovsky condition is actually a little bit subtle, and it's not obvious it's enough to be able to solve a system of ODEs or PDEs under just this condition. Okay, so but still that's what we're going to try to do. So in the very general case that Amann looked at in 93, what he was looking at is the following system of equations, where you even have here different directions of derivatives, which will not be our case in the following. The matrix could depend on T and X as well as U. Okay, so it's a very general situation. He even was in a bounded domain case, not just a torus. And what he proved is that if your initial data is in a W1P space, meaning the data is an LP and it has one derivative or its gradient is an LP, okay, with a large P, that implies in particular that your initial data is bounded and it's even continuous, okay, because P is larger than D. Well, in that case, you can prove, well, he could prove the local existence and uniqueness of solutions, what you would hope. And even if your data is small enough, you have a global solution. And if your lifespan is finite, then that means a solution will exit W1P. It will blow up in W1P. All right. So in some sense, the drawback of this result, maybe because it's so general, is that the proof is very, to my mind, quite complicated. It relies on very abstract results in analytic semigroup theory, general interpolation. So it's sort of involved. And what we try to do with Ayman Moussa is take a slightly less general situation in which we can develop maybe more modern techniques, or at least techniques coming from harmonic analysis, nonlinear analysis, and prove a similar result. So that's the aim of the talk today. All right. So let's see, my system is a little bit more less general than the Ayman system, in the sense that we're going to take the same derivatives here and there, okay, some divergence form in some sense. And the matrix A is assumed not to depend on T and X. So, okay, this assumption, maybe we could relax, we can put back those variables maybe. But for the moment, we're just trying to do something as simple as possible, which involves the SKT system, right? The SKT system is exactly like that. That's why we focus on this situation. And so again, we want to provide an alternative approach to Amann's theory in a comparable functional setting. So the sort of some symbolic type space, which looks like continuous functions, and in the periodic case. Right, so I see there's a question in the chat. No, that's not time. Okay, yeah, please, no problem. Okay, so let's move on now to what we try to do. So the functional setting is a symbolic space. So remember, Amann chose W1P, right? Okay, with P larger than that dimension. We're going to choose HS, which is the same as W1, S2. Okay, so S derivatives in L2. And to have the same kind of scaling, we're going to ask for S to be larger than D over 2. That's exactly the same scaling as Amann, but we're using symbolic spaces model in L2 to be able to use Fourier techniques easier. Right, so our data is the initial data, U0, and the forcing term F, which we might drop after a while, but let's keep forcing term F. Notice here, I didn't add any terms like function of U, which I could have done, but just to simplify the talk today, I'm not putting any function of U on the right-hand side, but it would work exactly the same. Okay, so where should the data live? Well, U0 should live in HS. Okay, and the forcing term, if you think of an elliptic equation or a parabolic equation, you lose two derivatives by the Laplacian, but you gain one by integration in time, just like for the heat equation. So that means that the forcing term, a reasonable place to put the forcing term would be this space here, L2 in time with values in HS minus 1. That's really the correct scaling. Okay, in that case, the solution should be in this energy space, which is a space of continuous functions in time with values in HS, just like the initial data. And then thanks to the smoothing of the Laplacian, the elliptic term, you expect the solution to be L2 in time with values in HS plus 1. Okay, so I'm just giving you some notation here. That's the data space. I'll be recalling it as we go along, and the energy space in which I hope to find the solution. So let me just state the result, and then we'll try to discuss the proof. All right. So let's see. So my matrix A here, again, it's a matrix field. If you give it any vector in Rn, I want A of u to be in the Petrovsky space. Okay, for some delta. I don't know what delta is. Okay, so that's my matrix field. And then my initial data, I'm going to choose in this HS space. Okay, and the forcing term in L2, HS minus 1. And in that case, I know we can prove there's a unique solution U in the expected energy space to the system. You have a stability estimate. If you perturb the initial data, you perturb the forcing term, then the solution is under control and is slightly perturbed as well. If the initial data and the forcing terms are small, then the maximal lifetime is infinity. And you can always band from below the lifespan by a decreasing function of the initial data. Okay, so in some sense, it doesn't really depend on S, for instance, and when the data is small, then the lifetime gets bigger. All right, so that's a typical theorem you would expect for that kind of a system, and that's what we're going to try to prove today. So let me make some comments. First, so this is the general situation. What we're maybe more interested in for applications is the SKT model, or dynamics of populations. So in the end, what we'll have to check is that the SKT system falls into the realm of this theorem. So this is not so obvious because we know that the matrix A of SKT has values in Petrovsky if, and only if, in some sense, the components of U are non-negative. So we have to add to the theorem in the context of, sorry, I don't know what's happening behind. Sorry about that. There's something happening to Zoom. I have to check that in the context of the SKT system, then if my initial data is non-negative, then the solution is as well. Okay, so that we have to check. If that holds, then Petrovsky will work, and then I can prove the theorem I want. Okay, another comment is to prove this theorem, actually, we'll spend most of our time solving the linear system. Okay, so for a fixed A, which does not depend on U. Okay, so we'll first solve it in L2. That will be very gradual, first in L2. Actually, first for A, which depends on nothing, either T or X. Then for A depending on T, then A depending on T and X. And then once we have an L2 bound, we'll see how to get an HS bound by some kind of parallel linearization procedure, which I'll be detailing. Okay, and you notice here S is not an integer, right? It's any real number larger than d/2 strictly. So in dimension 2, for instance, it's any number larger than 1. So it's not an integer. So you can't just take derivatives of the equation to solve the problem in HS. Okay. And then once I have understood the linear system, what I'm going to do is use some kind of a fixed point argument using the linear a priori estimates to be able to solve the nonlinear equation. Right, so that's the plan. So the plan of the rest of the talk is first look at the linear equation for a constant matrix, time dependent, time and X dependent, but linear, okay, not depending on U. In L2, that will take a little bit of time, not too much. Then once I've understood that, how to move from L2 to HS for any S larger than d/2. And then once I have a linear theorem, how do I move to the nonlinear theorem by fixed point argument? Finally, once I have this theorem, how do I go back to SKT, check that the solution is non-negative, and solve the problem? Right, so now let's go back to basics. I have a constant coefficient matrix, which I'll call B. Okay, I'm given initial data, so let me call V the linear solutions. Okay, so I have initial data, which I call V0. I have a forcing term, which I call F. And I'm given this matrix B, and I know it lives in some P delta for a delta positive. I choose my initial data in my Sobolev space. Okay, then what can I prove? Well, then I can prove there's a unique solution, which is not so hard to prove because the equation is linear, and there's a priori estimate, which I'm going to check just now. Okay, so there's a unique solution in the energy space, and it satisfies a bound. So for the moment, I've kept the deltas explicitly in the bounds. That won't last. After very quickly, in this symbol here, I'll put any constant, okay, delta, anything depending on the data of my problem. okay, on the matrix and on delta. But just for the sake of being a little bit precise for the moment, I put deltas here to show you that, of course, if delta goes to 0, then you're in big trouble, obviously. All right, so let's see how you prove this result. And the point I want to make here is that my matrix B does not satisfy the usual assumptions I guess we usually make, that B, for instance, is symmetric positive definite. If it were, then I'd just do an energy estimate and I'd be done. I could even take derivatives, B is constant, so everything would be very easy. In our case, if you do an energy estimate, you're lost because you have no information on the sign of B. All I know is that the eigenvalues of B are in this good side of the complex plane, but I don't know anything else. All right? So it's not an energy method, but then you have other things to do. We're in the periodic case. I can look at the Fourier coefficients of V. Okay, so I write down V as a Fourier series. I call K the wave number. Okay, and so then you just write down your ODE on the Fourier coefficients. The Laplacian becomes K squared. Okay, and then I have the matrix B. I take the exponential of the matrix at time t applied to the Fourier coefficients of the initial data and the Fourier coefficients of the forcing term F. That's just a formula. Okay, and now all I want to do is compute the norm of this operator here. I'm sorry. And what I claim is that the operator norm of this semigroup is controlled in the following way. So if delta is 0, everything goes wrong. But for a fixed positive delta, here's what I get. So let's prove this. Okay, so B satisfies Petrowski with a constant delta. How can I prove this? Well, first of all, what I'm really going to prove is what's in blue here, and then just optimize or just choose t is equal to delta over 2, I guess, or 1/2, sorry, and you get what you want. You're just optimizing t and you get what you want. Okay, so what I'm really going to prove is this estimate here, which is in blue. And now up to translating B by minus delta identity, you can always assume now delta is 0. So I want to prove an estimate for a B in Petrowski with delta equal to 0, which is just this. Okay, so let's do this. Now, my matrix B, I can always try diagonalize it. So I write it up to some orthogonal operators as diagonal plus upper diagonal. Okay, that's nothing new here. And so that means that I can use, instead of using B, I use T. So the ODE I'm looking at now is solved with T up to the following equation for Z. Okay, so I've just changed variables with that unitary operator U, and this is the new ODE I'm looking at. D is diagonal, and I know everything about the diagonal values of D. They're all larger than delta. The real part is larger than delta. Okay, and now since R is strictly upper triangular, I have my matrix here, and the bottom line is just made of zeros. So I can first solve the last line, Zn. Okay, for Zn, there's no one here, because R is strictly upper triangle. And since my matrix D here has positive real part eigenvalues, then I just have this control here on Zn. Okay, and then once I know Zn, I can compute Zn minus 1, which I feed here by Zn, and then go on and on using iterated GMF formulations, and I get the result I wanted. Okay, so this is an explicit computation using Fourier. It's not an energy estimate. Once I have that, I get the bound I wanted, which was here. For delta equals 0, then translate again in delta, and you have the bound you expected. Right, so now if I go back to my original equation, remember, I was trying to solve the equation with B, my matrix which satisfies the Petrowski assumption. I wrote down the solution in Fourier, and then I just write exactly what we just checked on the exponential, which gives me this bound here. Okay, and then the L2 norm is just summing the squares of the CKs. The HS norm is doing the same thing, multiplying by K to the 2S and summing over S. And then everything is really very immediate. Okay, you can work it out if you like. Right, so now that I've written everything in Fourier again, use the Petrowski assumption to get a bound on the semigroup, and you're done. All right? So this proves the result in the constant coefficient case. Now let's see what happens when B depends on time. So now it's not constant coefficients, if we call it M for a change. Okay, so M depends on time only. It's constant in X, so I can move it out of the Laplacian. Okay, just like B before. Now, what assumption will I make on my matrix M? I'm going to assume a little bit of smoothness in time, C0 alpha for any positive alpha. Just a tiny bit of smoothness. All right. Now, what's the theorem? Well, under this assumption, if your initial data is in L2, that's all I'll need for the rest of the talk, for the linear case. My initial data is in L2, L2H minus 1. Okay, so this space here with S equal to 0. Then I have a unique solution, and it satisfies the energy band. So now I've hidden in this inequality here all constants depending on M. Okay, I'm not saying that P is with some delta here. That's just because I'm in compact space and time, so I can always find the delta. I don't need to say there's a delta. Okay, so it's both values in P, which is a union of P deltas for any delta, but since anyway, M of T is in a compact set, I can always find the delta if I like. That's just a hypermark. Okay, how do you solve this? Actually, the proof is very easy once you know the constant coefficient case. Again, I'm in a compact interval 0t. So I just cut up my 0t to small sets where M of t is close to a constant. That's possible because I'm in C0 alpha. Okay, it's possible, it's even quantitative. Okay, so I know what the cost is between M of t and M of t0 if t is close to t0. So what you just do is replace M of t by M of t0 on a small interval. Put on the right-hand side the error you've made, M of t minus M of t0, okay, which is just adds up to this forcing F. But since it's very small, and you have this uniform Petrovsky constant because t is on a compact set, then if you've chosen t close enough to t0, and you can make it explicit because you're in t0 alpha, then you can absorb the error you've made by the Petrovsky constant. Because M of t0 for any fixed t0 is in the p delta. Okay, so if you've understood the constant coefficient case, you've also understood the variable coefficient case in time. Right? So now, next step, what happens if my matrix depends on t and x? Okay, in that case, I'm not allowed to move M out of the Laplacian because it depends on x. So let's assume now that my matrix M is in some C0 alpha of space and time. Okay? It's still given, it's a linear problem, but it depends on space and time. Then what can I do? Well, this theorem is the same. Choose your initial data in the space with S equal to 0. That will be enough for the moment and hard enough. Okay, and then you can solve the equation in the energy space with S equal to 0, and you have an a priori bound again. How do you prove this? Well, I know how to prove it for M depending only on t. Now it depends on x, but that doesn't matter. Let's freeze the coefficients. Okay, so I'm in some C0 alpha, so you can even assume by some mollifying argument that's even Lipschitz if you like. And then you just say, well, M of x is not so far from f of a constant if x is close to a constant. So before we did a partition of unity in some sense of 0t. Let's do the same thing on the torus. Okay, so you're going to freeze the coefficients in x to go back to the previous case. And whatever error you make, you put on the right-hand side. And since you have this uniform Petrovsky constant, because you're in a compact set in space and time, then you can eat up your errors by the Petrovsky constant delta. Okay, so this is a little bit technical because, of course, when you start doing a partition of unity, this will not commute with the derivative, so it's very messy, but you can control everything. Okay, believe me. I don't want to do it. It's really technical. It's not so interesting. But maybe if you want to remember anything about what I'm saying here, is if you're in trouble with space and time coefficients, you can always freeze your coefficients for a while if you're smooth enough. You don't need to be very smooth, just C0 alpha. Okay, we'll see how this applies later on to the nonlinear situation. But in a linear case, that's what happens. So now, at the end of the day, what have we proved? Well, we've looked at this abstract linear equation. Okay, we've assumed your matrix field was in this space here. Okay, it's given. Then I have a unique solution which lives as long as my forcing term lives. Okay, and my matrix lives. Okay, so it's global if everyone's global. And it satisfies an a priori bound. So that's what I wanted to do in L2. The problem is that I'm told I should solve the equation in HS, the nonlinear equation. So if I want to solve the nonlinear equation in HS, I better be able to solve the linear equation in HS. Now, maybe you could reasonably ask me, but why do you want to solve the equation in HS? I mean, you have this nonlinear equation from the start. I had this equation dtu minus dk of a of u dku, let's say is equal to 0, sum over k. You could wonder, why did I not solve this in L2 and then I'm done? If I believe it, I've done it in the linear case. Okay, so there's no chance for this to work. Even if A was linear, okay, if U is only in L2, how can you make sense of the product of U times dku? All right, this is going to be very complicated. Morally, even for scaling arguments, you should look at A of U just as a coefficient, like a viscosity coefficient. So it should be bounded, right? If it's just an L2, how will you make sense of this equation? I have no idea, in a strong sense, okay? So it's very reasonable to ask for A of U to be at least bounded, okay? And so U to be bounded, A is a function of U. And in terms of symbolic spaces, the good space, which looks like L infinity or continuous, is exactly HS with S greater than D over 2. Right, so there's actually no choice. If you really want to solve this problem, you're going to have to understand the linear equation in HS for S larger than D over 2. Right, so let's do that. So here's the statement. The statement is, give yourself your matrix field in this space, further space, as before. Okay, and assume it's also in this space L2 HS plus 1. In the end, we're going to replace M by A of U, which is like a power of U, whatever, a function of U. So its smoothness, if U is an HS, is essentially HS as well. Why? Because S is larger than D over 2, and that means that HS is an algebra. HS plus 1 as well. Okay, and so essentially, just pretend for a second, which this will not be the case exactly, but if A of U is just U, then since U will be solved in this space, L2 HS plus 1, then A of U will also be in this space. Okay, so it makes sense to look for the linear case situation with M in this space. Okay, you can wonder, why would M be in that space? Well, that's because when dtu is equal to something, then you get this kind of polar estimate. I won't go back to that, but it also makes sense even in a nonlinear setting. Okay. Anyway, so let's go back to my linear problem now again. Forget the nonlinear case for the moment. And take your initial data in the HS setting. Then the linear theorem is saying everything's fine, you have a unique solution, and it is in this energy space within the primary band. So what I'm going to do here is try to explain how to prove that. So I'm not totally certain about what the audience here knows or doesn't know in analysis, in harmonic analysis. So I hope you won't be too upset if I take a little bit of time to explain to you what this little Paley story is all about. So sorry about people who know all this, but I guess everyone doesn't know what that is. And I think it's a very nice tool, very important tool. So yeah, I'll spend a few minutes just understanding and just explaining how that goes. The idea is to say I have this equation with a space variable in particular coefficients M. I want to have an estimate in HS. Even if S was equal to 1 or 2, an integer, taking derivatives of the equation is not so easy because you're going to pay with derivatives of M and things are going to be horrible. So the idea is to say I have an L2 estimate, which I was able to prove because of Fourier, essentially. I want to prove an HS estimate just building upon the L2 estimate. And to do that, I'm going to apply what's known as the Littlewood-Paley truncation operator, which is this operator here, delta J. Okay, I'm going to define it in a second. But pretend you know what delta J is, just apply it to the equation. It's here, it's there, and it's there. Okay, now what is delta J? So this I'm going to write down for you. Delta J is the following. So again, sorry about people who know, and I hope the other ones will learn something here, which might be a little bit interesting. So what you're going to do in the Littlewood-Paley theory is to say, I can write a partition of unity saying that for any psi, which is, or k, sorry, which is my wave number. Okay, let's make it continuous because things are simpler in that case for me anyway. Okay, I can always write down a partition of unity, which is the following. So for the moment, just believe me. Let me just write this. That's equal to 1 for any function, for any wave number xi. Where chi here is supported C infinity with compact support in the ball centered at 0 and radius 1. And this phi here is compactly supported in some ring centered at 0 and let's say of radius, I don't know. This is totally crazy. I have no idea, but let's say, for instance, I don't know, 7/4. This is stupid. Anything going smaller than 1, larger than 1. Okay. And then what you notice, if you choose correctly those numbers here, is that essentially those functions are orthogonal one to the other, almost, up to maybe you have to put, okay, let me write something which is essentially true, I hope. If you take this times that, this is 0 if, let's say, j minus j prime is larger than 2, for instance. Okay, this is an orthogonal, quasi-orthogonal decomposition. The support of those guys is for psi of the size 2 to the j. Okay. The support of that guy is psi smaller than 1. And delta j is just taking the inverse Fourier transform of the multiplication by this truncation. Okay, so delta j, you feed it a function, it takes it and cuts it in a small piece of size to the j. Okay, and when you do, I'll call Sj will be chi of 2 to the minus j something. This Sj is taking all the frequencies up to 2 to the j. So now any function f can be written formally as, let's say, S0 plus the sum for j positive of delta j. Okay, that's exactly the same thing as what I've written up here. Taking the inverse Fourier. So I hope you believe me on this. So j and z would actually be j positive, non-negative. This is a very general theory. And the only thing maybe you can try to remember here is that if I want to look at a function f now in hs squared, what I can do is say, well, it's f in L2, let's say, plus the sum for all positive j's of delta jf in L2 times, I should have s derivatives. Well, s derivatives is like a power of psi. A derivative in Fourier is psi. Okay, s derivatives is psi to the s. The psi is the same as 2 to the j, so I have 2 to the 2js because I have a square. Okay, there's a bit of math hidden behind that, but please believe me. And this is a great way of replacing a symbolic space for any integer, for any index s, positive, negative, real valued, by just L2 norms. And you replace derivatives by multiplying by 2 to the j. Right. Why is that nice? Well, for instance, this is not very hard to prove. If I'm given, that's what I actually did in the previous slide. If I'm given a function u or f, okay, what I claim, if I take a derivative of that, this is the same as 2 to the j delta j of f. That's because psi is 2 to the j. But what you can also prove is that if you look at any LP norm, let's say L infinity norm, this is smaller than 2 to the j. That's the number of derivatives. If I have alpha derivatives, I have the length of alpha. That's just because psi is 2 to the j. And then I can move L infinity to L2 by paying by the size of my ring or my ball, d over 2. That's Cauchy-Schwarz. Why? Because the L infinity norm is bounded by the Fourier transform in L1. Okay, d alpha is 2 to the j alpha. And then what's the L1 norm of the Fourier transform? I have on one hand phi to the minus j times f hat in L1, and then Cauchy-Schwarz. Okay, Cauchy-Schwarz gives you the L2 norm, which is here, and the size of the support of phi is here. Okay, so you don't have to remember what I'm saying here, but maybe in a few minutes I'll tell you, remember we saw Bernstein before and we'll be using exactly this. The last thing that's very useful in this theory is the pair product, which is due to Jean-Michel Bonny in 1981. So that's an old theory, right? But very powerful. The pair product is the following. So I'll just give you, again, a crash course. If you give yourself two functions, f and g, you can say, well, f I can say is the sum of delta j f. Okay, let's just say notation. Okay, I'll just call f0 delta minus 1, just to have just delta j's. And g is the same for some other index. Okay, this is okay. And then what you're going to do, what Bonny tells you to do, is say, well, in this product, I have three possibilities, or two, let's say two possibilities. Either the frequencies of f are very small, quite small compared to those of g, which means I'm going to take all the frequencies up to some j plus 2, for instance, and then delta j g, sum over j. Okay, that means here xi is it's smaller than 2 to the j plus 2, essentially, and there xi is of the order of 2 to the j. Plus the remainder, and the remainder is saying, essentially, g has much smaller frequencies. So I have a delta jf and a sj prime minus 1g. Please believe me on the minus 1s and the plus 2s. That's just, if you've seen the story before, you'll believe me. If you haven't, I beg you to believe me. Okay, so why have I done that? What's the idea of Bonny? Well, the idea of Bonny is that low frequency functions are very, very smooth because xi is bounded. Okay, so this function here is much smoother than that one in some sense. Okay, all the information on frequencies is given by this guy. The same way here, this function gives you all the information on frequencies, and that one is just very low frequency, you don't care about it. Okay, so again, I can't tell you everything about that, but this is a very powerful way of doing products of functions in symbolic spaces with non-integer indices. And we'll be using at some point of this formula in a few minutes. Okay, so that was a crash course on little Paley theory. Let's see why it's useful. So I told you we have a linear problem. Okay, this m is given, but depends on t and x. I know an L2 bound, and I want to replace L2 by HS. And I've been told, well, that's easy, actually. Just use delta j, because delta j's, if you know them in L2, if you know that in L2 that decrease like 2 to the minus js, that means I'm in HS, okay? If I know that delta j, that delta jv in L2 looks like 2 to the minus js times a function, let's say a sequence in L2, that implies it's equivalent actually to v is in HS. Okay, so I just need to understand delta jv in L2, but I know the L2 estimate. Okay, I know the L2 estimate only if I have delta jv here and there, inside, okay? The unknown is delta jv. So what I really should write in this equation like this. And then when I do that, I have to take the commutator between delta j and dkm, and I call that rj. Right, this horrible formula, please don't look at it, just trust me, it exists. And if you remember what I told you before about the pair product, here's the pair product, j plus 2, j minus 1, and a commutator. So you put together a pair product and commutators, it's just algebra. Okay? I'm just writing things around, moving things around, and this is a formula you get. That's what we call para-linearizing the equation. Okay, I did as if m was constant coefficients. Okay, so I moved delta j inside. That was not allowed because m is not constant. So I have error terms, and algebra tells you here are the error terms. Okay, so please, yeah, just should believe me on this. Now I'm pretty happy because I can use the L2 estimate. The L2 estimate tells me that the L2 norm of this guy, squared, plus the L2 in time H1 norm, but H1 is like multiplying by 2 to the j squared, because I have a squared, okay, is controlled by the L2 norm of the initial data and the L2 H minus 1 norm of the right-hand side. L2 is here with squared, and H minus 1 is putting 2 to the minus j here and there. Okay, so here I've just copied the linear theorem in L2. Right? No work. This guy here is perfect because if I sum over j, I have L2 H minus 1. This guy is not perfect at all because I have the definition of Rj here, which is crazy, and I have to estimate this in L2 and see how much it costs with 2 to the minus 2j. Okay, so if you use pair product techniques, whatever I told you about the way I cut up my Rj, a little bit of work will produce the estimate you want. So here I'm sort of cheating. I'm going to uncheat by showing the estimate in one case for one of the Rjs. And you have to believe me, it works the same for all the Rjs. 1, 2, and 3. Okay, but that's exactly what you want. So the message maybe you can try to remember if you want to remember anything is, if you know the L2 bound for a variable coefficient equation, that's fine. Just apply a little Paley, work a little bit, and you get the HS bound, if it's linear. Okay, so I've planned to show you, for instance, in this case, okay, quickly how this works. Okay, so how can I estimate this guy? Let's say in L2 HS minus 1, which is exactly what I'm supposed to do for a forcing term. L2 in time. Forget the time variable, just look at the x variable. Okay, you want an HS minus 1, so I multiply by 2 to the j s minus 1 in L2. So this is here. I have one derivative with a delta j. Bernstein tells me that gives me an extra 2 to the j. Okay, so this goes away. This is with this. And then I just do Hurlder with L infinity, L2. Okay. Then what do I do? Well, first of all, minus 1 plus 1 go away, so I have to do the js. And then I just noticed that, as I said before, an Sj is a sum of deltas, if you remember, for j like double prime smaller than some j prime plus something, which I write like this. Okay, so here I've just used the definition of the Sj's which are supported in a ball by sums of delta j's which are in rings. Okay, nothing special here. Then I remember that my matrix M is in L2 with values in HS plus 1. Forget the time variable, it's in HS plus 1. This is here. That means I've actually gained minus S plus 1. That's what I told you before, the equivalence between the smallest space and the way those guys decay with this function, with this series here in L2. Second thing I've done, I have one derivative I've replaced by a power of j. Okay. And then the L infinity norm, remember, I replaced by L2 up to multiplying by j d over 2. I'm just using Bernstein here. Now, last step, this, I know that V is an HS. Okay, I'm going to use some Gronwall at some point. So I can replace this delta j double prime by minus j double prime. And then you just have to count. I have a js minus j prime s. J is small, so that you can sum. I have a minus j prime plus a j double prime. That's fine. J double prime is small. And then I have a j double prime d over 2 minus s. That's fine because s is larger than d over 2. Okay, so in the end, you can sum everything. All three terms are dealt with in the same way, and everything works. So this was probably a bit too fast, but try just maybe to remember that little Paley theory is a way of replacing derivatives by multiplying by powers of 2 to the j, which is much nicer. And then play around with power product and Bernstein, and you can do anything you like. Now, just to finish the last maybe 5 minutes, let's go back to the nonlinear problem. And that's actually what we really wanted to solve. But what I claim is that if you can solve the linear problem with an estimate, a priori estimate, then a fixed point will give you the results for the nonlinear problem, so to speak. So here's my system, and now A of U is with values in Petrovsky by assumption. So let's see, I want to solve my equation in this space ES of t. Okay, so I want to look at the vector fields which initially are equal to some U0, and which belong to this space here, and I call I call this GST of U0. Okay. And now I'm going to use a linear operation, linear theorem. So what I'm going to do is solve for any given U, the equation sending U to this U star. U star is driven by A of U. Okay, so I call theta the map that sends some given U to the solution of this equation. And I know it exists, we've done that before. Okay, we've solved the linear equation. U is given, I get U star. And now the nonlinear solution is just a fixed point. If U star is equal to U, I'm done. Okay, sorry, U star is equal to U, I'm done. So I need a fixed point for theta. Right? Okay, so now let's see. I want a fixed point. So I need the theta to be continuous. That's fine. We've done it before. That's the energy bound that gave me the continuity of theta. I need it to be Lipschitz with a constant smaller than 1. Okay, and this is not so easy because what you can prove is this estimate. If I have two U1s and U2s, I want a Lipschitz bound. So I look at U1 minus U2. I look at theta of U1 minus theta of U2, which is this. Right, and you work a little bit just using the linear estimate because I just write down the equation on the difference, which is linear again, and you get this bound. Okay, I won't prove that. Okay, I sort of plan to prove it, but I'll skip that. Sorry about that. Skip it. And so just believe me, that's the bound you can prove. And the problem is that you would like your theta to be Lipschitz with a constant smaller than 1 to have a fixed point, but you don't know that because this here will be smaller than 1 if t is small, but it depends on U2 star, which is a solution. Okay, so that's no good. So the idea here, and I'll stop, I think, pretty soon, is an idea actually you can use for lots of nonlinear problems, and maybe that's another message you can bring back if you want. So that's something I use a lot of times for the Navier-Stokes equation. So let me just tell you a second here. If you want to solve the Navier-Stokes equations, okay, and it's not hard to prove you have global solutions. If you don't know Navier-Stokes, forget that, but you have global solutions for small data because essentially U squared is smaller than U, so Laplacian wins. If your data is large, how can you do the same thing? Well, one way of doing it for Navier-Stokes, which we copy here, is to say, well, I'm going to look for U like the free flow plus something. The free flow is large if U0 is large. But this new guy here solves a perturbed equation with 0 data, so small data. Okay? And then what's going to happen is that it's going to be perturbed by this free flow. But this free flow for small times is small. Okay? In the same way here, I'm going to say, instead of solving U directly, I'm going to say U is like the free flow, some kind of free flow, which is actually the solution associated to 0 data, which is here. This I can solve globally. It's constant coefficients. I can solve it globally. And then I'm going to look for my solution near this guy. Okay, so smallness now will be to be near this guy, and this guy, UF, is small for small times. Okay, so I'm going to prove the map sending U to U star is a contraction not near U0, but near the free flow. Okay, for some small time. And the time will only depend on the initial data because initial data is entirely hidden in this UF. Okay, so, okay, I have to stop. So this is the idea of the nonlinear problem. And before I used to have a bad estimate with a gradient U2 star, if you remember. Now the gradient is now the gradient of UF. And UF only depends on U0. And this guy is small for T small. So I do have a contraction for a time T small enough depending only on the initial data. Okay, so now just to finish, back to SKT. I won't tell you how that works, but for SKT, what you have to do is check your solution is non-negative. And to do that, okay, so uniqueness argument, which I won't go through, but it's not so difficult. So I prefer to stop here. You can apply this theorem, the abstract theorem, to SKT if you check that non-negative initial data produces non-negative solutions. Okay, and that can be done. And I'll stop here. Thanks for your attention.
Thank you, Professor Gallagher, for your presentation, interesting presentation. We're now open for questions. If you want to make a question, you can raise your hand using the Zoom link, or you can write it down on the chat. No one? No, maybe if we have one question from the people who are in the auditorium, from people who are here in the university. Let me see. We can. Okay, maybe. I think Duban is trying to make a question, but okay. Let me see if I can mute. We have some technical problems. Just wait a minute.
No problem.
I'm asking to mute your micro from the auditorium. No, if no, you can write on the chat.
Okay, hello, can you hear me?
Yes.
Yes. Professor Gallagher, thank you very much for your presentation. Sorry that we have some echo. Okay, we are here in Javeriana University. The several students did hear your presentation. I think they were very happy with this opportunity. Thank you very much for accepting our invitation. Maybe I have just a comment. If you can mention something about another application of approach of in the sense of Jean-Michel Bonny to PDs, if you can mention something about this.
Yeah, so there are several applications. One is simply just in harmonic analysis. If you want to do the product of two functions, which are in any type of space, so whether it's symbolic or more general spaces, maybe you've heard of Bezoff spaces, whatever. Understanding, for instance, if I'm in HS, a function is in HS, another one in HT, in what space is F times G? Okay, and so if S and T are integers, you can just use Leibniz and answer the question. But if they're not, then the pair product, to my knowledge, is probably the most efficient way of proving that the product is in HS plus T minus T over 2. Or even in Bezoff spaces, you can. I mean, pair product is a way. So I haven't explained the thing here, but if you look at very small frequencies of one function and very large of another, okay, so one, let's say, in a small ball, the other one in a ring, which is far away, then the product, when you take Fourier, you're doing a convolution of the supports. And so if the ball is very far from the ring, the ball doesn't touch very much when you do the convolution, the ring is hardly changed. So the smoothness is really the same as the function up there in the ring. And that's what you use in the pair product algorithm. That's how it works. And so to my knowledge, it's been very much used in variable coefficients equations or nonlinear equations like wave equations or yeah, as soon as you have, like, for a cubic wave equation, if you want very low regularity solutions, the best thing to do is to para-linearize. People have done this a lot also for wave maps, but also for gravity waves equations on I don't know. As long as you have non-linearity and you're in the whole space or in the periodic box, if not, things get more complicated. Then it's really a way of quasi or para-linearizing the equation, exactly like I did today. So something very classical. Okay, so here it was just an example of using this method, but you can really see it in a lot of nonlinear PDEs in the whole space or in the periodic box. If you're in a bounded domain, things get more tricky.
Okay. Can you hear me?
Yeah.
Yes. Okay. Maybe another question. Last question is, Okay, in this case, you are investigating regularity for solid spaces and you use this technique of paraproducts. Do you think it can be also adapted to other spaces, like best of spaces or trivially sorting spaces that also are related with Lillieuth Valley theory?
Yeah, absolutely. So we could do the same proof would work in best of spaces at the limit points, right? Like here I have HS as larger strictly than D over 2. If you take the limit best of spaces, you get B D over P, or D over 2, 2, 1, B D over P, P1. That will work exactly in the same way. So because it gets more and more technical, we haven't written it that way, but it's absolutely certain. Triple Lizorkin, I'm not used to at all, so I can't guarantee it works. I would expect it to, but I really don't know.
Okay, thank you very much for your very nice story. And thank you for welcome always to ICMAM Latin America.
Thank you very much. Thank you. Thank you very much.
Thank you, Professor. Okay, next talk is in person by Professor Michael Rushansky. Welcome, Professor. I think we are going to make some video test and sound test. Please confirm everybody's in the auditorium.
Yes.
Okay, thank you. But
Just
But,
a couple minutes, please.
I think it's multiple times, right? Let me see. Okay, no, it's okay. It's okay. And try to use the micro, please, Diana or Duan.
Hola. No.
Dile que estamos tratando
¿Es
de
okay?
conectar la presentación de él, que nos dé un par de minutos.
It is okay. Okay.
Me está leyendo la voz que me entregas. No. Te voy a compartir la presentación a Brian y que la... Sí, sí, pero me está leyendo una USB que tenemos. No, es un...
Yeah, the system from the memory stick as well.
Okay, okay, so now I have...
Can I send it in?
No, it's- that we are sharing all the things about Zoom from this computer, and we cannot see the desktop. So she's trying to. Sí. Dile a Brian que mande la presentación de Michael, que por favor la presente. ¿Listo?
La presentación se está viendo ya. Es decir, no necesitan abrir ahí el Zoom, solo proyectar la imagen y yo los estoy escuchando. Y todo el mundo los está escuchando. Ahí se ve.
Okay. Okay, so it's my great pleasure to introduce our next speaker, Professor Michael Ruchansky from Ghent University and Queen Mary University of London. Has a tradition in ICMAM Latin America. Let me just say some words about Professor Michael Ruchansky. First of all, he has a very close collaboration with Colombian mathematicians, especially with Universidad del Valle. He collaborated strongly with Professor Julio Delgado, and throughout this collaboration, there is a growing group in analysis also in Univalle. Michael Ruchansky also support Colombian mathematicians and mathematicians from developing countries. There is, if you see, the website of the Ghent Analysis and PD Center, where actually Michael is the director of that center. You will see many mathematicians from developing countries, in different parts of their careers, like graduate students, postdocs, and so on. So it's really a big pleasure for us to have Michael with us, who will talk about recent progress on very weak solutions for PDEs with singularity. So welcome to Cali, and thank you very much for accepting our invitation.
Thank you very much for this introduction. Yes, thank you. Okay. Yeah, so pointer? How is the pointer? Yeah. I can go with this. Yes. So, yes, I'm glad to be here, and in fact, I was last week in Bogota at the conference in Uniandes, which was commemorating 60th birthday of the math program there, and then it was a good chance to also visit here. So thanks to Giovanni and to Julio for arranging this visit. Because I don't wear a watch here, I put a phone to see the time. So I guess I don't know how much time I have because the program is 50 minutes. Okay. Yes. Yes. So it is my pleasure to give this talk, and it is called Risk Progress on Very Weak Solutions for PDEs with Similarities. And I will first, well, it's recent progress. It's research that has been going for a while, and first I will give a progress somehow, and then I will explain what it is. So, in a simple situation. So, yeah. Okay, I have to see. Yes. Okay, thank you. So, it is. Yes. So, in fact, in the previous talk, you heard a situation when multiplication of two functions which are irregular is a problem, and in fact, indeed, this Boni theory of paraproducts allows one to deal with products of functions which are of less regularity than the in Sobolev spaces, but of less regularity than when Sobolev spaces form an algebra. That theory allows you to multiply some functions in Sobolev spaces, Bessev spaces, and so on. But the situation here is when we have much more singular functions. So then Boni theory of paraproducts doesn't work, but still in partial differential equations we have equations, some of which I will show, where this situation appears naturally. So the motivation here comes from I can show like this instead of pointer. So the situation is motivation comes from equations when we have very singular coefficients. So here, for example, wave equation, but the coefficient in front of delta, in front of Laplacian, is delta function. And then we cannot multiply distributions. There are some ways around it by trying to create nonlinear theory of distributions, which is, in my opinion, not so well suited for partial differential equations. So here I will present another way, namely a notion of very weak solutions, which allows to treat partial differential equations with such strong singularities. This notion of very weak solutions was introduced in this paper with Claudia Garetto, now almost 10 years ago, where we considered wave equations with of the type which I show here, and then the notion of very weak solutions, how to understand well-posedness of this equation, how to understand the equation itself when we cannot multiply. So let's say U is singular itself, then we cannot multiply U or delta U by delta function. So, but how to understand this equation? Because such equations often have physical meaning. So how to understand such equations and how to understand well-posedness of these equations. Usually we mean by well-posedness, we mean existence of solutions, uniqueness of solutions, and some continuous dependence on data. If we talk about Hadamard well-posedness. And so I will give some in a simplified setting. I will explain what it is, but first, as I said, I will talk about recent progress, but first, not so recent. So then we started to develop this notion and apply it to different equations. For example, these two cases will be here in this talk. One is very weak solutions to wave equation with Landau Hamiltonian, which is a physical situation of electromagnetism. Although my talk will be mathematical, will be not much physics in there. And then acoustic problems. Acoustic problems actually here. Juan Carlos Munoz is from Colombia, from Cali, from Univada. I gave a talk. It was in the beginning, so these papers we published 2018. The first paper appeared 2015. So somewhere around that time, I gave a talk here in Univada, and then he asked an interesting question, and then this led to this work for acoustic problems. And then later we extended some previous analysis in these papers. For example, Niyaz Tokmagambetov, my former PhD student, for general operators with discrete spectrum, and then also some analysis on groups, like if we have subelliptic situation, for example, Heisenberg groups, or stratified or graded groups. So they were this works, and so I will try to give you examples in simple case, but a little bit more about recent progress, because recent progress means we consider more and more equations over the years. It's not the most actively developing research, but for myself, but it goes on gradually over the years. So here, for example, so here in all these papers, we consider time-dependent coefficients. When we have coefficient depending on time, because then we can use Fourier analysis. But more recently, we started also applying this to x-dependent coefficients. For example, here I wrote some fundamental equations of mathematical physics, like heat equation, Schrödinger equation, wave equation. Also, we can put some powers here, but you can think of S equals 1. And Q is a singular potential. So here we have a problem. For example, if Q is singular, like delta potential, and initial data, U of 0, is also delta, then we have to multiply delta by delta. And we know we cannot do it in the framework of the theory of distributions. But equations, even with stronger types of singularities, like an acoustic problem, appear, and I will show you some motivating examples. And then some other types we considered, for example, here, so-called telegraph equation, that we have more terms, Schrödinger equation in this kind of divergence form, when we have singularity under derivative. So here we differentiate, not only G is singular U, but then we differentiate this, so it becomes even more singular. And recently some other people, so some papers also in the direction of considering equations with x-dependent coefficients. So also with Claudia Garetto, who was a postdoc at that time, we considered equations on groups, so on compact Lie groups, equation like this, when L is sublaplacian, A is singular coefficient, so we can, here additional complication is that sublaplacian is weakly hyperbolic, so we have to deal with multiple characteristics, which is another problem for such equations. Even if A is nice, then in Euclidean coordinates, this equation has multiple characteristics. So then again, it's another difficulties. Then later on, this so this is sublaplacian of compact Lie groups, and here with Tokmagambetov we extended this to general operators with discrete spectrum. So sublaplacian on a compact Lie group has discrete spectrum, but then we considered more general any operator L of the Hilbert space with discrete spectrum. And also L can be, so this is sub-Laplacian, but L can be higher order operator, also hyperelliptic, so-called Rockwood operator. I will not talk much about groups here, but also we proved very equal closeness for these equations. And so also other types, so this is wave equation, but then in these papers, we considered, for example, Schrödinger equation with singular potential. So this is more recent work. And so here, the most recent maybe, these are when we have Sturm-Liouville operator, Q is again singular, but then we have questions, different questions, like if Q is, for example, delta function, how do you consider this to the power S for fractional S? So it's not just multiplication of distributions, but taking fractional powers. So if Q is delta, then should be positive. And then, so for example, deltas, and how do you interpret this term? And how do you interpret solutions to this equation? And also discrete setting, one can consider discrete setting. Here, for example, it's equation of the lattice and kind of semi-classical formulation when we consider H a parameter. And then another question arises, like what happens when H goes to 0? So we have very weak solutions, but then we take H goes to 0, the mesh size of the lattice. Then we should somehow recover situation on Rn. And indeed we do. There are some interesting phenomena there. And in fact, there is here, I can mention some, this is equations from the lattice. We use some elements of pseudo differential analysis, which was this paper back in 2020 with two masters, at that time, I don't know, master students or students from Ghana. From Ghana, I was visiting African Institute of Mathematical Sciences and was there for a week, and then had to supervise, supervise some projects. So this is with these two students there, and Linda Bochway and Kibiti. So then we wrote this paper, developing pseudo differential analysis on the ZN, and then later on, Linda Bochway, she came to Ghent for a visit, and then we advanced this a little bit by semi-classical analysis on HZN. In fact, I was giving lectures. There are some schools in Via de Leyva here in Colombia, and I was giving the lectures about this analysis on the lattice, and there people were asking, I remember people were asking, but you have this analysis on the lattice, but if mesh size goes to 0, what happens? Do you recover Euclidean results? So this was a good motivation then to consider this. So recently, this is a paper published this year. We considered what happens with that theory if H goes to 0. So I'm happy to be in Colombia because you saw that my talk in Cali in Nevada led to further investigations with Juan Carlos Munoz. Here, my visit to Unilever, to Via de Leyva, led to this kind of analysis when H goes to 0. And furthermore, there is, of course, Joan Cardona as a PhD student in Ghent University, and Santiago Gomez Cobas, also another PhD student in Ghent University. So this is collaboration with Colombia seems to be productive. So this I'm happy about. So just I will move on to presenting you the notion of very weak solutions, but just to give you some other recent updates. So there is now a remote lab of our Ghent analysis in PD center in Armenia, and they're also doing very weak solutions. So here we have several people, and there we consider, for example, some kind of cosmological models, equations related to cosmological models, where we have this Laplacian anisotropic because there are these coefficients depending on IJ, which change in time and which may be singular. So here, and also recently some nonlinear PDEs, which is very nice because, as we saw from the previous talk by Isabel Gallagher, that nonlinear terms, and here is also nonlinear terms, when u is singular, how do we multiply? Traditionally, we have to be in the Sobolev space, high enough regularity so that we can multiply, but here we can go to more singular coefficients. And also this talk is related to this subject related to computer, some can be related to computer science, because if you want to do numerics for hyperbolic PDEs, there are oscillations, and it's very consuming, difficult from computer point of view to do it in higher dimensions. But one can do parallel computing. And in fact, Rashid Altubai, so former PhD student, he wrote PhD thesis about different methods of applying parallel computing to this. And now he's visiting Ghent also for a year. So this kind of analysis. And okay, so this is about recent progress, but now let me explain to you what are these very vague solutions in simple situations, and also some a little bit of philosophical discussion. We have this, first I give some kind of philosophical discussion about solutions, how to understand solutions to partial differential equations in general, and then I will give you a precise definition that we have. It's very simple for like definition of solutions, usually simple for PDEs. So, but examples like this, as I said, we can consider delta functions, we can consider Heaviside jump functions, and singularities appear in this way to this Cauchy problem. And as I said, there are several questions, like how to interpret this equation itself. If u is a distribution, when we have a product of two distributions, we know we cannot do it in the framework of the theory of distributions. There is a famous Schwarz impossibility result that says that we cannot multiply distributions in general. And there are some conditions when we can multiply depending on wavefront sets, but delta function has a worst possible delta wavefront set. So in this case, delta function cannot be multiplied by anything except for maybe continuous functions. And what is, so how to interpret the equation and what is the right notion of well-posedness for these equations? Okay, so let me put this notion a little bit in perspective. We have, let's consider simplest equation, also strictly hyperbolic if you want, for simplicity. So A is strictly positive because if A becomes 0, so A is not negative, but if it becomes 0, then there are some other phenomena appearing. So for simplicity, let's consider A to be strictly positive. So we are in a strictly hyperbolic case. And if A is C1, starting with, then there is classical theory of solutions. We take U, we plug it into the equation, and if equation is satisfied and U is regular, equation is satisfied at every point, then U is a solution. So this is a classical way, and if depending on the data, if the data is distribution, again we plug in this distribution, and we check if the equation is satisfied distributionally, and then it is a solution. However, now we start lowering the regularity of A. So A is Hölder, let's say Hölder class, C alpha. Alpha between 0 and 1, then there may be no distributional solution. This is another famous result. I will talk about this a little bit later. In fact, well, I can mention this is a famous paper by Colombini, De Giorgi, and Spagnola that shows that there may be no distributional solutions with smooth data. Even if the data, Cauchy data is smooth, A is Hölder, then there may be no distributional solution. However, so what happens is that one weakens the notion of solution, enlarging the class of I wouldn't say functions, class of enlarging the class. So we have a space of distributions. We cannot find solution in the space of distributions. We have to enlarge, and then once we enlarge, then we find solution. This is so-called ultra-distributional solution. If A is locally integrable, then we enlarge the class again, so-called hyperfunctions. Then we can find solutions in the space of hyperfunctions. If A is measurable, then there may be no space, but notion of solution can be discussed. Kato's theory of semigroups. And our case is distributional, so we have to enlarge somehow even further to find solutions. And I mentioned there is a Colombo theory which exists. There are several nonlinear theories of distributions when we can make sense of multiplication of distributions. Maybe most famous of these nonlinear theories is Colombo theory. But a problem with Colombo theory is that it's too, what we get, suppose we get Colombo solution and we get a classical solution, they're not related. So what we want to have is that, I will have on the next slide, so-called consistency. If we have, let's say, distributional solution, classical solutions, they should be related. Colombo theory problem is that what we get is often not related. And in general, from a good notion of solution, what do we want? Solution has to be weak enough to guarantee that solutions exist. This notion has to be weak enough, but it should be strong enough to give uniqueness. And as I say, consistency. If there are classical solution, for example, we want to recover this classical solution from distributional solution. So weak enough to say that I can introduce a notion of solution. I can say that any function is a solution, right? By definition. And then, of course, I have existence. Any function is a solution indeed, but I will not have uniqueness. I will not have consistency. So this is notion which is not. So this notion is not good enough. So let me give you a couple of more examples that, like this is Landau Hamiltonian, which I mentioned. So looks a bit complicated, but no worry. This is with physical constants. This is so-called Landau Hamiltonian electromagnetic field. Hamiltonian, which describes the particle in electromagnetic field, looks like this. So we put this physical constants equal to 1, and so Landau Hamiltonian can be like this, H. So we can think of this like this. B is just, let's say, B is a magnetic strength of magnetic field, and Q is electric potential. And then we can consider wave equation like this. So electromagnetic potential Q, electric potential Q depending on time plus some A additional. And you see here, if we have like deltas or Heaviside functions, like there is some, when we talk about electricity, so there is a light in this room, and if we switch off light, it means there is a jump, right? So there is a jump, and so we get some singularities here. There could be also some surges, like an electric, maybe some, you know, sometimes light just switches off because of some precautions, and because electric surge and then switches off. So this kind of delta kind of perturbations like this. And so again, this is this is an equation. If you see how, for example, wave equation, but we can consider other equation with this Hamiltonian, then we know there is no blow up, there are no explosions, everything behaves well, stable. But so from the physical point of view, this is okay, this equation. But mathematically, then we have problem because we have to multiply this distribution. So, and acoustic, as I mentioned, Juan Carlos Munoz from UNIVADE, So acoustic system, in fact, after I gave a talk about these very weak solutions, he asked, he drew my attention to this acoustic system, which is description of acoustic waves. And after some manipulations, I will not talk much about physics, but we can rewrite it in this way, because I started talking about wave equation, so we can write it like this. And B is a density, B is a coefficient, which is product of density and wave speed of the medium. So B is some, let's say, essentially constant function. So acoustic, it means I'm talking here. And so as I talk, you hear my voice, right? And my voice propagates by waves. And in this room, there is some density of air and also wave speed of the voice in this air. So we have some coefficient B in this room, which is a constant. But then there are walls around us, and my voice hits the wall, right? And wall has a different coefficient B. So B, it's a density of the wall plus wave speed of the wall. So B has a jump. And again, this is physically a very natural situation. We speak in this room, we don't think about equations, but propagation of my voice in this room is described by this equation. So B, let's say B is a jump function. B is a jump function. And if B is a jump function, then like Heaviside function, then what we have here is derivative is delta. And then we have to divide by the Heaviside function. So it's not just multiplication of distribution, here is division. Because what is delta function divided by Heaviside function? We cannot make sense of this in the theory of distributions mathematically. However, I am talking here, nothing is happening. There is very well-defined physical process, but how to interpret this mathematically? Mathematically, we have to divide the delta function by Heaviside function. And later on, we have to multiply it by another distribution, maybe another distribution. So these are the problems. And but before I go on, so I will tell you how to interpret these equations at the end of my talk. But first to say a few more to motivate definition, because if you will see the definition, maybe you will be a bit surprised. But so first to prepare you, I give you some historical perspective. So again, so what happened is that historically people were weakening notion of solution, as I already said. We cannot find solution in the classical sense. So classical solutions, these point-wise solutions, everything regular. We plug in function, function is regular. We plug in, differentiate, equation satisfied or not at every point, then it's solution or not. So this is classical. But as you know, there are many equations where there is no classical solution. Then the notion of Sobolev. So here is a picture of Sobolev and the picture of Laurent Schwartz came to Sobolev weak solution. When we interpret solution in a weak form, like integral, we multiply by a function, we integrate test function, we integrate, and then this is a solution. But Sobolev theory requires, because we write it as an integral form, requires that everything is locally integrable. Okay, but if things are locally integrable, we can talk about Sobolev weak solutions. So this we can no longer do if we have delta functions appearing, because they're not locally integrable. So Sobolev weak solution cannot be applied when notion of Sobolev weak solutions cannot be applied when we have delta function. So we have to weaken the notion of solution or enlarge the space of solution. So then we look for distributions, and the Schwarz distributional solutions. Distributions are functionals, and we interpret this as we test the equation on test functions, and it's see if it's satisfied or not for all test functions. Then this is a notion of distributional solutions. Again, distributional solutions may not be enough. Then we talk about ultra-distributional solution, which means that we so distributions is a dual space to smooth functions, but we can start taking functions more regular, like Jouvre. Then we consider dual ultra-distributions. Then it becomes larger and larger. So then this is a situation, and also this is what is important. We call consistency or backwards compatibility, which is crucial. So if you find two things, let's say you find Schwarz distributional solution and you find classical solution, then they are related. So then the distribution that you find is distribution arising from the function, and this function is a classical solution, and then corresponding distribution will be distributional solution. So they are related, and this is what we call consistency. It means that the notions that we introduce should be consistent. If it happens that we find more regular solutions, then they should be related. And another philosophical remark before I show you the definition. There are roughly two types, very different types of notions of solution. If you don't think of this, then kind of it's natural, but if you think of this, you see two different types. So there can be solutions which depend on the notion of solution is universal for all equations, they have the same notion, or notion of solution can depend on the equation. And we have this in these notions of solution, which I mentioned. We have these two different things. So classical solutions is, as I said, we plug in regular function into the equation. Equation is right or not. So this notion doesn't depend on the equation. I can do this for any equation. However, Sobolev weak solution situation is completely different, because we consider weak solution by usually we consider by test. For example, if we have delta u, we multiply by test function phi, we integrate, we put one of the derivatives from u to phi, and then this term, for example, is of this type, and the same for other terms. So it depends. The notion of solution depends on the equation. Then we have these distributional solutions and Colombo solutions, which exist again. They are of the type of classical solutions. There is the theory of distributions by Schwarz, or there is Colombo theory, which exists independently of equations. But then we try to see that if we apply it's the same notion which works for all equations. We do not care what is the equation, what is the equation itself. It's the same notion working for all equations. So here the situation is with our very weak solutions. That's why we call it very weak solutions, because situation is similar to Sobolev weak solutions. It will be adapted to the equation, or so it is in spirit. It is similar to weak solutions. The notion depends on the equation, and in fact, more precisely, it will depend on properties of solutions to regular equations with regular coefficients. So if you understand the same equation when coefficients are regular, we understand these solutions, then we build up a notion of very weak solution, which is takes these properties, regularity properties into account. Okay, and after a lot of talking now, philosophically and historically, I give you definition. Again, this is some preparation for the definition. I will give it in the simplest case, as I already considered, this wave equation, and I assume that A is strictly positive to avoid multiplicity phenomena when A is non-negative. So let's say A is strictly positive. And so this is the fact which I mentioned by Colombini, De Giorgi, and Spagnola, that we can find, so this is very remarkable, and it says that we can find smooth data, so U0, U1, smooth compactly supported, very nice functions. A is strictly positive, continuous function, so also nice. But there is no distributional solution for any time. This was of course very unexpected result, but it comes from the fact that A is continuous. So if A is continuous, or even Hölder, we can find even Hölder A's, equations with Hölder A's. If A is not Lipschitz, so to say, if A is less regular than Lipschitz, then this phenomenon can occur that we have no distributional solutions. However, if A is smooth, strictly positive, then there is a classical theory of PDEs. It gives a smooth solution. So there is a sudden jump in this kind of behavior. Okay, so as we said, if we cannot find solutions in the space of distributions, we can enlarge the space, and indeed, people did it. If A is smooth, if A is continuous, or Hölder, as I said, one can enlarge the space, considering ultra distributions, then one finds solution there. But we are interested in a less regular case than continuous. For example, think of delta. Then we have to enlarge even further. So how do we enlarge the space? Is done using another classical idea of regularization. So Friedrichs type regularization. So we consider convolution of A with a smooth modifier. Here I put omega of epsilon, but you can think omega of epsilon equal to epsilon for simplicity, classical Friedrichs modifier. And we consider convolution. So think of A as a distribution, delta function. We consider convolution with modifier. We get a smooth function A epsilon. If A is positive, then A epsilon is positive. So anyway, we can do like this. And then the definition comes is that a family of smooth functions is called moderate if this family with derivatives can blow up as epsilon goes to 0, but blows up in a moderate way, doesn't blow up exponentially, but blows up polynomially. So this we call moderate family. So moderate family is a family of smooth functions which bounded, which blows up for each epsilon. So for each epsilon this is finite, but blows up as epsilon to the power minus n. And then what we can observe is that this notion allows us to enlarge the space of distributions, because if you start with the distribution A, then from the structure theory of distributions, it's not difficult to show that the family of its regularizations, A epsilon, is a moderate family. Okay, so every distribution gives rise to moderate family of smooth functions, not in a non-unique way, because if you take another modifier, another function psi here, then we will get a different family of smooth functions. But so each distribution gives us a family of smooth functions, but not the other way around. If I start with the family of smooth functions, it doesn't have to come from a distribution through regularization. So it's really enlarging the space of distributions. It is a subspace of smooth, moderate families of functions. And with the very big solutions, we are going to look for equations for solutions. Now, not in this space of distributions. As I said, distributional solution doesn't have to exist, but we are going to look for solutions in the space of smooth or maybe not smooth, and this will depend on the equation, but in this case, smooth moderate families of functions. And here is a definition of very weak solution finally. So what to do? Let's say what do we do? We have an equation with some singular A here. Let me show the equation again. Where is it? We look at this equation where A is singular, like delta function, and we regularize it via convolutions. And instead of A, we get A epsilon. So if A was positive, A epsilon is also positive, but A epsilon is smooth because it's a convolution of distribution with a smooth function. Then we look at this equation now with A replaced by A epsilon with the same Cauchy data. And we know this now we're in the classical theory of PDEs, there is a smooth solution, U epsilon. Okay, so for each A epsilon, we can find smooth function U epsilon satisfying this equation. Then, so if it happens that this family U epsilon is moderate, then we call the family U epsilon very weak solution. So this is what happens. The precise definition is the following, that the family U epsilon of smooth functions is called the very weak solution of this Cauchy problem if there exists moderate regularization A epsilon of A such that U epsilon that solves this equation is moderate itself. Okay, so it's a very simple definition that if we regularize A epsilon, we get a family of U epsilon. If it happens to be moderate, then it's a very weak solution. Okay, and summary of results for this equation. So first, so this is a theorem which I formulate like to save space on the slides in this way. So as a summary, so existence for any A, there exists very weak solution, so we have existence. It's unique in an appropriate sense, which I will define on the next slide. This very weak solution is unique. And consistency, which is very important, is the following, that if A happens to be smooth, and let's say data is smooth, then we have from the classical theory smooth solution. We have smooth classical solution. We also have very weak solution by this theory existence. So how are they related? The question is, and indeed, so can we recover the classical solution from the very weak solution? Indeed we can. And namely, so there is a classical solution U, there is our very weak solution U epsilon, and then here was existence. In the definition I had existence of regularization. So here the strongest statement how we recover so is that for any, doesn't matter how we regularize A, for any regularizing family A epsilon, the very weak solution A epsilon converges to U in the space of smooth functions. So we do recover classical solution U from the family U epsilon, which is our very weak solution. Also, if another setting where we know existence of solutions, distributional solutions, A smooth, U0, U1 distributions, there exists a distributional solution U, this we know, because it's A is smooth. And then again, we have this very weak solution, which is given by this existence result. And then again, we recover distributional solution from very weak solution as a limit. So U is the limit of U epsilon, as epsilon goes to 0. Here we have to take a limit in the space of distributions because U is a distribution itself. Okay, so we have existence, uniqueness, and consistency. Okay, so uniqueness now. So this recapture a little bit. This is Cauchy problem. This is regularized Cauchy problem, depending on epsilon. So we have existence, as I said, for any distributional U, A positive, because it's a wave equation. Cauchy problem has a very weak solution, and uniqueness is the following. So uniqueness depends, in general, in PDEs, notion of uniqueness depends on the equation. It depends on the solution space in classical functions. Uniqueness means two solutions equal to each other everywhere. In Sobolev notion of weak solutions, it means that uniqueness means two functions equal to each other almost everywhere. Distributional means that they equal as distributions. So here, so uniqueness depends on the space where we look for solutions. Here is interpreted very naturally in terms of stability, namely because we are regularizing. So if we regularize in two ways, A, such as the difference between these two regularizations is negligible, then the difference between corresponding solutions, very weak solutions, is also negligible. So in mathematical terms, it means that if we find two families of regularizations of A such that the difference is negligible, meaning less than epsilon to the power n for any n, then the corresponding U epsilons in the suitable norm will be also negligible. So this is uniqueness. And the choice of norm depends on the definition of very weak solutions. And yeah, so this is, I will give a couple of more examples. How much time do I have actually?
5 minutes.
5 minutes, okay. Okay. So will be enough to show you other situations. So Landau Hamiltonian, as I said, notion of solutions depend on the properties of the solution to regularize problem. So here, the way we regularize, we adapt, and the norm, I said, the norm depends on the solution of the regularized problem. So what norm to take? Let me give you an example, Landau Hamiltonian. So Landau Hamiltonian has interesting property. It's operates, it has discrete spectrum and H, operator H here. It has discrete spectrum. And but the multiplicities of eigen values are infinite. So it's kind of interesting situation because discrete spectrum, eigenvalues, but each eigenvalue has multiple infinite multiplicity. But not a problem. We know this spectrum actually explicitly, spectrum of H. So we can define Sobolev spaces used based on the powers of this Landau Hamiltonian. So once we know the spectrum, we can define powers, fractional powers, and then this gives us Sobolev space. And first we look at the regular case. A regular case when, let's say, A and Q are C1, or one can sharpen a little bit like bounded function with bounded derivative. But so A is positive, Q is positive. Then this is a regular result, which is not difficult to prove, is that if data are in the Sobolev spaces for the S, according to this definition, then this equation LH, Landau Hamiltonian, has a unique solution in the space. So this is a regular case because A and Q are regular. So now we adapt the notion of very weak solutions to this case where we have this the regular case which we understand. So here comes the definition that a net U epsilon is a very weak solution. Here we can say for the S, if you want. So if there exists moderate, again, if there exists moderate regularization, say epsilon Q epsilon of A and Q, such that when we look at this equation, we know the solution exists. By this first theorem, we know that if A and Q are regular, then there exists a solution in Sobolev spaces. So this we know this A epsilon exists by the previous theorem. And if A epsilon happens to be moderate, then we say that the family A epsilon is a very weak solution. And moderateness here is understood. As I said, we have to choose norms correctly to have the uniqueness and consistency properties. So it's chosen in this way that it's moderate. Again, it means some norm is bounded by epsilon to negative power, but the norm we should take here is the Sobolev norm for the Landau Hamiltonian. So if we have these results, then we have again the theorem for this notion is that we have existence of very weak solutions, we have uniqueness in the same sense, stability sense, and we have consistency. So if A and Q are regular, then and data like this, and for any regularizing family, so we have this solution. In the regular, we have solution in the regular case. We also, by existence, we have a solution as a family, and consistency means that U epsilon, we can recover regular solution from this our very weak family. Indeed, we have U epsilon goes to U as epsilon goes to 0. Okay, the last example maybe I show this is because it's a more physical situation. In fact, it's kind of equa effect. If you know equa, you know, in Spanish, equa, yes. So equa, we all know when we talk, then here we cannot hear in this room. Very weak echo effect. But if you are in the mountains and you shout something and then something comes back. So this is acoustic equation. Where does the echo come from? Equation is, you see, equation is strictly hyperbolic. And in strictly hyperbolic theory, there are no such things as echo effect. The wave propagates and continues propagating, never comes back. However, here we have echo, which, and in fact, here, echo is coming from the singularity. So this is acoustic problem which I showed to you. The singularity in lower the term can create this echo effect. So this is very new phenomenon, I would say, because hyperbolic theory depends only principal parts, strictly hyperbolic. Nothing should come back, but the sound comes back, and this is because of this term. But again, as I said, so this is very interesting equation, but how to interpret this? It's delta function just divided by Heaviside function. Doesn't make sense mathematically, but you will see, according to very weak solutions, it's not a problem. The definition is the following. Again, a net U epsilon is a very weak solution of order S if there exists moderate circularization of B such that U epsilon solving this equation is moderate. Again, the same definition, but has to be adapted to the solutions to the regular equation. So if B epsilon is positive, smooth, then this equation has solution, no problem. This is because this coefficient is well behaved, depends on epsilon, and if this dependence on epsilon is again moderate in the Sobolev norm, in this case, because we have to adapt to properties of regular equation with regular coefficients. I don't give you this theorem precisely, but it is a well-posed in Sobolev spaces. So then we have to take Sobolev space. So in the first case, we were taking an infinity. In the Landau-Hamiltonian case, we were taking Sobolev space adapted to spectral properties of Landau-Hamiltonian. Here we take the usual Sobolev space, and then this is the situation, and here is the result. The result, again, the same existence. So for any Sobolev data, Cauchy problem has a very weak solution. It is unique, again, in the stability sense. Consistency, if we have classical solution, if B is regular, then we have classical solution. We have also very weak solution. And the very weak solution family, U epsilon, will converge to the classical solution U as epsilon goes to 0. And we can analyze this further. We can analyze these families. I don't have much time, but we can prove, for example, this kind of estimate from the regularized problem. And then B, as I said, B is a nice function. B, maybe in the real world, B is a piecewise continuous, piecewise constant function. It's a B prime over B, which causes problems. But B is fine. So, for example, here we can have this uniform estimate for the family U epsilon. We can look at other things. We can look at the singularities. So here is, okay, I don't have much time. Some numerics, thanks to Juan Carlos Munoz. I skip, but I just say that, for example, this, as I said, we can have uniform estimates, but one can also study like propagation of singularities, why it comes back. So this was done later in this paper by, also recent, when people analyzed the exact profile, wavefront set, this kind of things of the reflected solution and so on. But I think that, so maybe I skip the details. So there are also other interesting equations like tsunami equation we analyzed. But let me say that, to summarize, because I'm running out of time, to say that, so if we have partial differential equation with singular coefficient, then we have an ocean, a very weak solution, for which we can prove existence, uniqueness, and consistency. So it's kind of Adamar-Well posedness, according to the notion of very weak solution. And this is very interesting research topic, because there are many equations. We have to understand in each case how to adapt this notion to the equation. Some equations in the very beginning I showed to you, but there are more equations. So this is a topic which is very much open for investigation already. Over the years, several people defended their PhD thesis in this topic. And so this is interesting subject, especially nonlinear equations interesting, but still for linear equations, there are still a lot of things unknown. And I think that this is the end of my talk. Thank you.
Okay, thank you very much for this very inspiring talk. We're open for questions. Thank you, Professor Villaves.
Yeah, this notion of consistency that you described through, first of all, philosophically, and then through 2 or 3 examples that have many things. So, first of all, do you have examples where you have very weak solutions, but somehow no notion of consistency? That's my first question. Like, is there a family of examples where you don't have consistency, but you do have some very weak solutions, and what do you do with such examples? My second question would be, for each one of these examples where you have proved consistency, how much does it depend on the specific form of the problem, or is there some kind of general framework that would lead you, to work for a family of problems at least? So it's.
Yes, thank you. Very good question. In fact, I don't know if I have like here. Yeah. So it is, as I said, it depends. It's case by case, because we adapt the notion to the equation. Of course, we want to have consistency, because it shows that this notion is justified. Backwards compatibility. So in the examples that we have, we always have consistency, because this is what we want to have. However, it may happen that, but consistency is in the case if there is a more regular solution, then it's consistent with a more regular solution. But there are cases when there is no more regular solution, then we just have the family of u epsilon, and we want to know what happens as epsilon goes to 0. And then there are very different situations. For example, here, so some examples I show. So this is like for tsunami equation. This is the graph of the solution depending on epsilon. So you see they are all close to each other. They converge. In fact, in some cases, we show that as epsilon goes to 0, they converge to something. And where they converge, it is not a solution in the classical sense, because there is no such notion as classical solution. But it converges to some function, which we can call, well, we don't have the term for this, but we can call some limiting very weak solution. That will be just a function, single function, which will be a solution as the limit of very weak solutions. It may happen in some cases when, as we let epsilon goes to 0, we may have not one function, but we may have several functions. If you consider limits, so this is limits in the regular functions. If we consider in the other situations, we can consider, we may have different limits. We can consider some, so we can have different situations which are also physically justified, because there is an example of conical refraction, propagation of light in crystal. So if you have crystal, which consists of different parts, and you let a ray of light go, if the crystal at some point consists of 2 different parts with different density, then single ray splits into a cone. So this is a physically observed fact. There are a lot of papers of this from microlocal point of view. So it means that as a limit, so here as a limit as epsilon goes to 0, we may get not a single function, but a whole family of functions satisfying some properties. So this is, but this is very much open in the sense that for some cases, so for this tsunami equation, for some particular, so delta, it was delta type of, here was delta type of singularity. I didn't talk much about this equation, but for some singularity, we show that there is a limit as epsilon goes to 0 to some function. But in other cases, we either don't know, haven't investigated, or as I said again, it's case by case. So we don't have, we have to, for each particular equation, we have to look these questions. They're all interesting, but it means a lot of work, especially for young people. Maybe many questions. So I use this chance to attract maybe young researchers to this area, because there are many questions and many interesting problems.
Professor Julio?
In the same direction, I think, when you take the limit, when epsilon goes to 0, say something about the space where this solution is.
Yeah, so this is again whether the limit exists, first question, and in which, so first whether the limit exists in which way, in which norm, right? Because limit may exist in the distributional sense, but may not exist in the classical sense. So this all interesting question. In this case, you see from the picture, limit as epsilon goes to 0 exists, for example, in L infinity. So that we can say about this, but it's not a solution of the classical, because classically, so this is a picture corresponding to this equation when h is delta function. So h is delta function, and we take u0, u1 also deltas, and then we can see the very weak solution. So we cannot say that it's a solution to this equation in any sense, because then we multiply two deltas. But it happens, interestingly, that u epsilon has a limit as epsilon goes to 0, which is a nice function in L infinity. But it doesn't mean that there is a solution in L infinity, because yeah, then we would have to multiply these distributions. But so this is kind of limiting very weak solution. We haven't set up the term yet, but if I say like this, then this is will be some notion of solution.
You have a question?
Yes, my question is about if this method can be implemented in the discrete world, because when we make the calculations, usually the singularities are avoided, but when we work with very singular problems, the singularities can be avoided. So my question is, this has a discrete vision.
Yes, good question. In fact, very natural question, which we try to address. And as I mentioned, one paper, this is very natural question here. But paper where we have this kind of, this is discrete situation. K is in the lattice. This is discrete Laplacian. And so we have, so as you you said very correctly, that if A is regular, then we avoid singularities. So the situation on the lattice is very different from Rn. On Rn, there is no distributional solution to this equation, but on a lattice, there is always solution in L2. So we, by discretizing, we avoid singularity. Very good observation. We have always solution in L2. But in Rn, we don't have distributional solution. So how to explain? Well, it can be explained by taking the limit as h goes to 0. We have a limit of L2 functions, but they depend on h. As h goes to 0, then in fact, it is not in L2. Then it goes to this either Gevrey solution or ultra-distributional solution. But as a limit, so we do recover result on Rn through this more regular discrete result, but then it's interesting because we have two parameters, small parameters. Epsilon goes to 0, h goes to 0. So there are some interesting questions can be about limits in which order to take and so on. But it is in fact just for this case. For other cases, I don't know. There is only one paper where we did this, and it is this paper also published just this year. And yes, with these people, and yes, where this question is considered.
Okay, so let's thank Professor Michael Rushansky again. Just one small observation, right? Professor Michael Rushansky is editor of one series of books, right? Perspectives, Game Analysis, and 3D Center. You can visit the website of his center and you can see there this new series. And he very kindly also provides us the framework to support several of the conferences of ICMAM Latin America. So also somehow we are related with this series, which is very nice for us, good opportunity for us, and thanks to so just a small observation, and thanks to Michael for his time for this very nice stuff.
Okay, thank you.
Okay.
Okay. Can you hear me?
Yes.
Okay, Professor Jenny, please.
So, hi, Barbara.
Hi, Jenny.
Nice to see you. Could you share your screen, please?
Okay. I will try to share just this one. Let's see whether this works.
Yes, this works.
But I still have to go to full screen somehow. No, that's not good. This way, okay.
So are you ready?
Yes.
Okay, so it's my pleasure to introduce Barbara Kaltenreiter. Barbara is a full professor at the University of Klagenfurt. It's a member of the Committee of the European Mathematical Society and was also editor-in-chief of the European Journal of the European Mathematical Society. She published more than 140 scientific papers, and she is also co-author of 4 books. The last one on inverse problems for fractional partial differential equations. So for me, it's a pleasure to have Barbara in this workshop. Thank you, Barbara, please.
Thanks a lot for your kind introduction, and thanks a lot for having me here at this conference. I hope you can hear me well. Is it okay?
Yes.
Thank you. Okay, so my talk will be on nonlinear acoustics, mathematics of nonlinear acoustics, and some forward and inverse problems in this context. So on the forward problems, it's mainly cooperation with Vanja Nikolic from Radboud University. On the inverse problems, it's mainly cooperation with Bill Randell from Texas A&M. And you will also see some pictures and results that have been obtained by my 2 students, Teresa Rauscher and Benjamin Reiner. So actually most of the talk, a good part of the talk will be about modeling. And it's on one hand on this nonlinear aspect in acoustics and also on the damping, which is quite often modeled by physicists and engineers by fractional differential operators. And of course, this also gives yields to interesting mathematics. On the analysis, I will say a little bit about parameter asymptotics, and I will also look at frequency domain formulations of these nonlinear time domain acoustic equations. And concerning inverse problems, I will mainly focus on one of them, namely the topic of nonlinearity parameter imaging.
and if time permits, just mention shortly a few further ones. So, what's it all about in nonlinear acoustic wave propagation? So here are 3 snapshots over time where you are supposed to see a little bit on how a wave propagates non-linearly. So first of all, so the wave is excited here on the left-hand boundary, and the cut is done in such a way that you see the profile of this wave. You immediately see that it's damped because the amplitude gets smaller, but you also see, hopefully, that from left to right, so on the left-hand side, the excitation continues being just sinusoidal at a single frequency, but here you see that the profile of the wave changes. It steepens up, so it's flatter here and it's more steep over there. And so to say, in the limit, it becomes very steep and it becomes a so-called sawtooth profile. And this can really very nicely explained by the mathematical formulation, because actually, well, the physical background is that really the sound speed in this media can be viewed as depending on the amplitude, and not only on the amplitude, also on the signed amplitude. So if you have a positive amplitude, then it's faster here, and down here below 0, it's slower. And that's why it gets skewed like this, and in the limit it becomes a sawtooth profile. So this is another picture of this, where you maybe can see it a bit better. This is the outcome of a simulation. And here you see a comparison between linear propagation, damped linear propagation, where you would, this dashed line, you would have this dashed line, and the wave just keeps being sinusoidal. And the nonlinear behavior, where the wave, as you see, the profile leans to one side, to left side. So one can also view this from the time perspective. So here it's from the space perspective, here it's from the time perspective, and then therefore it leans to the other side as compared to the linear setting. But one can also view this from the frequency perspective. So basically doing a Fourier transform of the signal that is a time signal up here, one ends up with something like this. And what you see here is all these spikes. The very first one, that's the excitation frequency. That would also be the frequency of this sinusoidal wave that you see. But you also see contributions at multiples of this fundamental frequency. And that's actually a typical behavior that has been known for a long time by physicists and engineers, but it also can be cast very nicely in mathematical equations. Okay, how can something like this be modeled? And for this purpose, I would just like to go a little bit into the physical background of these equations, starting off with the main physical quantities, which are the acoustic particle velocity, acoustic pressure, mass density, and if one goes a bit deeper into modeling, there will also be the temperature, heat flux, and entropy involved. So all these quantities depend on space and time. So it's always the pressure at some point x in space at some time t in time. And they typically fluctuate around a mean value. That's what one would expect from sound waves, right? So if the pressure, there's some background pressure value, and added to this, there's a fluctuating pressure. There's also a background mass density, and on top of this, a fluctuating mass. For the velocity v, we have the same decomposition, but we assume that the background velocity vanishes so that there's no flow in the background, really just the acoustic propagation, and so on and so forth. And well, these are the main quantities with their mean and fluctuating parts. And here are the governing equations. So most of them are just simply physical balance equations. For example, momentum conservation, mass conservation. We have the entropy equation. This equation of state, as it's called in acoustics, that's basically a constitutive relation, a relation between P pressure and the mass density, also involving possibly the entropy here. There's also the Gibbs equation. And what you see here altogether, it's 5 equations. So there's still one equation missing. That's the one I would like to dwell a little bit on. That's the constitutive relation between temperature and heat flux. Well, you might say that it's known, it has to be Fourier's law. That's the typical thing that one would assume, that the heat flux is just proportional to the negative gradient of the temperature. That's where, so to say, the heat flows with a coefficient, the thermal conductivity. However, with this Fourier's law, plugging this into all these balance equations and putting things together, one ends up with a paradoxical situation of having infinite speed of propagation, which is what one would not want to have for a wave-type phenomenon. And therefore, what people have been doing is to look at alternative models. And one of them, which is also meanwhile a classical model for modeling the temperature heat flux relation in acoustics, that's this Maxwell-Cattaneo law. And you see, instead of Fourier's law, what we have is an additional term here, which takes into account relaxation effects. So this tau here is a relaxation time. So as you might observe, it also works out with units because we have a time derivative here. And it just includes also the rate of the heat flux rather than just the heat flux alone. We will see later on, there will be also alternative models for this purpose. Okay, now we have these models, Fourier's law, Maxwell-Cattaneo law. Now, altogether, we have 6 equations. We can put them together and reduce everything to what you already know, for sure, second-order wave equations. Not the linear second-order wave equation, because, for example, here, in this constitutive equation, you see quite a bit of nonlinearity going on, or of course also already in the momentum conservation equation, there's nonlinearity. So it will be nonlinear equations, but second-order wave type equations. So you see here the wave equation for the pressure, for the fluctuating part of the pressure, with the sound speed as a coefficient. There's also some damping involved. In this case, it's strong damping. And over here, there's the nonlinearity. So this is the part that comes from the momentum balance. This is the part that comes from the equation of state, from the constitutive equation. And it's called Kuznetsov's equation. So that's really a classical model of nonlinear acoustics. As you can observe here, it's not only an equation for the pressure. There's still the velocity involved here. And so one has to sort of close this relation between velocity and pressure. And since the velocity appears in a quadratic term here, it's okay to use the linear relation between pressure and velocity that comes from the balance of momentum equation. It's okay. That's actually a physical rule that acoustics physicists have developed, which tells us if you have a higher order term, then one can substitute a lower order law into it. That's the so-called substitution corollary. Okay, it's a coupled system of equations for the pressure and the velocity. One can also reduce this because here we have typically we have irrotational velocities. And so since the velocity is irrotational, it has a potential psi, and with this psi, plugging in this psi here, so of course we can plug in the gradient of psi back here for the velocity, but we can also plug in the psi for the pressure, because due to this momentum balance equation, there's also a direct relation between the pressure and the velocity potential. And so basically all the p's here become time derivatives of psi up to this whole zero factor. And that's why, and then afterwards we have to integrate once, because otherwise there would be a time derivative on everything. So we reduce the number of time derivatives by 1, as you can see here. And that's now the classical form of Kuznetsov's equation in terms of the velocity potential. Okay, one point that I would like to make here is this B on A. That's really sort of historical notation, because these coefficients A and coefficient B come from a Taylor series expansion and eliminating afterwards, which gives this fraction B on A. And this is actually known to be an important quantity in nonlinear acoustics. And later on, we will see that one can even use it for imaging with nonlinear waves. Okay, that's Kuznetsov's equation. Let's move through the further models of nonlinear acoustics a bit more quickly. There's also the Westerveld equation, which can be obtained from the Kuznetsov's equation in pressure formulation by just simplifying this velocity term with the substitution over here, which is justified in many relevant settings too. So also Westerveld, the Westerveld equation is a classical and often used model of nonlinear acoustics. There's also advanced models, and in particular, if one uses this Maxwell-Cattaneo law for the heat flux temperature law, then one ends up, not surprisingly, with an additional term, which just has one more time derivative. So a third order in time derivative on psi with the relaxation time as a factor. Otherwise, it looks like Kuznetsov's equation. And actually, the fact that this avoids the infinite speed of propagation paradoxon can be seen by looking at this combined quantity. Okay, if one takes this quantity and plugs into the equation up here, one sees that actually this set here solves a just weakly damped wave equation. Okay, basically a wave equation just with this weak damping up to some lower order remainder term. And well, weakly damped wave equations have infinite speed of propagation. They preserve this from the undamped setting. And that's also an explanation why, in order to avoid infinite speed of propagation, it makes sense to look at this equation up here. Okay. Now, another advanced model is this Blackstock-Crichton equation. It takes into account energy balance, and it contains the thermal conductivity here as a coefficient. What I would like to point out is really both of them are generalizations of Kuznetsov's equation. And formally, if one puts this thermal conductivity A to 0, then if you look a bit more closely, one just ends up with Kuznetsov's equation, up to a time derivative that we can integrate out on both sides. And also for this JMGT equation, if we just put this tau to 0, then obviously it's really just Kuznetsov's equation. Of course, being mathematicians, we don't want to just put this to 0. We want to look at limits as A tends to 0, and we want to see in which sense does convergence occur and under which conditions, and likewise for this tau. And I would like to talk a little bit about this in a moment. Okay, this is just an incomplete set of many citations, but still many are missing. Just to give you an impression that this has been a field that has found quite a bit of attention also from the mathematical side recently. So just to give you an idea what the difficulties are in the context of these equations, and for this purpose, let's just return to the most simple model that we have here, the Westerveld equation. This is just exemplary for all these problems that, all these models that we and other people have been considering here. So typically one would look at initial boundary value problems for these wave type equations. So we have initial conditions on a bounded domain. One might also have boundary conditions. And in case of Westervelt's equation, so this first one here, it looks like this. And then we want to show well-postness in the sense that we have existence of solutions. The solutions are unique and also depend in a stable way on data such as this G over here or the initial data. And given that we have strong damping here, we might also be interested in decay properties, and indeed they can be established. So long-term behavior of solutions. But the most critical thing here is potential degeneracy of the equations. If you look at this at the first glance, it looks like quite harmless and innocent, just having a squared nonlinearity over there. So it's well known that with wave equations, nonlinear wave equations, one can take much higher powers, even with weak damping. But the point is that there's a second time derivative on top of this. So if one differentiates this out, then there's a term which has the second time derivative of u, clearly. So since in the wave equation, the second time derivative should be in the wave operator somehow, we move it over there. And you see there it is our coefficient that depends on u. And so there's also some leftover quadratic nonlinearity containing ut over there, but this is less critical. So the potentially problematic thing is over there, because clearly if u is too large, if the amplitude gets too large, so u is a pressure here, if you have too large pressure amplitudes, then it could happen that this coefficient over there is not positive anymore. And then it would simply not be a wave equation anymore. It would not describe wave propagation. So that's something which does not happen in reality, and that's actually due to the damping. But of course, one also, in order to really show well-postness, one also wants to make sure mathematically that it doesn't happen. And it's the same problem for all these models. The second time derivative term gets such a coefficient here. So the approach to control this is to employ energy estimates, so derive energy estimates for this strongly or differently, also fractionally later on damped wave equation, and then get a sufficiently high energy estimate. For example, H2 of omega in a three-dimensional domain omega would be enough to have continuous embedding into L infinity. And as soon as we can bound the solution u in L infinity, we get control of this coefficient. And then after all, it's a bootstrapping argument that tells us, yes, we have, on one hand, we get these energy estimates due to these terms over here, and therefore we can also estimate this term. So it's a fixed point argument, basically. Okay, also this allows to give an explanation of this sawtooth or leaning profile of the wave, because we have this state dependence, pressure dependence of the effective wave speed. So once we are here, we can easily divide by this 1 minus kappa u, provided it's non-zero, and it hopefully also doesn't change sign. And then it's in the denominator of this c squared, and we take its square root, then we get such an effective wave speed. That's this c tilde of u. And what you see here, u appears in the denominator with a minus. So there's yet another good reason for hopefully u not being larger or equal to 1 over kappa, because it's the square root and it's in the denominator. But it also explains why for positive u, this sound speed becomes large, because we have 1 minus kappa u, so the denominator gets smaller, so the effective wave speed becomes larger. And on the other hand, for negative u, things become slower. And that's actually what you have seen in the picture. Okay, but now after all this modeling, let me talk a bit about mathematics. And at least the thing that I've promised, that we are going to take limits as the relaxation time tends to 0. So what we want to prove in a mathematically rigorous way, comparing this JMGT equation with the relaxation time term to Kuznetsov's equation, what we want to show is that if we have this family of solutions of the JMGT equation, is there a limit as tau tends to 0? And does this limit satisfy Kuznetsov's equation? And of course, the question, in which sense does the limit exist? With respect to which norm or with respect to which topology? So the challenge here is that clearly as tau tends to 0, this leading order term, the third derivative term, just gets dropped. And so the equation changes its behavior from hyperbolic, although it's not clearly visible here, but if you recall this auxiliary variable set, it's clearly a hyperbolic equation for this auxiliary variable, and actually also it has hyperbolic behavior for this psi formulation here. Whereas this equation here, although there's this wave type thing, because of this strong damping here, it actually behaves more like a parabolic equation. So actually one can show that's also a very classical result that this strongly damped wave equation gives rise to maximal parabolic regularity, and it generates an analytic semigroup. So its first order formulation is an analytic semigroup. So letting tau tend to 0, this was an idea that actually all the 4 of us had. So Vanya and myself, as well as our good friends Marcelo, Irina, and sorry, so forgot his name. So all the 4 of us had almost simultaneously. So we looked into this, but we looked into this from slightly different perspectives. And what I'm going to show you now is the result that we obtained. So that's the one from joint work with Vanya, and just point out what Irina and co-authors have obtained, sort of in parallel. So maybe we don't need to go into this. So we have this, as already pointed out, we have degeneracy also here, because if we just differentiate this out, also here we have this second order in time. Yes, second order in time term with a coefficient that depends nonlinearly on the state. Okay. The plan here is, I will just show this for the Westervelt equation, so without gradient nonlinearities. The plan is to establish energy estimates and then have uniform boundedness in certain norms, and then from uniform boundedness one gets existence of weak limits, and then one can look along these weak limits, then potentially due to compact embeddings one also gets strong limits in certain norms. And that's what finally leads to the limiting results. And so that's contained in these 2 papers. So first of all, to show well-posedness, we look at a linearized problem. And for this purpose, instead of our coefficient 1 minus, let's have a look at this again. Instead of this red coefficient here, we just say we have an alpha coefficient that depends on space and time. Okay, then we have a problem like this. One can derive energy estimates for something like this under certain conditions on the alpha, and in particular, since we are going to use a bootstrap argument, we assume here for deriving energy estimates, we assume that alpha is bounded away from 0 and positive. And afterwards, by plugging in, so to speak, we will show that actually alpha, setting alpha to this 1 minus kappa psi t, that this will satisfy this property. So this is first of all a result on this linearized problem, which shows you that we get well-posedness, existence and uniqueness of solutions in certain spaces, and that the uniform estimates, so estimates that are uniform in tau, are obtained this way. So we have factors tau, but that accompany some of these norms that we can bound. We also have some taus on the right-hand side, so in the data terms. We also have some mild tau dependence in the constant here, but this is after all then uniformly bounded for bounded tau, so it doesn't matter. So this tau dependence here does not matter for taking limits as tau tends to 0, but these tau dependencies, they do matter, of course, because we don't have uniform boundedness of these norms as tau tends to 0, only for these terms here. And this, of course, needs to be taken into account. Before doing this, we need to establish well-posedness of the nonlinear problem, and that's done by the already mentioned bootstrapping, or actually fixed point argument. So we just basically use the linear well-posedness proof, setting alpha this way. That's just the alpha that we need, and then applying a Banach's contraction principle. So for this purpose, one has to show contractivity, and that's done. So that's the typical contractivity that one aims for in appropriate norms. First of all, it's with these tau dependent norms, but this also gives us, of course, something on tau independent norms. Sorry. Okay, one can obtain this again by using the fact that the differences of images under these fixed point operators, again, will satisfy these third order wave type equations, linear ones, with an appropriate alpha and an appropriate right-hand side. And therefore, one can again make use of the energy estimates from the linear theorem in order to get contractivity. Okay, the result from this is that we get, provided the initial data is small enough, because we have a nonlinear problem, we need smallness of initial data, we have existence of a unique solution, and we have boundedness in this norm. Okay, the norm, just to recall, that's this norm here. Okay, that's bounded by a constant that only mildly depends on tau, because the initial data does clearly not depend on tau. And so we have some boundedness. So here's again to recall the norm that we have, for which we have uniform boundedness. A certain part of it is independent of tau. That's the norm in which we will also get uniform boundedness independently of tau. And well, the rest of it is just making use of the fact that bounded sequences are weakly compact or weakly star compact. So some of the spaces here are reflexive. Some of them are duals of separable spaces. So we have sort of a mixed weak star and weak topology convergence in our family of solutions. And this family of solution also therefore converges weakly, mixed weakly star in this space up here. So convergence is just easy to show. Then then one still have to show that the limit satisfies the Westerveld equation, which one can also do, and as well as the initial conditions. And that's, so to say, the formal establishment of these limits as tau tends to 0. So the mathematically rigorous, I wanted to say, establishment. Here are some numerical simulations with realistic parameters. I just would like to show you what these waves behave. So also the simulated waves behave as you have seen in the picture before at the very beginning. So here's just one excitation in the very middle, and then it goes to the left and the right. So it sort of shares its energy between these two sides. That's why the amplitude immediately halves, basically. And so you see, there's not that's the propagation of the wave over time. That's not so much damping here, but what you see is that the wave starts leaning away from the source, so to speak, on the left hand and on the right hand side. And here you see snapshots at the final time instance after 45 microseconds. That's a typical time frame for ultrasound. And here you have typical values of relaxation times in human tissue, for example. And you see if you have a larger relaxation time, then it's this leading over behavior is less emphasized, but on the other hand, it's a more peak-like wave that you observe. Okay, here's also the numerical simulation of the convergence as tau tends to 0. That's the convergence where we expect convergence without rates, where we just expect actually only weak convergence, but you see here in the numerical results, we even get norm convergence. And the rate looks a little bit like a square root rate, which is actually what our colleagues, Irena Lasiecka and colleagues, have proven. And over here, of course, with compact embedding, one can also go ahead and prove rates in spaces where this space here would be compactly embedded. For example, this one here, and you see it seems to be even a linear rate. Okay, we have ticked these boxes here, so we have established this convergence as tau tends to 0 in appropriate function spaces, and also the limiting thing. So, well, what I've shown you is just Westerveld equation, but we can also include this gradient nonlinearity and do it for Kuznetsov's equation. So now I am almost done with time. Or how much time do I still have? According to the schedule, I should finish very soon, but maybe I have
you are 10 minutes late, so you have still 10 minutes, 10, 15 minutes.
Okay, thanks a lot. Okay, just to give you an impression, there's of course other interesting quantities that one could send to 0. For example, the diffusivity of sound. This was this delta coefficient. The difficulty here is that the delta, this coefficient delta, appears next as a multiplier of the damping term. So taking limits formally as delta tends to 0 yields a quasi-linear wave equation without any damping. And that's something which is not easy to handle, or put it the other way around. It actually can be shown that with, at least without the gradient term, it has been shown that the solutions of this equation blow up in finite time. And so for establishing that limit, one can anyway just look at finite time horizons. But looking at finite time horizons, it works again. One can really send delta to 0, so to say, in a controlled way in appropriate function spaces, and then really show that the families of solutions of the damped equation converges to a solution of the undamped equation. So something like this can be done also in the Black-Crichton equation, where we have this thermal conductivity A. Also here, we're just setting A to 0 here and here, and integrating once, we end up with Kuznetsov's equation. But yes, in order to do it mathematically rigorously, one has to think about which are the proper spaces, or more precisely, which are the proper energy estimates that are uniform with respect to A. And then on top of this, one also has to justify this integration in time. So still obtaining smooth solutions. So the initial data has to be compatible in order to admit this time integration, so to speak, or the other direction, the time differentiation. Okay, one can also look at fractional equations. Unfortunately, I don't have time to say much about fractional equations. There's really interesting models on fractional equations in acoustics. We have also, in particular, Vanyo Nikolic has done quite a bit of work on the modeling. which I think is really important to point out, because maybe you know that a lot of work is going on fractional equations, and sometimes people just put a fractional term without asking about the physics behind it. This is something which I think one should not do. One should not do when claiming to look at real physics models. So if one does so, one should also take care of the modeling, which Vanya Nikolic has been doing. And that here's just one example of a model that comes out of this and that can also be physically justified. And then it can also be mathematically justified in the sense that taking this fractional order here and here to the respective integer order, so letting alpha tend to 1 here, one can actually really prove that the family of these psi alpha solutions of the fractional equation tends in a certain sense to the limiting equation. And again, the challenge here is, of course, that as the alpha changes, the order of the equation changes. Okay, now I have to think a bit about how to deal with the rest of time. So I still have sort of 10 minutes. I promised to say something about forward and inverse problems. And so there would be still a section about fractional damping models, but maybe let me just skip this and jump to inverse problems. And in particular, there's a very interesting inverse problem that we have been looking at recently, that's coming back to this B on A parameter that you have seen in the previous equation. That's actually known to be something which is very characteristic of certain tissues, meaning that if you have different tissue, we will also have a different B on A parameter. So B on A will depend on space. If you have a heterogeneous biological tissue, then at every point space X, you might have different value of this B on A parameter because there might be different tissue there. And on the other hand, if you have this B on A parameter as a function of X, if somehow we manage to determine this B on A of X, then this also gives us an image of the tissue in the sense that corresponding to typical values of liver, muscle, bone, and so on and so forth, we know, given that we have a certain B on A of X, we know which tissue we have at this point. So this gives us a way of doing tomography, of doing medical imaging. This has been investigated also already quite some time ago by many well-known physics group. And only recently, mathematicians have been started looking at it. Well, as a mathematician, of course, one would go back to the PDE and recall that this B on A parameter was part of this kappa parameter. It appeared inside the definition of kappa. And instead of saying that B on A depends on X, we can say kappa depends on X. And then it's really a coefficient identification problem in a partial differential equation. So here's the PDE. That's, again, basically Westervelt's equation with a certain damping here and with a coefficient kappa of X. So what we want to do here is we have a boundary value problem, for example, with these impedance boundary conditions. We have initial conditions, typically everything is at rest at the beginning, so initial condition 0. And in order to determine what we want to determine, namely kappa of X, we need additional observations. So this will be observations on the boundary. So sigma will be typically on the boundary of the domain or immersed in the domain, but typically far away from where the kappa of X is really a space-dependent function. So that's the typical setting in medical imaging. And well, we have in 3 space dimensions, X has 3 components. Sigma will be lower dimensional. For example, if it's part of the boundary of omega, it will be just 2-dimensional. And so where's the third component, the third dimension that would make up for identifying uniquely three variable function, that's now the time interval. So the time dimension makes up for the missing space dimension, so to speak. And to really prove that it makes up, that's also something which is mathematically quite challenging. That's the usual thing that we do in inverse problems. Uniqueness proofs, for example, in this case of uniquely recovering a space-dependent coefficient in a wave-type equation from boundary measurements over time. Okay, I haven't said what D is here. D is a damping term, and here's also where this fractional damping comes into play, which I didn't have time to go into detail about. So here are some typical models. You see also in certain limits, this would correspond to the strong damping that we had before. Okay, the challenges here in recovering kappa of x arise that from the fact that already the model equation is nonlinear and the nonlinearity occurs in the highest order term. Our unknown coefficient appears actually in this nonlinear term, so which looks like, well, making it really, really troublesome. But actually, the fact that it appears in the highest order term, as you might already conjecture, this high derivative in the kappa of x term also emphasizes the nonlinearity. And it emphasizes in particular the term in which kappa of x is contained, and this makes it sort of more visible to the observations. Of course, very indirectly visible, but at least more emphasized. So what I have already mentioned is that making up for the third space dimension, because we only have boundary observations, happens through the time dependency of the observation. So the observation is so at least in one component, it's so to speak orthogonal orthogonal to the space dimension. And this is something which is known to lead not only to this difficulty of really proving uniqueness, but also to severe ill conditioning. So inverse problems are typically unstable, so stability cannot be expected. And for problems of this type, it's really severe ill-postness, exponential decay of singular values of the linearization, which makes numerically solutions extremely challenging. But there's an important point here. The nonlinearity that appears in the equation that makes the analysis challenging also helps in the sense that it adds information. And the point that I would like to make here is relating back to the picture on the very first slide, actually on the second slide, the one in frequency domain. So, well, in the linear setting, if you have a linear wave equation, if you double the excitation, it will just result in doubling the amplitude of the observation. So that's nothing exciting is going on here. So by changing the amplitude of the excitation, we do not get any information in a linear equation, but in a nonlinear equation, modifying the amplitude of the excitation changes the picture. So it also changes the observation. It gives additional information. Likewise, also for wave equations, in the linear case, if you have excitation at a certain frequency, then also our observations will only occur at that single frequency. Whereas, as you have seen in the picture on the second slide, in the nonlinear case, even if we just have a sinusoidal excitation at one single frequency, the response will exhibit this so-called higher harmonics. So if you maybe remember, in the frequency domain, we had these spikes at multiples of the excitation frequency. And of course, at these multiples of the excitation frequency, we also have these observations. So we have more information. Information multiplies, actually. So here's just to give you an impression on what has been going on recently in the mathematical literature on nonlinear acoustic tomography. And well, let me point out, well, I don't have time to really point this out. Maybe in the last few minutes, what I would like to go a little bit more, right, at least show you the equations on this point of excitation at a single frequency, but observation at multiple frequencies. That's just by comparing it to the linear case. This is just to recall the picture that we had at the beginning. It's a slightly different picture. It's now with real measurements. Here's the time signal. On one hand, with small amplitudes, the yellow signal here, where nonlinearity doesn't play a role. And with higher amplitudes, the blue line, where nonlinearity is important. You see this in frequency domain. So that's a similar picture. It's not as spiky as the one before. But you see that you have contributions for the blue line, you have contributions at higher harmonics, whereas in the basically linear case, it's just a fundamental harmonic. And that's also what is intuitively clear from the linear wave equation, because in the linear case, you just have the linear wave equation. Here it's also written without any damping. And you probably know what people often do, for example, in inverse scattering problems, doing a harmonic excitation by a plane wave, for example, then one can also use a harmonic ansatz for the solution. And this harmonic ansatz will just simply solve the Helmholtz equation. And so the space-dependent part satisfies the Helmholtz equation, the time-dependent component is covered by this single frequency sine cosine excitation behavior, not excitation, but response. Okay, what happens if we add nonlinearity here? For example, with the Westervelt equation. Again, we just use a single frequency excitation, so it's just one omega up here with some time-dependent source term. But now, due to nonlinearity, we expect responses at multiple frequencies. So mathematically speaking, we have a function of space and time. We expand it with respect to this basis of LT2 of 0t, where capital T is the period of this, the fundamental period, and with coefficients that also depend on space. Okay, that's for the moment, it's just an L2 in time series expansion of the solution. But plugging it into the Westervelt equation, we end up with not just a single Helmholtz equation, but a system of Helmholtz type equations. So you may figure out here up to this sort of complex part that is actually just reflecting the damping here. We basically have the Helmholtz equation over here, but and we have the excitation on the other side, a bit like in the previous case, yes, looking like this, up to the damping. But in gray, we also have further terms that come from the nonlinearity. And not only do we have nonlinear terms in this fundamental frequency, but also we have to take into account all these components of U. All those follow Helmholtz type equations with right-hand sides that fully couple to all the other equations. So including these gray terms, we have a full coupling among all these terms. And that's maybe not surprising because up here we have a quadratic term. So thinking about frequency domain, we can also view it like as doing the Fourier transform with respect to time. And doing Fourier transform of a product means that we have a convolution. And you might see here, that's actually what you see here, or what you see here. It's a discrete convolution here because we are looking at a discrete set of frequencies. We can do so. And so it's sort of a discrete convolution that we end up with over here. Sometimes one skips the gray terms, then it's only, so to speak, a triangular coupling. One can solve this forward in with increasing frequency, but still it's a coupled system. Well, plugging in this ansatz, of course, needs to be justified. So first of all, what one has to prove is that if one has a periodic excitation of the Westerveld equation, then the solution will be periodic as well. Otherwise, this ansatz would not make sense. And that's also something which we have done here. This is just to give you an impression on what the result looks like. Okay, and with this, well, this is just to sort of mathematically underpin the point that the appearance of higher harmonics shows that information multiplies in the nonlinear setting. So if I still have a little bit of time, I would like to show you some reconstructions, so solutions of the inverse problem. But, well, I am afraid I have already gone over time. So I think I should just simply skip to the very end. And thank you very much for your attention.
Thank you very much, Barbara, for your interesting talk. It was clear, very clear. Are there some comments or questions? The people that are online can be also write in the chat or can open the microphone. So perhaps I can start with questions. Barbara, just some curiosity. Do you know, or I don't know if you have some results, when in the equation we consider a delay? So since
yes, that's an interesting question. Actually, to some extent, there is also, there's clearly an interest in something like this. And we have also been looking at this in a bit by modeling memory, by convolution with kernels like this.
Okay.
So this has been done, for example, here in the context of elasticity equations, but also in the context of wave type equations. Actually, these fractional models, now they are too far away. Sorry, maybe it doesn't make sense to try well, I will give it a try. These fractional models with the definition of the fractional derivative. So here's the definition of a fractional derivative. It's also in some sense a convolution with a certain kernel. And in this sense, it's also a memory term with a memory kernel. And so also for this particular fractional equations, there is some analysis around, well, maybe, yes, for this one here. So in this sense, this is already something containing memory, but we also have been looking at more general memory kernels instead of these particular ones giving rise to fractional derivatives. But there's certainly interesting work to do here. So looking at memory and delay is certainly a topic that would be of interest.
And another curiosity, in the linearized Westerveld equation, you consider alpha xt strictly positive,
yes,
since it is related to the fact that alpha is given by 1 minus ku, and this has to be strictly positive. But if we consider a general function, can be 0 or not?
Yes, there's also, so for example, for this linear problem, there's also the possibility of just setting alpha to 0 or even choosing a negative alpha. This, of course, influences the decay property and stability properties of the equation. So there are certain critical values of this alpha also related to the wave speed. So it's sort of a combined coefficient between alpha, wave speed, and the tau, that if it goes beyond or above or below a certain critical value, then the stability of this equation will be lost. And there's actually a very detailed analysis of things like this by people like, again, Irina Lasiecka, also Roberto Tricciani with co-authors has done a lot of work on these MGT equations. So that's the linear versions. And here the value of the alpha S related to tau C and also B is studied.
Okay. Just the last two questions. In the first problems, you consider the function K that can be degenerate, and it is in front of you. You have some results if it is in front of the Laplacian. And the second one, and this is my last question, is a limit on the dimension of omega in this case, or
so in this case, so we can consider omega, three-dimensional omega.
Three-dimensional.
So of course it influences the level of regularity that we can use, because in order to get this embedding into L infinity, of course this is space dependent, and in order to get control of this term, we have to go up higher with regularity, up to larger than 3/2, of course, if we are in 3 space dimensions. For lower dimensional omega, in particular for 1-dimensional omega, one can prove low regularity, so existence of low regularity solutions. But the typical physical setting would be 2 or 3-dimensional. And then, yes, the question of what happens if the coefficient and also actually even the nonlinear coefficient appears not in the second time derivative, but in the space derivative. That's actually an interesting question, because it actually arises in one alternative model of nonlinear acoustics that I've not shown, namely the so-called Blackstock equation. So I've shown you the Blackstock-Crichton equation, that's something else. There's also the Blackstock equation, where a nonlinear term would be sitting here in front of the Laplace. But it would also come with a sort, so also here we have 1, so to say, 1 times u tt and some perturbation, some nonlinear perturbation. And also here it would be 1 and a nonlinear perturbation. And then one can go ahead and study what happens and establish well-posed. And this has actually been done by Vanja Nikolic with co-authors sometime, I think 2 or 3 years ago. That's also an interesting point. And it's also interesting to look where the space-dependent coefficient sits, whether it sits inside the Laplace or outside. Yes, because then depending on this, you can admit more or less regularity of this coefficient. Quite often in imaging, one is interested in low regularity coefficients. And then it's more advantageous if it appears like, for example, the sound speed here, which can actually also depend on space outside the Laplace. And that's actually the case for this Blackstock equation too. That's why it's also interesting from the inverse problem point of view.
Okay. So Barbara, there are some questions in the chat.
Okay, yes, I will have.
Can you read?
Yes.
No,
okay. I will try to do it in this order. Can we extend this to all fractional equations? It can, here we go, yes. It's to put the parameter m. You put the parameter m. So the parameter m, well, the parameter, so m appeared as a counter for the higher harmonics. That's probably not what you mean.
In the last part.
In the last part, okay. Then it's, there's a new message maybe. In the last part, okay. Yes, that's the number of higher harmonics that one takes into account. So in principle, it's infinitely many, but in practice, maybe you have seen there's a strong decay of these amplitudes as the frequency gets higher. And so usually it's just 2 or 3 higher harmonics that one really takes into account. And in the reconstructions that I was going to show, it's actually just 2 higher harmonics that one uses. But it does make a difference from just m equal to 1. So m equal to 2 already gives a lot more information as compared to just looking at the linear case. Does this answer your question?
Lamin, it's okay.
Okay.
He has
Yes.
also for omega.
Yes, there's a question of unbounded omega. Yes,
Yeah.
work has been done on this, not by me, so I can only report from a certain distance because it's not my own work. But in principle, the strategy is like usually for Cauchy problems on unbounded domains, looking at basically the idea is to go into frequency domain with respect to space. And then first of all, establish some results again for the linearized equation, and then go back, get from that a linear, sort of a linearized energy estimate, and then look at the nonlinear equation, and again do basically a fixed point argument. So, for example, also Vanya Nikolic is one of the persons who have done something on this by together with Pelkathem Saidhouari, and also Marta Pellicer is a person who has done a lot on this. So yes, people have done work on this. Some of the references, I hope, on my overview slide are only also on this. So of course, I'm happy to share my slides afterwards. The space of work and how is it, maybe it's also, so we can also extend it to fractional equations, not arbitrary fractional equations, but there's also a certain, first of all, just from a physical point of view, some of the equations make sense, some of them don't. And yes, some of the fractional equations. Basically, the way in which we look at this is, as already has been mentioned in my previous answer, equations with memory and certain memory kernels. And then it's a certain interplay between these memory kernels and the other terms in the PDE that have to be satisfied in order to get out reasonable energy estimates, which also sort of relates to the physical background, that the equations that would make sense are those that would exhibit a certain energy dissipation or energy conservation, but certainly not a blow up in energy. And this also is reflected in the mathematical analysis. So
Okay.
yes, there's also work at this. So, but maybe now it's time for you to have a coffee break, isn't it?
For lunch.
Of course, I'm happy to answer further questions, but you might already be wanting to go for coffee or for some other breaks. I don't want to keep you from this.
Okay, so are there other questions or comments or remarks? If not, thanks again to Barbara for our talk. And now we have a break. And I don't know at what time we start again. So we'll start again in 1 hour and 30 minutes. Okay, so see you later.
Okay, so
Thanks,
bye.
Barbara.
Bye. See you. Thank you. Bye.
See you. Thank you. Bye-bye.
Bye.
Welcome back, everyone. Can you hear me? Okay, in a few minutes, we are going to have a little presentation about our project of ICMAM Latin America. We're going to discuss some things before Professors Wigderson talk. We want you to know about our initiative, our project, our events, and some things we have been doing. For now, I can tell you that this initiative began at the Universidad del Valle, really, which is in Cali, Colombia. Maybe some of you know that university. And it's an initiative from ex-students from that university of the mathematics program over there. So we prepared a little presentation just to show you what we have been doing these years, and always invite you to join us in the events, in the congresses, with some contributions, and where we want to look forward. So we're preparing the auditorium to present in, or also for the people who is here in the Universidad Javeriana. And I think in about 15 minutes we will be starting. From now, maybe I can unmute everyone if you want to discuss before the presentation. Maybe you want to talk about where are you, which countries are represented here by you, the other stuff.
¿Me escuchas bien, Brian?
Sí,
Muy bien.
espérame. Ya estás presentando, ¿cierto?
Sí. Esto es lo que se ve, ¿no? Listo. Okay, good afternoon, everyone in Colombia. Okay, the idea of this meeting is to give information about ICMAM Latin America. So just let me give information about our organization, right? That you are looking at this moment is our website. Essentially, just let me tell you, ICMAM, which we call the ICMAM Latin America, which we call International Community of Mathematicians from Latin America, is a young research organization that born in 2020 in the pandemic time. From that time, we start organizing several conferences, right? Essentially, you can see in our website, ICMAM conferences, right? And then you will see some of the conferences that we have planned that we are organized from 2020, like ICMAM Latin America 2020, ICMAM Latin America 2022, right? Essentially, our motivation to organize this conference has been to allow young researchers, right, to interact with outstanding mathematicians. Okay, so from that point of view, in 2022, you can see there we had very nice speakers, like let's say like Terence Tao, like Michael Ruchansky, like Simon Donaldson, Enrique Suazua, Carlos Koenig, Tatiana Toro, Harald Helgoff, David Dos Santos Ferreira, right? All of them, of course, outstanding mathematician, and also a very nice team of speakers here. What is important, that was important, is that we keep the videos of these talks. You can, if you want to have a look about what was ICMAM in 2022, there is a recording about all the conferences. I suppose there are somehow interest, especially for young researchers, to see, for instance, which is the topic in which outstanding mathematicians are working, right? Here you can see ICMAM organized conferences. ICMAM also has some agreements with international societies like ISAAC, which is actually the International Society for Analysis, Its Applications and Computation. The idea was to organize with the support of ISAAC several conferences and seminars like Mathematics and Memory. One seminar that we plan and that has two sessions every month, right? You can see also two upcoming conferences, right? Between ICMAM and ISAAC, like the conference for women in mathematics, which actually will be organized in November of this year. And the next week we also will have the conference of analysis in developing countries. So people that are interested in analysis and who wants to somehow hear about what researchers from developing countries are doing can visit the website of this conference and maybe to see how to connect, right? There is also a plan to organize ISAAC Congress, which is actually the main congress of this organization, of the International Society for Analysis, Applications and Computations, in 2029, which is supposed to be in Barranquilla, in Colombia. And behind of this plan is all the team of ICMAM. Just let me tell you that you saw today one talk. You had the opportunity to hear today the talk of Professor Michael Ruchansky, right? Which is the director of the Ghent Analysis and PD Center. Just let me tell you that there is one activity that will be organized between ICMAM and the Ghent Analysis and PD Center, which is this one, Global Minds in Pseudo-Differential Analysis, which is a project that will be organized next year in 2025 in Belgium. And the idea of this conference will be to allow some researchers from Colombia to interact with the researchers from this international center, right? Somehow this is part of this I mentioned is somehow a list of all the events that we had, that we are going to organize, seminars that we organize, and future events. You can also have a look to past conferences, right? like the one that we organized in the Friedrich Alexander Universitat in Erlangen with the group of control theory of Professor Enrique Suazua. There also you will see the conference, the name was Trends in Mathematical Science. If you visit the website of this conference, you will see several recording videos about the about the speakers, very nice speakers that were in that program. In December also, because ICMAM is trying to make agreement with different international societies in Latin America. For instance, we make agreements with the international societies from Central America, societies from El Salvador, from Nicaragua, societies. We also have under construction one agreement with the Mexican Mathematical Society. So the idea was to organize one colloquium of analysis and partial differential equations. So if you are interested, you can have a look to this colloquium, right? Especially, for instance, if you are in Central America and you want to see what the people from Central America is doing in analysis and partial differential equations. So this just is brief information about our conferences. Let me show you, we have different research projects, right? If you visit our website, you will see our Springer Book of Series, right? Which is actually not a series completely, because there is a series of Springer, which is Research Perspective and Analysis and PD Center. And the director, the editor in charge of this series is Professor Michael Ruchansky. And usually this series gives us the framework to publish several somehow books related with our conferences, right? So for instance, related to ICMAM 2022, you can have a look to this book we published just this year, right? The conference was 2 years ago, but the book was published this year about analysis and partial differential equations in Latin America. You can see there the information of the book, and also some upcoming books also, like for instance, one book also dedicated to analysis of partial differential equations, right, in Latin America, that is based in one conference on analysis of partial differential equations that we organized the past year in 2023. Sarah, you will remember that was a satellite conference, right? Satellite conference that we organized also, where we also have, like, in following the spirit of ICMAM, different speakers, like for instance, we had the talk of Charlie Pfefferman, right, a Fields medalist. You can have a look also to this interview we made with him. Maybe good for the young researchers, right, to see how people like Charles Pfefferman do mathematics, right? If you want to see something about the history of one big figure in mathematics like him, this is a good opportunity. There are also some recordings of these conferences. You can have a look there. And then dedicated to this conference, we also are planning to publish one book, right? Probably at the beginning of the next year. There is also one book that is in preparation, right? Which is Women in Mathematics Latin America 2024. This is another of our projects, right? This was a project supported by the International Mathematical Union. The Ghent Analysis and PD Center and his series give us the support to publish this book. And you will see, if you came here and see the projects that we have in terms of women in mathematics, right? You see, for instance, one conference, the conference I mentioned before that will be organized in November, right? And you will see the different activities that maybe are related with the work and the visibility of women in mathematics in Latin America. For instance, this kind of project took the attention of other people in Latin America, like in the Chamber of Senators in Mexico. There you can see Yuriko Pitones, who actually is one of the leading woman mathematician about the project of women in mathematics, talking in the Chamber of Senators in Mexico. in Mexico. And so on. Just this is somehow one a small report about our activities, and to allow the people that is attending the ICMAM Latin America 2024 to keep updated with respect to all this conference and all these projects. So I want to invite you to visit our website, right? To see, for instance, our video explaining which is our vision, maybe to visit our website and to see who is the people, right? Are the people that are behind of the organization of our conferences and of our activities. And if you want to participate, organizing some conference, or if you want to organize one activity in which you think that ICMAM can contribute, just let us know. We can see how ICMAM can somehow support your activity. So that's all that we wanted from ICMAM to show you, right? Maybe just I will finish the presentation with some words in Spanish, right? For the people that is in Universidad Javeriana, in Cali, Colombia. So, buenas tardes a todos. Gracias por estar aquí. De verdad que para mí es un placer que en especial los estudiantes de la Universidad del Valle, de la Universidad del Cauca y de la Universidad Javeriana pues puedan asistir al evento. La organización ICMAM Latinoamérica nació hace 4 años y nació durante la pandemia. Iniciamos como un proyecto que quería contarse entre amigos que están haciendo jóvenes matemáticos graduados de la Universidad del Valle en ese momento. Queríamos contarnos qué hacíamos en términos de las matemáticas. Vimos una gran oportunidad en el desarrollo de eventos virtuales, ¿sí? En 2022 nos dimos cuenta que ese potencial podía ser enormemente explotado, permitiéndole por primera vez a jóvenes matemáticos unibayunos, a jóvenes matemáticos colombianos, interactuar y escuchar el trabajo científico de los mejores matemáticos del mundo, de personas como Terence Tao, de personas como Simon Donaldson, ¿verdad? Personas que de alguna manera han sido galardonados con premios internacionales como la medalla Fields. Ahora, luego de este conversatorio, tendremos a Avi Vigderson, ¿verdad? Que ha sido galardonado con el premio Abel, ¿sí? Naturalmente son premios que en la comunidad matemática son atractivos para los matemáticos, por supuesto, pero que también muestran cuál ha sido la profundidad del trabajo de los matemáticos que han sido galardonados con esos premios, ¿sí? Organizamos este tipo, digamos, de iniciativas para inspirar a las jóvenes mentes matemáticas en este momento, para permitirle a los jóvenes matemáticos, especialmente en este momento de Colombia, conocer el trabajo de científicos que están liderando y que están cambiando la perspectiva matemática, digamos, en ese momento, ¿sí? Entonces, no sé cómo haya sido la perspectiva de muchos otros matemáticos 10 años atrás o 20 años atrás, pero escuchar una charla por un medallista Fields o escuchar una charla por un premio Abel, casi que estaba en la imaginación, casi que era un sueño, ¿verdad? Y nosotros, pues digamos, a través de esta iniciativa y del trabajo de todo el equipo de ICMAM, la mayor parte de ellos son matemáticos colombianos, matemáticos mexicanos, matemáticos centroamericanos, pues han puesto, digamos, ese trabajo a su disposición, ¿verdad? Han puesto, digamos, esa experiencia que puede llegar a inspirarlos y de alguna manera, permitirles a ustedes, pues, ganar algo de inspiración para sus carreras, ¿sí? Entonces, pues, esto es ICMAM, es una organización independiente, distinta de otras organizaciones de pronto más oficiales y más antiguas que hay en la región, como Malca o como las sociedades matemáticas de cada país, pero que pues tiene unas actividades complementarias que busca sobre todo inspirar a las jóvenes generaciones que vean, digamos que les permitan, digamos, vivir experiencias que de otra manera distinta, de una forma virtual, no se podría hacer, ¿verdad? Porque todos sabemos, hay ciertas limitaciones, no tenemos mucho financiamiento para traer speakers de este nivel en presencia aquí a la Universidad Javeriana, por ejemplo, o a las universidades colombianas, y pues lo hacemos de la manera en la que lo podemos hacer en este momento, que es de forma virtual. Entonces, como saben, es una iniciativa que está para el servicio de ustedes. Desde ICMAM, digamos, desde el equipo de ICMAM siempre buscaremos organizar iniciativas que de alguna manera los inspiren y esperamos que en el futuro las personas que están aquí también puedan ser parte de nuestras iniciativas. Si quieren organizar conferencias y creen que ICMAN los puede soportar, estamos para soportarlos. Si consideran que podrían organizar seminarios y que ICMAN puede soportar en nombre de esos seminarios o esas actividades, por supuesto que nos encantaría hacerlo, ¿verdad? Porque nosotros consideramos que la investigación matemática es importante en diferentes partes del camino. No es la misma investigación matemática que hace un estudiante de pregrado, un estudiante de maestría, un estudiante de doctorado o un matemático ya establecido, pero en cada parte del camino la investigación matemática se puede disfrutar. En cada parte, digamos, del camino, la investigación matemática tiene una complejidad distinta y si bien escuchar matemáticos establecidos como esto, pues nos sorprende un poco por la cantidad de lenguaje que nos tenemos pues que cargar para poder entender, digamos, en términos de contenido científico, de alguna manera el vocabulario o las cosas que ustedes lleguen a escuchar en este momento, en el futuro, cuando tengan una formación más sólida, puede llegar a ser muy valiosa, ¿sí? Entonces, esperamos que disfruten en la medida de lo posible la experiencia y siempre que ustedes consideren que ICMAM puede soportarlos de alguna manera, no duden en contactarme, en contactarnos. Allí en About Us, sobre nosotros, está todo, digamos, el equipo, el consejo de ICMAM y a cualquiera de ellos les pueden contactar con su iniciativa y bueno, lo que esté en nuestras manos, pues lo pondremos a su disposición. Así que muchas gracias por estar aquí. Muchas gracias a nuestros speakers por estar aquí también. Los speakers que han aceptado venir digamos, de forma presencial. Profesor Andrés Villaveses de la Universidad Nacional. Profesor Michael Ruchansky de la Universidad de Gante. Sí, el profesor Jesús Alonso Ochoa de la Universidad Javeriana de Bogotá. Y muchas gracias a la profesora Diana Bueno, ¿no? Que ha sido el artífice de que podamos organizar por primera vez de forma presencial, de forma híbrida realmente, ICMAM. Entonces, pues, muchas gracias a todos y los espero activamente en la conferencia del profesor Avi Wigderson, que iniciará en 26 minutos a las 2 de la tarde. So, thank you very much to all the people that join us in this short discussion about the activities of ICMAM Latin America. And see you soon in the talk of Professor Avi Wigderson in 26 minutes. So thank you very much.
Hello, hello, Professor
Hi,
Widerson.
Avi, yes.
Hi, welcome.
Thank you. Good to be here or somewhere.
No, thank you for being here, Professor. It is really an honor to have you here.
Yeah, but
Could we-
please call me Avi. Nobody else calls me anything else.
Abe.
Yeah, Avi, that's my name.
Okay, okay, okay. Professor Avi is okay, or just Avi?
Avi is fine for me.
Okay, Professor, will we be starting in about 12 minutes? Maybe if you can try to share your screen
Yeah,
and
let's
check
check
it's
it. Yeah, very good.
everything's okay.
Just 1 second. Um, let's see. Mhm. You
It's okay.
see? Yeah.
Yes, yes, yes. We're seeing. It's
Okay, let me just move to presentation mode. Yeah,
yeah,
let's see.
yeah, yes.
Very good.
Okay, Professor, maybe you can wait just a few minutes.
Yeah, you tell me when to start. I am in no hurry.
Okay,
But I
nice.
have an hour, right? 50 minutes.
Maybe between 45 and 50 minutes
50 minutes, yeah.
and 10 for questions. But
Yeah.
if you go a little more, there is no problem.
Okay, great. Yeah, no, it will be 50 minutes, no problem. What's your name?
I'm Brian.
Brian. Yeah, okay. So we corresponded with you.
I'm not in Brazil at this moment. I'm in Cali, but in Cali, Colombia.
Okay.
Have you heard?
Yeah. No, I know. Yeah, I heard the name. Yeah. I never been in Colombia.
Yes. Ah, it's nice. You
Yeah,
should.
I know. I heard, Israelis, they love to visit South America and they travel all over. So I talked to, several people who've been there.
Yeah. Yes, because this time we're having this event in hybrid format. So a few talks are in person here in the Universidad Javeriana in Cali.
Yeah, and how many people are actually there in the audience?
In person, I don't
Yeah,
know.
you don't
No,
know.
because
No, but
because
maybe you know for other reasons. Maybe
no,
some.
because I am in charge of this virtual part.
Yeah, I know, but
Maybe
nobody told you how many people actually came.
to hear in person, I think that there was like 60 people registered.
Okay.
Mhm.
So this is about what you get in every year, or?
Well, this event is biannual, is every
Biannual,
2 years. Yeah,
yeah.
it's okay. And last time, no, virtually we have like I think 600 registered people, but in virtual format. In person is less.
Yeah.
But for now is okay. Everything is good so far.
Yeah, that's the end of the second day, right?
Yes, this is the second day. And we have people from many countries. In particular, we have the students, undergraduate students from the Universidad del Valle and Universidad Javeriana.
Mhm.
They are in person here in the auditorium. We are projecting the screen in the auditorium
Uh-huh.
for they to see all the
Right.
presentations.
Yeah, I met today Peter Sarnak, and he told me he already spoke yesterday.
Oh,
He's,
yes.
we are in the same place, so.
Okay, nice. Nice, nice. Yeah, we know. Yes. Okay, Professor, maybe we can start now. I am really honored to introduce Professor Avi, who is currently a professor at the Institute for Advanced Study in Princeton and has made groundbreaking contributions in several fields. Professor Avi was awarded the Nevan Lina Prize in 1994, the Gödel Prize in 2009, and the Amazing Nobel Prize in 2021 for his fundamental contributions to theoretical computer science and discrete mathematics. I am glad. Thank you for being here today, Professor. I hope you feel welcome here, and you can start now.
Thank you very much, Brian. I'm very happy to be here, even though I'm far away. So it's always strange to give a lecture without seeing the audience, but we are in this world of Zoom already. So I'm going to talk to you about the value of errors in proofs, and in particular, I'll tell you the story of this journey of about a century, which is the evolution of proof systems. I will explain this title as we go along. The basic plan of the talk is I want to talk about the value of errors in proofs and how they impact essentially everything, science, technology, philosophy, if you will, and mathematics. But before value of errors in proofs, I'll talk about the value of errors in computation. And before that, I just need to talk what are proofs and what are computations. Most of the main message of the lecture will be just that it is a story, one among many, that follows the methodology of my field. My field is computational complexity within the theory of computer science. And you'll see as we evolve part of this methodology, which in particular includes modeling, algorithmic efficiency, classification, reductions, completeness, and so on, from the lens of proofs. So proofs and computations go along for many millennia. I'll give you just 2 points that you are familiar with from this very long history. The first one is Euclid's famous book, The Elements, which we all know as a collection of proofs of theorems in plane geometry, and it's a deductive system. It deduces all of them from 5 simple familiar axioms. But if you look at all these proofs, they're actually algorithms. They are actually constructions, explicit constructions of point sets in the plane, using 2 basic operations, the use of a straight edge and the use of a compass. So what this means is that proofs and computations coincide for plane geometry. For every proof produced, there is an algorithm that actually gives you the construction that proves that's ahead. That's the turn of the 20th century. Hilbert had a dream that what happens in plane geometry happens in all of mathematics. More precisely, he believed that truth in mathematics is the same as probability in mathematics, and moreover, that everything provable can be computable by what he called the mechanical procedure. Of course, as we know, this dream was completely shattered first by Gödel's incompleteness theorem, which refuses the red equation, and then by Turing, proving its undecidability theorem, disproving the second. His main contribution was to define what computation actually means, what algorithms mean, and this is what we call today Turing machines. This paper had a huge influence. In particular, it started the computer revolution that we all are part of. But I'm not going to talk about computers. I want to talk about theory. So we'll talk about algorithms or Turing machines computing decision problems. What do I mean by decision problems? There's some fixed S, like the prime numbers. We are given an object, a number, for example, and we ask, is it in the set? Is it a prime or not? This is the kind of problems our algorithms want to solve. And Turing defines essentially two families of sets, those that are computed by finite algorithms, these are decidable, and recursively enumerable sets, which is a larger class. This is a family of sets that are provable to finite algorithms, namely that finite algorithms can verify. And he famously proved that these are different by showing that the halting problem for Turing machines, which is basically a problem of debugging programs, is unsolvable. It is in the second set in RE, but not in R. To point out that the famous Peeves NP question that we, are still searching the answer for is actually the same question about the finite algorithms by efficient algorithms, by which I mean algorithms running in polynomial time. There's only one notion of efficiency. We'll stick with it, but of course others were studied. So this analogous question, different form. Okay, so I want to start by some examples of what proofs are and related concepts of claims, arguments, proof systems, verification, so that we'll see what in general proof systems are and what are proofs. So the basic underlying question is, what is a convincing argument in any setting, even when you are trying to convince a friend to vote for someone? So there is some claim in the background. We all know that some element is in a given set. There is a verifier who would like to know that, so he would like a proof of that. And there is a prover who knows the answer, in fact, knows the answers to every question, is infinitely clever, but you cannot trust this prover. So in order to verify claims the prover makes, prover needs to send some kind of an argument to the verifier who looks at this and decides whether he believes the claim or not. Let's see some examples. Here's the proof system for the composite numbers. Claims are that some numbers are composite, like this one. What's an argument? It's a very simple argument. It's just two smaller numbers whose product is a given input. So verification is a simple procedure, very efficient algorithm. It's just multiplication. This efficient verification is crucial. And of course, in general, it works for any number. Such proofs exist for all composite numbers. There are no proofs like this for prime numbers. And I want to stress that, so this proof system has a set of theorems. Everything the verifier accepts. This is a set of composite numbers here. And I want to stress that the arguments, namely what the prover would provide, is something that doesn't have to be efficiently computable. It can come out of thin air or, in fact, in this particular case, we believe that finding such arguments are difficult because we believe, or at least security systems depend on the belief that factoring integers is a difficult problem. So this is irrelevant to proof systems. We only want the verification to be efficient. Here's another example, this proof system for Sudoku puzzles, in which claims are that a given puzzle is solvable. An argument is just the obvious filling of this table with the missing numbers, such that you can verify it by checking the Sudoku rules, the famous Sudoku rules. Again, verification is very simple to check the Sudoku rules that there are no different numbers in no similar numbers in rows, columns, or subsquares. And the set of theorems provable in this system are all these puzzles, initial inputs, which are solvable. This is not a finite set because you can generalize Sudoku to any dimension you want. So again, it's an infinite set, and some puzzles are solvable, some are not solvable ones in this system. Maybe a more familiar example to everybody is just standard deductive systems from logic, for example, piano arithmetic. In this proof system, objects are formulas over integers, which I denote by capital letters. There are axioms, like in plane geometry, but about numbers, and some deduction rules which tell you how to infer some formula from other formulas, for example, modus ponens. If you know that A is true and A implies B is true, you can infer that B is true. How do arguments look in this proof system? Well, they are just a sequence of formulas. If you are trying to prove claim C, the last formula should be C, and all the others should be either axioms or follow from previously given axioms. So this is something that, again, very simple to check efficiently. It's all syntactic. And this is a much more interesting proof system than the two previous ones because it contains theorems in number theory, like that there are infinitely many primes, or the Fermat's theorem is true, and so on. Okay, so you've seen some few examples of proof systems. Now we try to generalize them to capture all of them, which is what we like to do in complexity theory. What are the essential features of all of them? Well, the two properties of proofs, namely completeness, saying that true claims should have proofs, soundness, that false claims do not have proofs, and finally, this insistence of efficient verification. So distinguishing the true and false claims is done by efficient algorithms inspecting the argument. And efficient, again, for us will be polynomial time. The complexity theoretic point of view of this is the formalization of the same statement was done by Cook and Rachel. What's the formalization is that a proof system is defined by an algorithm, the verifier. It's a machine that has two inputs. One can be called a claim, the other is an argument. And as I said before, should satisfy two properties. If the claim is true, then some argument should convince the verification program to accept. This, of course, the happy case. Then we call the claim a theorem, and we call the argument a proof. Soundness, and if the claim is false, then no matter what argument is fed to the algorithm V, it must reject. And efficiency is encoded into the fact that the verification procedure is efficient. So for every efficient verifier, there's a set of theorems for the system, namely all the claims that are accepted by it. And this is seen as very simply to be another definition of the class NP, is simply the family of all theorems for every possible verification procedure. And we saw that Sudoku or compositeness or are examples of such sets in NP. And also P, the class of polynomial time solvable problems, namely polynomial time computable ones, is a very simple subclass defined by verifying procedure V that ignore the argument. They just look at the claim and determine whether it's true or false. So P and NP come into this picture in a natural way. So far, I talked about the classical setting of proof systems where the verification procedure is deterministic, and now I want to talk about probabilistic proofs and the errors that come with them. So first, I'll talk about computations. I'm sure everybody has seen randomized algorithms, but nevertheless, I'll give one slide introduction. It starts by noticing that nature seems to provide unpredictable phenomena. And so, why not let algorithms use them and make random choices? That was the initial motivation. And to define exactly how probabilistic algorithms look like, let's contrast them with deterministic ones. If a deterministic algorithm computes a function, then whatever it outputs, a of x, must equal this function value f of x for every x, always. That's the deterministic one. Whenever we have a probabilistic one, we are willing to have errors as long as there are few, and there are few for every input. So if B is a probabilistic algorithm for a function f, we demand that the output equals f of x. The output is now a random variable, but we want that with high probability, let's say 2/3, it gives the correct answer. So that's a probabilistic algorithm. And you see that already we introduced error in computation in this definition. We are willing to tolerate this. First of all, I want to address the question of when I say high probability, what do I mean? Here, the probability of error is 1/3, and maybe you can consider it to be too big. Maybe you want error probability 1 in a million or 1 in a billion. That's no problem. This number can be easily adapted because error can be efficiently reduced. How? In the obvious way. If you have an algorithm with 1/3 probability of error, for every k, you can run it k times independently and then take a majority vote. And in this case, the error reduces to exponentially in k for any k of your choosing. So you can really make the error arbitrarily small. What's the value of allowing errors? We allow something normally we wouldn't like, but the value is that we seem with these algorithms to solve many other problems that we cannot solve deterministically. I want to stress that this is just our understanding today. We don't know that this is really needed, but that's the subject of a different lecture. What's the rationale for allowing errors? Well, one basic one is that we tolerate uncertainty everywhere else in life. It's not clear why not in algorithms. Like even if we cross the street, we are not sure we'll get to the other side with 100% certainty. Okay, so that's errors in computations. Let's talk about errors in proof systems, in proofs. And it's actually very simple to introduce them because we have already said that verification is an algorithm. So we make it a probabilistic algorithm. So more precisely, this definition came in 1985 in 2 independent papers motivated by different motivations. Anyway, the way they define probabilistic proof systems is to let the verifier be a probabilistic machine, okay? And then, of course, you have to add to completeness and soundness that they happen with high probability. You can do this, it's formally easy, and we introduced in this definition errors also in proof systems. And this seems to be very different, at least certainly to mathematicians, where proofs are supposed to be holy, right? It's sacrilegious to have errors in proofs. It's true, and we'll just have to, accept this, and let's see what it gives us. But more generally, you should think of the kind of theorems for which you allow errors may not be statements like the Riemann hypothesis, but maybe statements in cryptography when you just claim that you are behaving as some protocol tells you to behave. So these are theorems that mathematics doesn't really care much about. And small errors, if you can reduce them, are perfectly reasonable. Also, for probabilistic verifiers, you can define what are the set of theorems accepted by it, so T sub B. And the collection of all of these, in analogous to the class NP, is called IP. And I want to stress that I didn't finish the definition yet. I told you how to introduce randomness and error into the proof system. There is one more ingredient, which is interaction between the prover and verifier. So let me complete the definition. In this paper, they're actually suggesting to generalize the class NP. One way is changing this deterministic to probabilistic. And the other way is to change the single message from a prover to the verifier in NP to an interaction in which the verifier can actually ask questions of the prover, arbitrary questions, and get answers, and then his decision to accept or reject depend on this interaction. So that's the acronym I is for interactive and probabilistic proofs. Whenever a new model is considered, and we have many in computational complexity, it's always good to think whether it's a reasonable model, let's say a reasonable model of proofs. And I would argue that it is. I mean, we can study models also if they are not reasonable, but certainly it's a good question to ask. At least two reasons why it is reasonable, at least intuitively, is one, in normal mathematical discourse between, let's say, two mathematicians working on something, it's normal to really ask questions, to really interact. Also, when we are teaching a class, we often get questions from students. We have to answer them to convince them. And so at least it's a natural framework to work with. But I claim that it's, regardless of whether it's reasonable or not, this framework, this new definition, is absolutely revolutionary. It's a revolutionary scientific notion. And I'll try to explain why. This introduction of errors in proofs and interaction had a huge impact on science and technology, on mathematics, and on our thinking about these notions. I must say that I will not discuss many important variants of this definition. It's not the only one. And there are versions in which you do it without interaction, or in which we place some limitations on the prover, in which the coins that are tossed are public, and so on. I will not go into that, but it's important for technological advances like cloud computing and issues of this nature. But I want to focus on the conceptual part and showing you examples of how this type of proof systems can have paradoxical properties which normal proof systems like NP systems don't have. And in particular, I'll discuss in a little detail the zero-knowledge proofs and probabilistically checkable proofs you'll see soon. Moreover, this kind of new proof systems lead to more proof systems. And I want to explain in what way we got to zero-knowledge proofs and to proof systems I'll talk about later, like multi-prover proof systems and quantum variants of them. So let's talk first about zero-knowledge proof systems. That was in the original paper of Kozak, Mikhaly, and Rakov. And they define a restriction of IP, this zero-knowledge IP. It is those proof systems, interactive proof systems, in which maybe I'll comment that the formal definition is quite complex, but the intuition is very simple. It's just what you here. What you demand is that it's an interactive proof in which whenever the verifier accepts a claim, namely believes the prover, then it learns absolutely nothing that it didn't know before. So it's a kind of magical or maybe paradoxical notion in which you believe the claim after this interaction, but you learn nothing more than you knew. So, if you try to think when was the last time you convinced a friend or colleague about something they didn't know without giving them any information, it's a proof that is convincing but does not give information, it looks very bizarre. In this paper, they gave a couple of examples of claims that can be proved in zero knowledge, some number theoretic claims. You think, how would you convince someone if you did have a proof of some non-trivial mathematical theorem? How could you ever convince them that you know a proof without showing them anything they didn't know? It looks a little ridiculous, but actually, it's very surprising that not only you can have it for non-trivial theorems, you can have it for all theorems. So whenever you have a proof, you can turn it into a zero-knowledge proof. This is something that we proved a year later after this original paper, together with Goldreich and Micali. And more formally, let me state it, this theorem exists under an assumption. The assumption is that one-way functions exist, which is the basic, the minimal assumption on cryptography. So it's something the whole world accepts and uses whenever they shop online. Under this assumption, like factoring is difficult, for example. Under this assumption, everything in NP has a zero-knowledge proof. So everything for which you have a classical proof, you can prove in zero-knowledge interactive proof as well. I'm not going to show you how, how to do that. That's a separate lecture again. But tell you a little of the impacts it had. In theory, it turns out to be the foundations of making protocols secure, cryptographic protocols secure for arbitrary tasks, whatever it may be, electronic voting or playing poker without cards or doing many, many things. Zero knowledge underlines a general way of doing that. There are many practical applications. This was actually implemented in anonymous cache settings or blockchains and many others. People have extended them from digital to physical in amazingly surprising settings like nuclear disarmament or anonymous DNA testing. I will not go into this. I want to talk about proof systems. I want to show you how it led to actually more proof systems, more games we can play with. And this is MIP. Go back to zero knowledge, and I want to explain how this came about. Well, I told you that this theorem, that everything has a zero knowledge, everything with a proof has a zero knowledge proof, came under this very natural assumption from cryptography. But you can still ask yourself, and we often ask ourselves in complexity theory when an assumption is made, is it minimal or can we remove it? And we ask ourselves whether cryptography is necessary for this theorem, or maybe you can have zero knowledge for free. And it turns out that the answer is yes and no. Yes, you need cryptography. Ostrovsky and I proved it in '89. In this setting, if you have a non-trivial zero-knowledge proof, then you must have cryptography. You must have one-way function. But also the answer is no. And how is it possible? Well, of course, it's possible if you change the model. So in the assumption, we are going to look at a new type of proof system. And this we did in a paper with Benor, Goldwasser, and Kilian. We suggested the proof systems which look like this. Two provers are trying to convince the verifier about the truth of some claim. And in this setting, the provers may develop a strategy together. They may discuss whatever they want about the claim, but then they are physically separated. And then the verifier can interrogate them, asking them various questions. They have no idea what was asked or was answered by the other prover. And then the verifier decides, as before, to accept or reject, and this should happen with high probability. What we proved that in this setting, in two-prover systems, you can actually get zero knowledge for free without any assumptions. In some sense, the physical separation of the prover replaces the computational assumptions needed for cryptography. Here, you don't need cryptography. But again, I'm not going to explain how to prove this theorem. What's interesting is to ask the same question: is it reasonable to have a model with two provers? And well, you can argue about that. Again, in some settings, it's more than reasonable. It's used all the time. Like if the police captures two people who are suspected of doing the same crime, they will often separate them and interrogate them separately to look whether the stories are consistent. Another maybe demonstration that it might be reasonable is that at the time we did it, the two institutions we were at, this was MIT and Hebrew University, decided to patent it. So they believe that it has a actual value in the real world. That may be a sign that it's reasonable. Of course, it was against our opinion. We thought nothing will come of the patent, and indeed nothing did come. But many years later, actually, it was used. But again, I'm not going to talk about practice. I want to go back to the theory and look at what we've done. So we introduced randomness and interaction in proofs, and we introduced it with one prover, with two provers, and in fact, in the same paper with many provers, 3, 4, n provers, and so on. And as we said in the beginning, we are trying to understand what's the computational power of a proof system? What is, how much computation is needed to check claims without a prover in any proof system? And in the beginning, there were trivial inclusions. It was very easy to see that every type of claim in IP is actually solvable in polynomial space. Everything provable in many prover interactive proof can be solved in this class that you may not know, called non-deterministic exponential time. But anyway, these are classes for power of computation. And they looked like very weak inclusions. People believe the upper bounds will be improved. And then, something amazing happened, like in a year or so. People obtained exact characterization of the computational power of each proof system. You don't have to like the acronyms, but we know exactly how much computation is required for IP. It's actually p-space. And for 2IP, again, the upper bound was tight. It was non-deterministic exponential time. And I want to stress what's written in blue is a conceptual meaning of these results. So it's not just equality between acronyms that you may not know, but really the first one says that it is efficient to verify claims like, I have a winning strategy for chess. This is strange because it's not a claim that there exists an object, but it's actually a claim that there exists a move I can make so that for every move you make, there exists one that I can make, etc., and eventually I win. This type of claim that I have a winning strategy for chess can be efficiently verified in this system. The second one, because it NX is a class much bigger than polynomial times, really says that statements that are not efficiently computable at all can be proved efficiently. And the last one I'm going to talk about, which gives a new characterization of the class NP by probabilistically checkable proof. So let me explain what PCPs are. This is a major theorem of complexity theory. So what are probabilistically checkable proofs? First, let's look at the standard definition of NP, in which you have a proof and verifier. It's not interactive. The verifier is probabilistic. There is an argument that prover sends the verifier or writes it. And we again have a demand on the verifier, and the demand is that the verifier is not allowed to look at the whole argument. It is allowed to read only a constant number of bits in the argument. It can sample these randomly, but it is not looking at the whole proof. So if again, it looks pretty ridiculous, but because if it's a 100-page proof, how do you hope to find a bug, if there is any, by looking at expecting just a few bits of the proof? If you imagine, I have no idea what Andrew Wiles is doing now, but let's assume he's trying to prove the Riemann hypothesis. He may eventually come up with this volume of hundreds or thousands pages, and whoever checks this proof can look only at a few bits of it. So again, it looks pretty paradoxical, and again, the answer is that it's completely universal, like zero knowledge. Turns out that whenever you have a proof, a normal mathematical proof, it can be turned into another proof, which can be checked with this few spot checks. This is a PCP theorem of Aurora et al., as I mentioned before. And again, I'm not going to tell you how it's done, but it has, again, huge impact. I mean, maybe the most impressive one to mathematicians, but was not formalized yet, is that this allows to referee papers just in seconds. Instead of asking the people to write their papers in normal mathematical form, they just convert it. There is always an efficient conversion into another, again, mathematical proof, which is of this PCP form, and then it can be verified by few spot checks. The real impact of this definition comes in things mainly in optimization, where it enables us to do things we had no idea how to do. We always knew, since NP completeness, how to argue that certain optimization problems, it's very hard to solve them optimally. What this allows to do is that it's always possible to argue the hardness of approximating them, let's say within a constant factor or within any particular factor. It enables proving hardness of approximation. It had a lot of impacts on coding theory and complexity theory that I will not get into. And also on technology. I mentioned cloud computing before, and this has a very important impact on delegation of computation, blockchains, etc. Okay. So I have 12 minutes. I want to conclude with quantum proof systems. So we saw that probabilistic proof systems, in the single prover or many provers, we have a complete understanding. And now we are going to move into quantum proof systems. As before talking about quantum proof systems, I'll talk about quantum computation, and then we'll move to the proof systems. Again, I'm sure many of you have seen this, but I'll give you a one-slide introduction. It again rests on this belief that quantum mechanics is correct and nature provides us access to quantum phenomena, and so we can integrate quantum mechanics to algorithms. In particular, Manning and Feynman suggested that we build computers that rest on this theory, namely they can manipulate quantum superpositions using unitary operations. And let's see the power of this. Well, even formalizing a quantum Turing machine took time, but this was done. We have a notion of the analog of P for deterministic and BPP for probabilistic. We also have BQP for efficient quantum algorithms. So we have a notion of what efficient quantum algorithms are, and their power, was begun to understood slowly, and then like an earthquake happened, a volcano erupted, and Peter Shaw wrote this paper in which he proved that in this hypothetical machine, quantum computers, you can efficiently solve factorization of integers, discrete logarithms, and these are not arbitrary problems. These are the problems on which most security systems in the world rest. So this was a shock, and it caused a frenzied attempt to develop many things. First of all, the technology that will allow constructing quantum algorithms, and billions were invested by governments, by companies, and so on. And huge progress was made on this technology, although from the point of view of factoring, it's still weak. I think the biggest number that these machines can factor today is maybe 65. But it does other amazing things. Yeah, we don't know whether they can be built or not. Of course, there were also friendly attempts to develop cryptography that can fight against quantum computers, right? That we may be able to hide secrets from quantum computers. So there are other problems, not factoring discrete log, but for example, lattice problems, for which we have no quantum algorithms, and they may be the basis of future cryptography. People continue to develop quantum algorithms, and we know a few more, but not many. And what I want to talk about is how it enables more games, more models of proofs that we can play with. So let's do that. We don't care that nobody can build quantum computers. We are going to nevertheless look at the proof systems they define. So now we allow the verifier to be a quantum algorithm. And of course, the provers can do what they like, so they can be quantum. And then people started defining these classes. The one prover version, so whenever I have a star, it's a quantum version. Interactive proof with quantum players. And understanding the computational power here took a decade. It's much more difficult than with classical proofs, but turns out that it's not more powerful. With quantum proofs and one prover, you cannot do more than with a classical, in the classical setting. It's still p-space. People also define a many-prover analog, like two-prover or many-prover analog of quantum proofs. And here, it took many years just to show that this class is at least as strong as the classical one. It's not obvious because you add power both to the verifier and to the provers. But this was done, and everybody expected that soon equality will come and it will be like the classical case. But here came a surprise where Natarajan and Wright showed that actually you can do more. You can do non-deterministic double exponential time in this many proof system with quantum provers and verifiers. And people pushed it further until the most amazing result of 4 years ago, that in this proof system, let's say two provers, interactive proof with quantum participants, you can efficiently verify claims that are, not even computable at all, not in any time bound. So remember that RE is a class of recursively enumerable functions, which includes the halting problem, that is not computable. That's what you prove. And it's sort of mind-boggling that a statement that's not computable at all can be verified by some notion of efficient verifier, this quantum notion. You can at this point, if you're a mathematician, you can say, okay, this complexity theorists love games, and they are playing with these weird models that have no, fit in reality. And okay, maybe it's surprising, but that's totally in the realm of complexity theory. The further surprise is that this theorem implies the resolution of fundamental questions in mathematics and in physics. It provides counterexamples to the Thirson problem in quantum information theory, very basic question. It provides a counterexample to the famous embedding conjecture by Kohn. I was just in a conference a few months ago where Gilles Pizier, a famous analyst, was talking about the 500-page book he wrote about everything known on the quantum embedding conjecture. And he said, then this theorem came, what can I say? And it looks correct. And it was a great shock in the von Neumann algebra part of mathematics. And it disproves other conjectures. So this theorem about computability and efficient verification turns out to have a fundamental impact on mathematics. So in the last slide, I want to tell you one way to look at it that actually, or a couple of slides, that is actually related to a fundamental question in quantum mechanics. This work of Einstein and collaborators on whether quantum mechanics is true or not. So let me tell you about this. First, I need to tell you one fact, is that when you have many provers, like two provers, it turns out that there's never a need to ask more than one question of each prover. So one round proofs are enough to get all the power of two prover interactive proofs. And also it's easy to see, you basically, everything is determined by the verifier function. You can define the value of such a system is simply the largest probability with which the provers can convince the verifier to accept a particular function on the questions and answers. And of course, we said that, if the claim which is embedded here was true, then this number will be close to 1. If the claim is false, then this number will be close to 0. So basically, we want to approximate this value. You can think of it as a game, G, basically encoded in the verifier function. So for every game, we have a value. This value doesn't change if we allow the provers. They cannot communicate, but they can both look at the same random string. This is easy to check. That's a classical side. The quantum side is exactly the same picture, only that because we are quantum now, we allow the provers not just access to a random string, but actually to a quantum state. So in a sense, provers are entangled. And when they are entangled, this is a different game, and you can ask what's the maximum probability, we call it value star for quantum, that this type of provers can convince the verifier. And for computer scientists, we said this about about approximation. What does it take to approximate this value or that value? And we know the computational complexity of this approximation problem. One is non-deterministic exponential time. The other turns out to be not even computable. But physicists look at this differently. And Einstein and his two postdocs, Podolsky and Rosen, almost a century ago, proposed the famous EPR paradox, which, if you think about it, looks very much like a two-prover system. They suggested many people, if you never saw it, doesn't matter. But if you saw it, a collision between electrons that produce photons going in opposite direction at the speed of light, and somehow, if like quantum mechanics said, they are entangled, when you measure them, it seems that information is transferred faster than the speed of light. But the EPR basically called the quantum mechanics explanation a quantum non-local game, and the possibility that information travels faster than the speed of light, they called the spooky actions at a distance. And they were trying to find explanations. Physicists were trying to find classical explanations of this phenomena by classical local games, which are basically two-proof proof systems. And this is what's called in physics hidden variable explanation. And it took some decades, but Bell and then many others proved that separation between these two values. So this was known decades ago, that actually quantum provers can have strategies that cannot be implementable by classical provers. In other words, the motivation of EPR was basically asking whether quantum mechanics is reasonable or is complete. The physics side provided many examples of games in which the quantum value is higher than the classical value, which led actually to tests of these values in the lab. And these tests basically confirmed that quantum mechanics is true. There is some phenomena which you cannot explain classically. On the computer science side, rather than look at examples of games, as we do always, we look at the class of all possible games, all possible problems in a certain class. And this is a class MIP star that I define. And again, repeating what I said, the sequence of works which actually rely on all the methodology that was developed when proving your proof systems, classical ones, and all these techniques that were developed, and many more, in order to get to this conclusion that MIP star can compute the halting problem and other recursively enumerable problems. And this computational result led to structural understanding in various mathematical areas, which I mentioned already. Okay, good. So let me conclude with some comments. We saw many types of proofs. We saw that allowing interaction, randomness, and errors in proofs lead to really magical proof systems. And I talked about some practical implications, but I want to stress that theory, as happens often, predated this use in science and math and society. There are many connections between subdisciplines revealed by this work on proof systems, like in the last slide. I hope I demonstrated the power of following this methodology of modeling and minimizing assumptions, algorithmic efficiency, classifications, etc. This is my final slide, which I always put in the last 5 years. So 5 years ago, I published this book, which is an invitation to computational complexity, my area, and its interaction with mathematics. You don't have to buy the book. It's free on my website. That's it. Thank you very much. And I welcome questions from the audience.
Thank you, Professor Avi, for that amazing talk. We have some questions. We have a first question by Carlos Ernesto Ramirez Ovalle.
Let me just remove maybe remove the talk from not share it. How do I do this?
I can't do that for you.
You can do this for me.
Yeah.
Okay. So then I will be able maybe to see who is asking questions. Anyway, what is the question?
The question is it possible to see these interactive proofs as a kind of two-person game in which the winning strategy culminates in a valid test?
Which one? The one-person interactive proof? Well, basically, you can, yes, the answer is yes. You just have to remember the computational limitations on the two players. That the verifier is efficient, and the other, or the others, the provers have this infinite computational capacity, and they can be classical or quantum. But yes, the value is similar to the value of other games that we are more familiar with. We are looking for the best strategy, thinking as if the prover wants to cheat the verifier, and the question, with what probability can he do it if the claim is false? Yeah.
Okay, thank you, Professor.
Every input defines a different game, right? For every
Okay.
input, yeah.
Again, Carlos Ramirez says, for PCP, how to give a representation of the probabilistic component in the structure of the game?
Yeah, so what happens is that this PCP format of a proof, which is something you can get efficiently from a normal format of a proof, will be a sequence of symbols like a proof. And it just has a remarkable feature that a verifier that selects at random appropriately some few bits of the proof is able to determine whether it's correct or not. And of course, for this, it must be the case that if there was a bug in the original proof somewhere, then this translation into PCP format will spread this error somehow all over the place so that random selection will catch it. And of course, otherwise it wouldn't be true. So in some sense, you can find an analogy in error correcting codes where the encoding takes even a change of one bit into change on many bits in the encoding world, and then well, you can correct them, or you can check them by probabilistic means, etc. So there's some analogy, and in fact, this analogy is also in some sense used in proofs of the PCP theorem, but because proofs have a semantic meaning, right? It's can be true or false. Unlike coding, where it's just information, there's much more work to do.
Okay, thank you, Professor. Anybody else ask questions? Maybe in the auditorium?
Yes, in the auditorium, Professor Andres Villaveses.
Yes.
Right. Well, first of all, thanks a lot for your lecture. I have actually two questions. One of them is kind of more sociological, mathematical, and it is, you spoke about all these, what you called 50 shades of proofs at the end, which you illustrated with the quantum verifier and the game and all the variants of and the errors. But on the other hand, you have all the program, that started with Voevodsky and then has been, growing into all these lean-based proofs that some people are saying. Even Tao recently, 2 months ago, he said that he saw part of the future of our mathematics, kind of transferring those proofs, but they don't seem to, at least as far as I see, they don't seem to incorporate all those notions of proof. So how do you see these two sides, your 50 shades of proofs versus what they are proposing?
Yeah, so I think that these are parallel developments, and both are interesting and important. The one you are talking about has to do with proof verification, like this one. But here you are simply not allowing errors. So as we know, the way we write mathematical papers is not exactly in a formal language. We write in freestyle, and we write all sorts of things like the proof of claim 2 is the same, similar to claim 1, or we write it is easy to see, and anyway, we write in English. So lean and other and other similar languages allow to formalize, first of all, formalize proof, formalize in a sense that a computer program can verify it because it's written formally, so it can be verified that it's correct, something we would very much like to know about our proofs. The probabilistic proof setting just has different wishes and different motivations. Some of them are theoretical, some of them are technological, which is allowing various properties of proof systems that cannot be hoped for in the classical ones, namely, things like zero knowledge or a host of, delegation of, if your iPhone is talking to the cloud and the cloud is computing something for it, why should you believe that it's true? So it's a very different type of questions and need different type of proofs where you are willing to tolerate errors. So in summary, these are two parallel developments and they are important for different reasons.
Yeah, thanks. May I ask one more question? I had a kind of more internal question. There used to be a time when complexity theory was running in parallel with finite model theory, and some kind of model theory was there, and then they kind of split for a while. But there was the Erfurt-Fraise game, which was a game not of verification, like the many variants of games you described, but more the comparison game. How do you give two structures to huge databases or two models, infinite models, and one player knows that they are different, and one player says yes, but they're almost isomorphic in some sense. It's a kind of dual game. Do you have anything to say?
I know about these games and other games in model theory. And in fact, you can say that finite model theory is a part of complexity theory in the sense that we use it, or descriptive set theory. It turns out that some purely computational models like NP, computational classes, have description in descriptive set theory. So it turns out that everything in NP is exactly, the classes in NP are exactly the classes describable by monadic second order formulas. So, yes. And there are many other analogies. So complexity classes can be captured by model theoretic models. And not only can they do it, but actually techniques like Erfurt-Fraise games can be used sometimes to prove lower bounds on the, let's say, the size of certain type of circuits computing certain functions. There's also the area of proof complexity within computational complexity, in which you try to study the power of certain types of arguments, like arguments using algebraic techniques or arguments using certain logical techniques, and they can be captured by proof systems by propositional proof systems even, that I did not discuss at all in this talk. So there are a lot of connections with it didn't die out, I would say, but certainly because we are stuck in computational complexity on proving lower bounds. Let's say we cannot prove that any function is hard, right? The previous NP only asked to prove that some natural problem requires more than polynomial time, maybe requires brute force search. And some of the techniques in model theory or any techniques in mathematics don't seem to help us so far in resolving that.
Okay. Well, thank you very much. Thank you.
Sure.
Thank you, Professor. Another question? Maybe I have one. Let me see if we have, okay. You said that, for example, a proof can be made as an interactive proof or a two provers interactive proof. I want to see if I want to check if I understood well. that is constructive, that inclusions are constructive in the sense
Yes.
that you, okay.
Yeah, the inclusion, the fact that IP generalized NP is constructive and the 2IP generalized IP is constructive. All the transformations I talked about, like taking a proof, making it zero knowledge, or taking a proof, making it PCP, they are all done by efficient algorithms which are known. These are part of the proof of the theorem. Yes, all constructive.
Very amazing. Okay, Professor. So thank you again.
Thank
Have a
you.
good day. Thank you for supporting our conference.
Bye-bye.
Bye-bye. And for our participants, we will start tomorrow at, I think it's 7 a.m. Colombian time or 2 p.m. in Central European Summer Time. First talk tomorrow will be in charge of Professor Efim Selmanov. So have a good rest of the day and bye-bye. Thank you for being here.